Yeah. All right, great. Yeah, no problem.
Yeah. So yeah, so I was teaching responding to recently to the design
Just like I think just yeah, I think yeah, I actually read with yeah, he's there.
Hello, everyone. Yeah. Welcome and thanks for coming to Chicago in this early morning. We have guests all around the world, from Japan, from Germany, from Swiss, and thanks everyone for attending this event. So I have the honor to introduce Dr. Ana Machado, who is the PI of iDASH, San Diego-based NCBC, National Center for Biomedical Computing, which has been hosting this privacy workshop 6 years in a row. And Dr. Ana Machado is the Associate Dean of Information and Technology at UCSD, and she has led numerous big biomedical projects in the intersection of privacy and security. So let's welcome Dr. Ana Machado to welcome us.
Thank you, Jonathan. Can you hear me in the back? Yes. Okay, thank you. So I'll be brief because I know you have many more interesting things than my intro here. But I want to thank you all for coming to Chicago for this event. It's the sixth event. iDASH itself is 7 years old now, and we've been very successful in presenting new technologies that have been implemented in some real-world settings. So I would start, this is a slide that I show to audiences that are not as familiar with privacy issues or re-identification issues. And I say, well, big data are a big deal because so-called the identified database of condition X can reveal information if you match someone into an observation in that database. So that's the primary thing that people are not understanding. People say, well, we have whole genomes, but they're not identified. They don't have names, they don't have social security number, addresses, and so on. So it's okay to compute with them without any protection. And my point is exactly if those are part of the database of a particular condition, by determining that a genome is in there, an individual is in there, you're revealing information that you shouldn't have. And this is not something that everyone is very familiar with, so I try to reinforce. I also get into this dilemma of doing the right thing. So it's ethical to share the data. As you know, electronic health records in the United States, as long as they are de-identified, which is the removal of 18 identifiers as determined by HIPAA, then you can share them without asking people about that. And is it ethical to do that? Or also, is it ethical not to share? Because if we can get new knowledge from those data, and that is not shown to harm anyone, shouldn't we continue to do this without, being over concerned about these attacks that we don't know if they happen or if they don't happen, right? There hasn't been a major one in the news and so on, but there might have been other ones that we don't know about. So what are the solutions? And it's, as always, it's technical plus policy. But also I would like to add participant-based solutions or strategies. So many years ago, and this was like 5 years ago when I wrote this little perspective article, what we envisioned was a data center or a system where you could share the data in a protected fashion. And what we said at the time in the iDASH Center was that we would have the policies and the technologies. And different people would contribute software, would contribute data, and we would make those data available in different ways. In a traditional mode, by downloading the data with protections, and then differential privacy plays a major role here. Or we would invite people to compute in our data center because that is more controlled and it's logged and it can be audited more easily. Or we would follow a third model, which is now very common in clinical data research networks, which is to distribute the computing to where the data are. And as you know, you've done some challenges in many of these different strategies. So I think it all connects, we have different projects that connect to this goal of sharing data with the protections for the individuals. We also develop now metadata so that you can find those data more easily. And as part of it, the reason I wanted to mention this other project, which is the Data Discovery Index Consortium, is that there is a small portion of it that relates to metadata on access. So that too, we need to start making more clear in the data sets we're going to share. Who we're going to share, how it's going to be accessed. So when you're doing a search for data sets, if you're not willing to sign certain agreements or get IRB approval, then they don't even show in your search. So this is metadata for access that has been determined, and we want to use in our system called DataMed, which is equivalent of PubMed, but for data sets. Another project that we're involved is the authority-funded clinical data research network that involves 14 health systems now. So it's more than 24 million people. It's the whole data warehouse for the VA, it's the Veterans Administration in the United States, plus University of California, plus some clinics in LA, led by USC, plus Safety Net Hospital and a very large private hospital. We also have collaboration of other CTSA colleagues in this. And this network is essentially using that premise that the data remains federated and we bring competition to the data. Another project that we are involved with relates to precision medicine, in which the model is similar. We are centralizing the data at UCSD from 6 systems, including our own. And then those data will be submitted to the data coordinating center, as well as data that will come from the individuals themselves and from monitoring system. So we are using a particular standard for the common data model, and we intend to utilize the same strategies that we're doing for clinical data research networks. So there are issues of linkage that you all here probably are interested in. There are issues of how to compute with this data without compromising the privacy of individuals. And I would say the privacy of institutions start becoming very important as well. The privacy workshop, for those who haven't come before, again, is the 6th one. It was made into challenges for the past 3 years, so this is the 3rd year in which we will give awards and judge what the submissions were. There are groups around the world, so it's very exciting to have you all here. This is a picture taken last year where we were in San Diego, so I doubt that Sean has brought this big check here to Chicago, but it's an incentive, small token of appreciation for you all coming here. So I'll talk about 2 things quickly, and you will talk a lot about technology solutions, and I'll just say to you, bear in mind that there are people-centric solutions as well, either in the form of an institution-centered data broker, which is the current way we do clinical data research networks, or something that we have experimented at UCSD, which is patient-defined data sharing permissions, consent management, and I'll talk just a little bit about that. So this is an old consent for care example from a particular institution, and what says that is your biospecimens, your data can be used for research according to the law and according to approvals of institutional review boards, if so deemed necessary. And a lot of patients don't know about that. And if you go to the doctor with a broken leg, that record can be used for research. So we developed this system on top of our electronic health record data on our clinical data warehouse, in which patients would determine who they want to share their clinical data with. And this is a pilot project at UCSD, so that we honor the desires of those patients. And why is this different? Because most of the projects before were hypothetical. You would ask, what would you do if you had this control over your own electronic health record data, over your study data? And this was real. For the period that we were studying this, we would honor the preferences of the individual. I was warned not to do this project because if patients started withdrawing a lot, then that would damage our research component of the health sciences. Though it was a small pilot, and as we saw later, patients do not withdraw to a large extent. So what happened in here, the interface has changed, but it's similar to this one. You have 3 columns. The columns tell who you want to share your data with. If it's UCSD and the associated VA. If it's any nonprofit institution, or it's also for-profit institutions. And we wanted to have each category of items to be selected by the patient, or in this case, unselected, because currently we can't share all of those without the identifiers. And patients made their choices, so just to summarize what they did into what matters for precision medicine, for example. We saw that the rate of removals for particular items was variable. Some items are removed more than others. And also there are people who will share everything with everyone. Some people are very fine with that. Most people would share something with someone, and that is, they will share most of their items, and they will, particularly with nonprofit and with your own healthcare institution. And a few people won't share anything with anyone, and those, again, were recognizable. So the lesson here is, if you want to get as many people as possible, you have to allow for the sharing to occur, possibly only through the control of the healthcare institution that patient is getting care from. Because people trust their healthcare institutions, and many trust their healthcare institutions to decide what to do. So for any nonprofit, for example, people are comfortable with that. And the number of people who remove items is very small. That possibly not sufficient to bias your data very much. But then again, depending on what kind of institution you're talking about. So, and this was only for research. Now imagine if we had asked the question, can we share this with anyone? And we haven't asked that question, but that would be yet a smaller pool that would like to share everything with everybody, like I said here. So the reason I say this is because as you develop your technical solutions, think about how to combine that with people-based solutions. Because if you are studying risk, what if people could decide what risk is sufficient for them? So if it's very risky, then I will only share with my own institution. It's not that risky, then I'll share with for-profit institutions as well. So there is a component that you need to add to what you think about in terms of technical solutions, so that the combination of them is what actually goes into practice and becomes part of protocols and how to conduct certain studies. So with that, I just want to thank a lot of funders for that and say that nothing is perfect. I took this picture last year in San Diego, and as you can see, there are a couple of clouds over there. There's a dog. But other than that, we hope to continue to do this workshop, hopefully back home there. And I would like to thank the organizers, all of them, for it's a lot of work involved. And today you will see the winners of this competition. Thank you.
Thanks, Dr. Marcello, for the welcome. And we had a pleasure and honor to have Dr. Christine Lauder to give us the first keynote speech. And she has been a great friend and a great supporter to our workshop. And she is a principal researcher and a research manager for a cryptographic group at Microsoft Research. Her personal research interests include homomorphic encryption and cloud security and privacy, including especially privacy for healthcare. Dr. Lauter is a fellow of American Mathematical Society and currently serving as the president of the Women Association for Women in Mathematics and on the council of AMS. She is also an affiliated professor in the Department of Mathematics at University of Washington. She completed her PhD in mathematics at the University of Chicago in 1996. And she was a T.H. Hildebrandt Assistant Professor of Mathematics at the University of Michigan. In 2008, Dr. Lauter, together with her co-authors, was awarded the Shelfridge Prize in Computational Number Theory. And let's welcome Dr. Lauter.
Sorry, here we go. Wasn't quite set up yet. So thank you very much. Thank you for inviting me, and thank you especially to the organizers of this workshop and this competition. It's a great honor to be part of it and to be here to speak to you. So I'm going to kind of try to keep this brief in the sense that we already had a very nice introduction, and actually what I was going to say kind of follows perfectly on what's already been said. So we kind of know what the context here is. The title that I picked, How to Keep Your Genome Secret, is just one that I've been using because it's kind of fun. People seem to like it, but it's a little misleading because the point is that we don't want to just keep our genome secret, right? We want to be able to have our genomic data being pooled for medical research because that is overall going to advance the human condition to enable research and study. So the point is that we're interested in genomic privacy for a number of reasons. The privacy is really important now that we can generate so much more human genomic data cheaply. But the privacy risks, things like disease disclosure, potential actual discrimination, employment discrimination, that kind of thing, other types of collateral damage. And so what we're really trying to do is we're not trying to keep our genome secret, we're trying to preserve privacy for individuals while allowing for medical research, which can benefit human health, interaction across different data sets, and convenient and cost-effective cloud storage and computation on our data. So to me, this sequence of conferences and competitions that iDASH has been running is extremely important. I think it's a great model. I'm a mathematician. I come from the mathematics community. I've actually been giving a version of this talk over the last year to mathematicians and computer scientists in cryptography, and kind of highlighting the iDASH and this series of competitions. I think it's such a great model that having support from NIH and using this energy to build an interdisciplinary research community. So I think if we took a poll of hands around the room, people are from all different communities, from bioinformatics to computer science to mathematics. It's very exciting to have everybody coming together. And it's really necessary. I certainly cannot work on genomic data without some help from an expert telling me what is this data, how to parse this. I don't know any of the algorithms, I don't know any of those things. On the other hand, I know the mathematics behind the encryption technology, and I can work on that side of optimizing things. So the other thing I think is really important about this series of workshops and competitions is that really it's creating benchmarks. So each year you're kind of choosing tasks, and last year at the end of the workshop there was a discussion about what tasks could be considered for the following year. And so as a community, you're choosing tasks, and then when teams come together and compete and put their best foot forward, their best solution gets submitted, that really creates benchmarks for for these new tasks, and these benchmarks did not exist before. And it's also a snapshot for policymakers and funders of the state of the art. What can be done? How efficient is it? Where are the challenges? Where do we need to move next? Also, just having a competition, I mean, I think it inspires people, right? It really accelerates research in this area. So I've actually explicitly suggested this to NSF for funding within mathematics and computer science. If they really want to make progress on strategic areas, these competitions are obviously a lot of work to run, but they're a really amazing way to accelerate research in an area. And so finally, I wanted to mention, I think this is a very important point. I think this community that's being built here is also the foundation of a path towards standardization. So a lot of this new crypto technology, one of the main things that I get asked in every single meeting with product teams or external customers is this technology standardized? Is it NIST approved? Is it FIPS approved? Is it, you know? So this standardization is going to need to happen in order to get widespread adoption. That's, I think, a pretty clear statement that everyone would probably agree with. So I think having those conversations, and we've started having that type of conversation with even many of the people that are here in the audience today. So just to advertise the kind of the workshop and the success of this a little bit, these were the articles from last year in Nature and Genome Web about the competition last year. There have been a few articles about the homomorphic encryption work in particular that we've been doing last year. Quite a bit of progress that we made, actually following up on the competition, releasing a library called SEAL, which I'll talk to you about in a little bit more in a minute, and making a lot of progress on what types of tasks can be done with homomorphic encryption. So there's been a lot of good press, and you know, kind of why all this excitement, and I think it's what I've already said about the importance of the contest. It's a really fundamental problem, combination of exploding research in genomic data coming from the ability to sequence the human genome more cheaply, combined with this high risk for personal privacy and the fact that we're bringing all of these communities across all of science together. So last year's competition, these are just kind of the highlights. As Lucille said, it was held at UCSD, focused on the tasks last year were genome-wide association studies and sequence alignment. So what I thought I would do this year is talk a little bit about the 3 tracks. What I think is really neat is, so last year we basically had kind of a multi-party computation and homomorphic encryption track, and I believe it was the year before that in the competition that it was differential privacy. And so now we have kind of these 3 tracks this year with all 3 of them, which is really cool. And what I did was to just kind of think about this a little bit more, just kind of stand back and think about it from a high-level perspective. So I want to just kind of compare these three tasks and the different scenarios that they dig into and the different technologies. And then at the end, I'm going to show you some demos, which are primarily focused on the 3rd track, but which are just kind of fun to look at. Okay, so really these 3 tracks, the scenarios are very different, if you think about it. I mean, the first one with differential privacy, often, I don't know how many of you have this experience, but when I'm talking to customers or internal product groups, people usually have no idea what the difference between differential privacy and, say, homomorphic encryption-based solutions are. They'll just kind of have this, you know, massive idea of, okay, privacy concerns. We're concerned about privacy. And so people that aren't at the level of thinking, well, you know, what is this technology used for? They've heard the words differential privacy, they've heard the words homomorphic encryption, but what's the difference? So I kind of like to think about it from the point of view of the scenario, like what are you trying to do? So with differential privacy, to me, it's very clear that what you're really trying to do is kind of answer like database queries on aggregated data. So if you have one person's genome and you're a database and you answer questions, then obviously you're answering questions just about that particular person, and that's leaking a lot of information. But as Lucilla pointed out, people think that when all the data is put together, lots and lots of people, and it's anonymized, that it doesn't leak information about a particular person. But we know that it does, or it can. And so differential privacy is trying to answer questions, say for research scientists coming and trying to query some large database of genomic data and get answers, but they are going to be, with differential privacy, they're going to be approximate answers about aggregate statistics. And the challenge there is that to see that these answers can actually be useful for research without leaking the information about the individual's data. So that's the kind of scenario that I think about for differential privacy, and that these are aligned with the 3 tracks. So you can see the first track is practical protection of genomic data sharing through beacon services, and so I'm sure we'll hear more during the day about beacon, but beacon was essentially designed to exactly answer this type of query. The second track is essentially related to secure multi-party computation. And what it's trying to do is, again, it's just a very different goal. It's trying to enable collaboration across kind of mutually distrusting data sets. So I think of a perfect example of this is, let's say, 2 hospitals, 2 clinics, and they want to pool their data, or even could be more, could be 4 clinics or 8 clinics or whatever. They want to pool their data and build, for example, a predictive model, some kind of machine learning based model, but not just from their own data set, but from all the data sets together. So that's a really concrete task, and we actually have a nice demo of that from the same team that competed in this 3rd track, the SEAL team. I'm not showing that demo today because I'm not an expert at showing that one. I would need Peter over here to show it for me. But so we have worked on that kind of thing. And this is very closely aligned with this second task. So track 2 is the privacy preserving search, basically, of similar cancer patients across organizations. So multi-party computation is one of those things where for computer scientists in cryptography especially that work on multi-party computation, they basically think it's the magic pill that can do everything, which is kind of true in some sense. I mean, multi-party computation can, kind of abstractly defined, it is very, very general. It can do many, many, many things. But what I like to focus on is more not what it can do abstractly, but more concretely the scenarios that it really enables. And the one, for example, to differentiate track 2 from track 3. Track 3, where you're just doing secure outsourcing to the cloud, that is a scenario which makes perfect sense for homomorphic encryption and really not as much sense for multi-party computation. There's a lot of extra weird assumptions that you would have to make in order to say that you can solve the 3rd problem with multi-party computation. Whereas track 2, where you're fundamentally taking 2 data sets under the control of 2 different entities that do not want to share the data, they do not want to share their keys, that does not work with homomorphic encryption. That's something where you really need the multi-party computation. So there's the kind of major difference between those 2 tracks. So as I said, so track 3, this secure outsourcing, this is very important, and also for us from a business perspective. So I think it's interesting to see the perspective that you heard from Lucilla when you think about, for example, an academic hospital with a lot of patient data and the perspective that the hospital has versus, for example, my interest in track 3 is really from working at Microsoft in a more commercial perspective. We have a commercial cloud. We have built like 5 $2 billion data centers around the world, right? I mean, so we have a business, which is our cloud business, Azure, and so we like to be able to provide services, cloud-based services to customers. And so this is a perfect match with Microsoft's business interests and other companies' business interests that run cloud services, because they're basically interested in providing either consumers or enterprise customers, or and large entities such as hospitals or clinics, the opportunity to store their sensitive data in a public cloud and have it be securely stored in the long term and be able to get some services and computation and kind of results computed on that data. Okay, so I have kind of three, just to kind of recap, I have three pictures here now of these scenarios. So this is kind of track one. The idea is having some common database that everybody can query, any kind of researcher or doctor, but the queries are going to be answered only kind of approximately. And that way, the nice thing there is that if we do have a secure solution, people, including not just a hospital, but also individuals, feel comfortable contributing their data to this platform if they feel that it's not going to be misused or leak information about them. The second track is this multi-party computation. I call this kind of adversarial cooperation. The idea that you'd still be able to compute something and everybody learns the output, but the private inputs do not have to be shared. And then the third picture is the kind of outsourcing of storage and computation to the cloud. So you have some private data, which is encrypted locally. It's uploaded to the cloud. The cloud stores it long term and can do computations on it and can return encrypted results, and these results are only decrypted locally by the client. So look, these are kind of the three pictures. And so now let's talk a little bit more about the technologies. Okay, so differential privacy is actually not something that I or my team have personally implemented, but it was actually proposed by Cynthia Dwork from Microsoft Research, and Microsoft Research had a team working on it for a long time that developed PINK, which was an implementation. I think there's other implementations and attacks, and there's been a lot of great research in this area. So, I mean, basically at a very high level, differential privacy is essentially adding, it's a statistical technique. It's not really a cryptographic technique. It's adding noise to data, or kind of answers to queries in order to hide private information. So the goal of differential privacy, kind of a rough definition of it, is that kind of a query answering model will be differentially private up to a certain amount if, when you answer questions about two different data sets that differ only by one record, the answers will not differ very much. They'll differ only up to that amount, kind of epsilon, they call it epsilon delta differential privacy. So that's kind of a nice definition, and I'll talk a little bit more in a minute about some of the challenges. So multi-party computation, so there's a couple of different solutions or building blocks for multi-party computation. So surely when we hear more about the solutions today, people will be talking about what they actually did here. So one of the main building blocks for multi-party computation is Yau's garbled circuits. So it's an interesting kind of historical perspective that Yau proposed this technique in the 80s. So we're really talking about kind of a 30-year-old technique. But it laid dormant for a long time because people thought of it as being so impractical. And so it's only really recently in the last 10 years that the community has really dug in and it's kind of exploded, making it so much more practical through things, so these types of optimizations, circuit optimizations, these kind of fast cut and choose protocols, fast OT protocols, also kind of streaming data, all kinds of different innovations. And so it's really impressive and fun to see this technology come into the kind of practical realm after having been just kind of a theory relic for literally decades. But there's also some more kind of algebraic mathematical building blocks that are very important for multi-party computation as well. So secret sharing that can be built on, the classic example of the secret sharing technique is basically the kind of polynomial interpolation idea. And this has been generalized, and there's other kind of mathematical algebraic instantiations of this technique as well. So these are the kind of underlying building blocks for multi-party computation. You can already see very, very different from differential privacy, these kind of statistical approaches to handling data. And then finally, homomorphic encryption is fundamentally nothing more than saying that you should be able to encrypt data in a way that is homomorphic. Homomorphic meaning if you operate on the data in the clear and then you encrypt it, that should be the same as if you encrypt it and then operate on the data. And that is the definition of homomorphism, really, is that it preserves the operation. So basically means you can go around this diagram either way and you should still get the same thing. If you're a client with your data, you should be able to either encrypt it and upload it to the cloud and then have the cloud operate on it, or operate on it yourself and then encrypt that and send it up to the cloud. And the answer should be the same thing when you decrypt it. And this is what we want is to be able to implement any circuit. So we want not just homomorphic encryption under addition, but also under multiplication, so that you can do any kind of and or circuit. So the mathematics, I don't have a lot of complicated mathematics slides to show you this early in the morning about homomorphic encryption. But the idea is that the kind of analogous historical snapshot to the Yao's garbled circuit protocol is homomorphic encryption basically laid as kind of an unopened, unsolved problem for about 3 decades. And it was really in 2009 with Gentry's proposal that we got a kind of a breakthrough, and his proposal was not really very practical or implementable, and even the hard problems were not very well understood. But it gave ideas that quickly led to many breakthroughs, and the systems that we use now for homomorphic encryption over the last 5 years are based on a very, very closely related problems in lattices. So hard lattice problems have been around for decades. Things like finding shortest vector problem is a well-known hard lattice problem. And so these new mathematical systems that we use are very closely related to these hard lattice problems, which, when you think about it, for any of you that work in cryptography, is very different than what's used in mainstream public key cryptography today. If you think of RSA, based on the hardness of factoring, if you think of elliptic curve cryptography or the discrete logarithm problem in other abelian groups, these hard lattice problems are very, very different. And so the nice thing about it is not only that these are providing solutions for homomorphic encryption, but they are also potentially what we call post-quantum solutions, in the sense that as a quantum computer becomes more and more of a reality, we have to look at what algorithms we're going to be able to run on quantum computers that can break standard cryptography. And so far, these problems, these kind of new or different problems, such as hard lattice problems, we do not know polynomial time solutions, quantum solutions for breaking these. So this is kind of a little snapshot of the technologies that we'll be talking about throughout the day. So these 2 slides should maybe come more at the end of the day, but since I'm speaking in the beginning, I'm going to put them up there anyway. So when you think about it, just at a very high level, like, what are the challenges for these technologies? And that's, every time when we have one of these tasks and we're trying to get the best possible solution for some concrete task, we're kind of pushing on these challenges here. So I'm not a real expert in differential privacy, but one thing that's very clear, even from like the iDASH workshop several years ago, this issue of the privacy threshold is really critical. How much, what is the quality of the answers that you get, and how useful is it to policymakers and researchers if you still want to have these very strong privacy guarantees? So there's that trade-off there, and that privacy threshold is really critical. And the second thing, and that's across all different types of tasks, right? Could be very satisfactory for one type of task, and very unsatisfactory for another. By task, I mean like a particular algorithm, for example, like a machine learning algorithm or something. So another thing is that there is a concern about a record being in kind of multiple data sets and what happens to the privacy over time when the record has been part of many different sets of queries. So that's another thing to kind of consider for differential privacy. So for homomorphic encryption, it's very clear that there are still some major challenges that we work hard on. And this may be kind of counterintuitive for people that don't work on it, but really the storage costs, the actual size of the ciphertext is a real issue. So when you take genomic data that's already extremely large, and then you tell somebody that you're going to encrypt it, and you're going to blow up the size of the data by, if you don't use any optimizations, you'll end up blowing it up by a factor of, 700,000 or something like that. I mean, it's just completely ridiculous. And so then, we work really hard and we use, all of these kind of packing techniques, and we do our best, and we get it back to, oh, isn't this great? We only blew up the size of the data by a factor of 10. At 10, we're so happy about it. At 10, they're still, So the storage cost is really an issue, and that has to do with bandwidth as well, of course, for uploading. Another thing is, as I mentioned when I talked about the history, these are new, hard problems. We work on kind of attacking them and trying to understand them, but typically in cryptography, there's a lag of adoption of new cryptographic systems of something like 10 years, which makes sense because we want to kind of give the community time to work on these hard problems. So it's good to recognize that we're still talking about very, very new cryptographic systems here. Another thing is just the overall efficiency at scale. These large amounts of data on these deep circuits are the real challenge for homomorphic encryption. So for things like garbled circuits, we do have typically a very, very high interaction cost, so a lot of communication overhead, and as bandwidth becomes a limiting resource, that is a real concern. Another thing, actually this is a direction which we started to make a little progress on, that is multi-party computation is really good for kind of one-time interactions. So how does that fit well with storing data long-term and touching it many different times for different uses? So these are the kind of challenges the way I see them. So I want to have time to show the demo. So how much time do I have left? Like 4 minutes or 9? I can't tell. Okay, good. Good. So so one of the things when I started working, I really started working, concentrating on homomorphic encryption about 5 years ago. And that was because I had a person on my team, Vinod Vaikuchanathan, who was really the inventor of the solution that we all use right now for homomorphic encryption, which is the ring learning with errors-based solution. And so we saw an opportunity to combine he was more on the protocol side, and me and people in my team were more on the math side, to really start kind of building an efficient system and trying it out on lots of different concrete tasks. So that was about the same time that I started going to privacy conferences. And Microsoft hosts conferences for customers, innovation outreach program. And so I was actually talking to real customers about what type of computation they like to do on sensitive data. So I got all of these ideas, and these are from advertising companies, car companies, makeup companies, pharmaceuticals, all different types of companies in the industry. And the one thing that I was really surprised about is how consistently people talked about wanting to do basically statistical queries, which are from a mathematical point of view really like the easiest thing you can do. The circuits are very, very shallow. And so what I was just so surprised about is everybody at that time thought homomorphic encryption was insanely impractical, because IBM had come out with this really nice library, HElib, but they were showing a single AES encryption at that time, the 128-bit encryption in about a week. And so it could be amortized for multiple encryptions, but I mean, the first published benchmark was to take a week to do a single encryption, 128-bit encryption. So it just looked like the technology was completely preposterous. And yet, an AES encryption is a pretty deep circuit. I think the depth is like at least 30. Whereas these statistical computations, the depth is essentially 1. I mean, these are very, very simple computations from that perspective. And so things like data quality testing, statistical functions, even statistical computation on genomic data, and then more complicated, so we started to look at more complicated tasks such as machine learning predictions and things like that. And we found that there's an amazing amount of computation that you can do extremely practically with homomorphic encryption if you concentrate on those tasks which have this, you can essentially represent with a low depth circuit. So what I'm going to show you is 3 demos now, which are kind of fun. These are based on the SEAL library. So SEAL was released publicly about a year ago, and it was used as the basis for our solution to this contest. And actually, as a result of this contest, on all the work that my team has done, a lot of fabulous work on this, they have improved here's the SEAL team from this year. So Kim Lane, Hao Chen, Gazem Chetin, Susan Zhao, and Peter Rindel. Done so much work that now if I showed you the new demos based on the new library that was released last month, these same demos that I'm about to show you would be somewhere between 10 and 100 times faster than they already are. And that was partly due to the work that was done on this for this contest solution. So I think that's a very concrete example of how it has a really important effect. Okay, so let's see. Can you see the demo here? Great. So let's hope it's working. Yeah, it's working. Okay, so that was just a test. So now I'm gonna do it over again. Okay, so I'm gonna show you 3 demos in increasing order of difficulty. So meaning in increasing depth. So this is actually a linear predictive model. So this is, we have a genomics team at Microsoft Research that works on genomics, and they developed these things called fast LMM. I don't know if any of you have heard of it. It's fast linear mixed models, and they're very efficient for doing machine learning predictions. Let's see. So in this case, they developed a model for predicting the flowering time of a flower. So we're using flowers, plant genomic data here instead of human data. It's just easier for us to get access to plant data than human data. And the plant data, although you might think it's smaller, this algorithm is actually operating on 200,000 SNPs versus, for human data, you might want to be operating on something like 1 million SNPs or something like that. But still, already 200,000 is pretty good. And these times scale linearly. So whatever you see here, if you just multiply it by 5, you'd be able to handle a million SNPs at a time. So what it's doing is it's taking 200,000 SNPs from a plant, and it's using this model and predicting the flowering time. So the average is something like 37 days. So when I hit next here, what it does is it sends the encrypted genomic data up to the cloud, computes the prediction, and sends it back. So you can see it took 1.2 seconds and a little bit of time locally to decrypt the results, and it's predicting the flowering time of 29 days. So this is fairly efficient. As you can see, it's barely had to even wait for the answer. As I said, if we had the new version of the library, you wouldn't even have noticed the amount of time that it took to send the data to the cloud, operate on it, and send it back. So it's really kind of showing things that are extremely practical and yet also very useful. But as I said, that was a linear model, so that makes it particularly suitable for homomorphic encryption. So now let's move up to something a little bit more challenging. So, and this represents, question?
Yeah, so what's the setting of your server? So what are you measuring? What's your machine that you're using on the server side?
Oh, to be honest, we actually have different servers that this runs on. So I could make it run faster or slower based on using of it. So I'm sorry, I mean, the actual precise data is in the paper, but I don't remember which one this is running. I can talk to you about it afterwards. Yeah, so, but it's not like a supercomputer.
Okay.
It's just like a regular server. Yeah, that would be kind of cheating. Okay, so here's another thing, so sorry, I need to speed up here so I can get done in the right amount of time. So this is another task. It's an interesting kind of health related task, not so much genomics. And this is predicting risk for pneumonia. So a patient shows up at the hospital and they have pneumonia. This could be very serious. Should they be sent home and have chicken soup at home, or should they be admitted to the hospital? So kind of, in other words, what is their mortality risk? And this was a project by several machine learning researchers at Microsoft Research. And if you see down in this lower left-hand corner here, there are a lot of different attributes that go into making those kinds of decisions, and models that have been considered for a long time based on things like, can you see this, age, gender, chronic lung disease, asthma. Oh, there's actually 46 different attributes that go into their models of predicting how great a risk they are of dying of pneumonia. And so I'm going to start the demo going here. What they did was to build models. These are degree 4 models that are running on these 46 attributes. You can see that it took only 8 seconds to process. And another good thing about this is with these batching techniques that we use for homomorphic encryption, in that 8 seconds, it not only did one prediction of mortality risk for one patient, it actually at the same time did 4,000 predictions for 4,000 patients. So if I click next and go through this, you'll see lots of other predictions for different patients. And this is one reason I like to highlight this demo is that this is an example of combining machine learning researchers with cryptography researchers. There's no way we would have been able to do this demo otherwise, because they actually trained new models for this task to specifically have low degree polynomials. So they have 46 degree 4 polynomials that they trained, and they considered all different possible degrees, but the point is that because they were working with us, they were trying to replace the usual models that they use with low degree polynomial models and still get like 99.6% accuracy in the predictions, but to get models that could be used a lot better with homomorphic encryption. So very quickly, let me start the last demo running because it's the most complicated and it takes about a minute to run. So this last demo I'd like to show you because this is really showing the ability to do deep learning algorithms on encrypted data, which is something that people certainly did not think that we could do. And to be honest, it was very challenging. So the task we're doing here is kind of a neural net prediction. It's kind of an image processing task. It's handwriting recognition. So this is a well-known data set, public data set of handwritten numbers, and the task is to take an image, and so there's a lot of pixels in this image. Each image is something like, I don't know, 256 pixels, and to take this image and to recognize what digit is this. So that's the task. The algorithm is this kind of neural net predictive algorithm. But again, working in combination with machine learning researchers, we were able to tailor the internals of the machine learning neural net predictions so that they work better with the mathematics of homomorphic encryption. And so what we're able to do is do predictions for each one of these digits. So we actually, again, batched something like 4,000 images all in one. So you can see it took 80 seconds. Like I said, with the new version of CL, this would run at least 10 times faster. Maybe, I mean, this we'll see, but it might be something that would even run in a matter of seconds. And that's even without a supercomputer or fast special purpose hardware. But you can see what this is. This is my last point right here. These are the predictions. So the size of the yellow digit shows the confidence. So here you can see it's very confident that it was a 7, but like I said, it did 4,000 of these predictions. So some of them are slightly more confident than others, that kind of thing. So there's a lot of big digits like this, it shows it's slightly less confident. But these models have very, very good accuracy when you run them on even on plain text data compared to other known machine learning models. So anyway, this is the end of my demo and the end of my presentation. I think my overall point is that I really want to thank the organizers for organizing these competitions. I think they're a really great contribution to our community. And I showed you these demos basically because they're fun, and to be able to see homomorphic encryption actually in action in the clouds, in a cloud service is kind of fun to see it on concrete tasks. We're not trying to say these tasks are the most important ones. We're just trying to say these are things that kind of show how far we've come in the technology. And like I said already, the fact that we worked on this task for the competition greatly improved the performance of the whole library and all of these tasks as well. So thank you very much.
Thank you, Christine. But it's very tough, and it's really great to see those demos. I remember when I was a graduate student, I was working on this missed data. It took like more than a dozen seconds to compute, even without encryption. Thanks a lot. Okay.
Super server.
Yeah, thank you, Christine. I think it's excellent work, and excellent introduction for our challenge, and actually much better than what I was going to say. But I have a question about the crypto math.
Yes.
So is this the prediction? Or actually it's a learning, the time?
Well, unfortunately, this is just the prediction.
So do you think it's possible to do the learning on the encrypted data?
So learning is a big challenge, and we do think about it, and it is, I think it's definitely possible to do something. Right now, it hasn't been the lowest hanging fruit, so we haven't been picking it, but it is definitely, we can go there. The fact is like, say if we did something today, and let's just say that a circuit depth of something like 20 to 30 is doable, but kind of horribly slow, like no commercial entity is going to be interested in it now. So I think if you get tasks down into that range, like if your depth is 100, don't even think about it. But if you get down into that range, then I think you start to hit with all the different hammers that you have, and you can probably, make it look a lot more viable. So what we find ourselves doing is trying to do kind of innovative combinations of things, either doing hybrid solutions where you combine with more communication, or things like, comparison-like tasks. An easy example is, bucketing things so that you don't have to compare as many digits, that kind of thing. So we would, do the same kinds of things in the internals of the learning as well. And that's why it's important to work with machine learning researchers, because then they can validate whether we're still building good models. And we see a lot of fun examples of that kind of thing. So I think it's there, it has a big red target mark on it that we need to shoot at.
So fascinating work, that's great. My question is a follow-up to this one. As you pointed out, making progress in this field requires, not only with the ML connection, a lot of making use of various hammers and tricks, etc. And you aim at more performance, more accuracy, and so on. How do you make sure that you still retain the robustness of the crypto solution that you are proposing? So how do you make sure that at some point there's not a kind of a breach that surreptitiously enters the design just because of the tweakings that you have to make?
That's a very good question. I think it's the kind of thing we should always keep in mind. So one kind of advantage of working on homomorphic encryption is that the model is extremely simple. This model of outsourcing, it really is, it's actually even, we have public key solutions, but we can even just use a private key solution. And so what you're doing is you're encrypting things locally, and the only thing the cloud is doing is operating on that encrypted data. But with if you don't use a public solution, they don't have any opportunity to even inject anything of their own. They can't like take some other data and encrypt it with your key and compare it, or and it's randomized, all this. So the nice thing about these models is they're very, very simple. On the other hand, what it does not tolerate very well is if you put it in a homomorphic encryption into a scenario where you allow decryptions selectively of things. That will end up completely breaking these public key primitives underneath. So I think it's a big warning sign that, so if you use like a public key system and you put it in place, and like we had some scenarios for advertising, for example, where the cloud could potentially collude with an advertiser, and the result would be that they would end up kind of getting decryptions of things. They would end up being able to break the underlying public key. So it's very important to make sure, like I said, these things that I showed you here are such a simple model that we're very confident we're not introducing backdoors into the crypto. But when you want to use it in a lot of different scenarios, I think we absolutely should be modeling these things from kind of a crypto protocol, or even a kind of a formal languages, formal proofs type of approach.
Yes, thank you for your very interesting presentation. Concerning the last question that has been answered, even if you are not sending a public key, there is the problem of the fact that the cloud may learn something about the result, maybe because it published the results, or maybe because you only want to have some error handling to say, hey, you didn't compute the right thing, or something like that. So he can get a bit of information. Also, we're in a CCA model where he can not do the right computation and see if you react or not. And that's for realistic environments. Very scary, no?
So no, you're absolutely right. There can be a feedback loop depending on the commercial setting and how you use the data. There can be malicious intent on the part of a server if they like interactively give you wrong result and see the result. Again, because we're kind of commercially motivated, I'm always assuming a semi-honest cloud. That's because from a business point of view, we're thinking of the Microsoft Cloud services. We're incented to honestly provide these services to our customers. If we don't, nobody's going to want to use our services. So I admit it's a completely simple model that we're semi-honest model that we're using, and it does not take into account these kind of surreptitious feedback loop that could happen based on what the outcomes are. So very good point. I'm sorry, I hope it seems I might be taking up too much time. Okay, thank you.
Laying the ground. Yeah.
Thank you.
So let's welcome Xiaofen, Haixu, and Shuang for the set stage.
Are we supposed to be standing there?
All right, thank you everyone. So I'm Haixu from Indiana University. I'm one of the organizers of the workshop and the competition. So this is exciting time. We will soon announce the winners. And it's a great honor and
Haixu, can you talk louder?
Oh, okay. I think it's not working. Anyway, I can speak.
Yeah. Okay.
Is it better? Okay, all right. So it's great honor actually, and very nice to following what Christine has said, because it saved my time, and I don't have to talk about the big picture, why we are organizing this competition. So I will go to very details how we actually come up with these challenge problems and how we actually evaluate the results. So and then I hand up to Xiaofeng and Sean to announce the results. Okay, so as Christine already described, we have 3 tracks. So the first is to challenge the approach for privacy preserving data dissemination. The second is about secure collaboration, and the third is about secure outsourcing. So again, I don't have to go through why we are coming up with these scenarios. So a little bit background of the first track. The first track. So the background is like there's a beacon project. Actually, we have Knox and Stefani here from the GA4GH. And they basically proposed, they initiated this beacon project to testing the willingness of data holders to share genetic data in the simplest technique context. So the query is as simple as just to ask if there is any patient in a database, in the genome database, have a particular allele, or say have a particular nucleotide at a specific position in the genome, in the chromosome. So this as a simple query. So in the beginning, people think maybe there's little information released. From this kind of a query, and we see now there's many actually participants who use Beacon as as a platform to share their human genomic data. But surprisingly, like early this year, there's actually a tag proposed by Stament and colleagues. It basically shows that based on it's an inference attack, like similar as the previous inference attack shown on the aggregate genomic data. But this basically showing based on the answers from those beacon queries, one can infer the probability of individual to be present in a database. Okay, based simply on the accumulated information leaked from the query of the Stament attack. So we come up basically the challenge is as also a very simple design. We basically ask the team to come up with a solution to mitigate this attack, but still try to responding as a maximum number of queries correctly. I mean, if this present, it's a yes, then if not present, it's a no. So we want to maximize the number of correct answers, still try to mitigate this Stament attack. Okay, so we ask each team to prepare programs that will answer the variation to the beacon. So when we evaluate, we basically query the database, okay, through this particular submitted program. And then we evaluate the program, each program, based on the number of correct answered queries. Okay, so and simultaneously we will run a modified, as I will describe a little bit later, hopefully stronger Stament attack on those answers to see if any information has been leaked. So before the attack, before the information, we will stop when actually there's sufficient information leaked. Then I will count the number of correct answers before that break. And the team with the maximum number of correct answers, or the smallest rate of errors among these answers will be the winner. That's our criteria. So I think I don't want to go detail about how we calculate it, but briefly, so I should mention that we have developed this modified Stament attack in collaboration with the JP's group at EPFL, and we have, I think, a manuscript under review right now describing this attack, describing this kind of modification. So I won't go detail about this. So just to develop a baseline, we develop a very simple approach. We just say, okay, we will hide a k% most real slip in the database. So if the query is about one of the k% of the slip in the database, we just say no, even it's present in the genome. So we found this actually can mitigate the attack at some level. This is a very simple approach, but as I see, we can in this approach, if we just apply this simple approach as a baseline, we can crack answer like from 8,000 to 32,000 query correctly. Of course, it's better than applying nothing like that. You can only means you will get sufficient attack power even after just 2,000 queries. So we can increase that by this simple approach to answer more queries. But we can see that later on when we show the result from the participant team, that actually both of teams who submit their solution do much better than our baseline solution, which is good. Yeah.
Are you going to show our solutions before we present them?
I'm going to show the evaluation result, but you can present your method. I mean,
Yeah, you
I
guys
don't know
supposed
your
to
method.
present your
Of course. This is our evaluation result, not your result, right? Okay, the track 2 is again it's a scenario of secure collaboration. So assuming basically there are 2 hospitals or 2 medical institutions, in this case, one hosts a database or sequence for a gene, let's say important for a particular disease like cancer. And the other institution has a sequence of the same gene from a single patient. You try to see if there's a similar patient in the database with a similar gene sequence with a query. Again, in the scenario, we assume that the hospital the institution who hosts this database cannot release the whole database to the other party. And similarly, the query, the institution who hosts this query don't want to share the sequence to the other institution too. So we want to do a secure multi-computation on this one to allow the search to get the top K similar patients in the database. Okay, again, I want to emphasize just because we organize a challenge, we want pretty specific tasks. So this specific task, as you say, to retrieve the top K most similar patient may not be ultimately the result this query want to get, but we we want to just get some standards so we can actually run a computation to evaluate the submitted results. So in this case, we test actually K equal to 1, 3, and 5 respectively. So there's some details like we asked each team to submit 2 programs, each run on one of the 2 institutions. When we do the evaluation, we run them both on the same setting, the virtual machine with the same setting, one running on a computer at UCSD, the other running on a computer at Indiana University. So we'll measure this running time of both computers on each side. And then we will evaluate the accuracy because we allow, in this case, the challenge team to develop, we actually encourage them to develop approximation algorithm, but we also will evaluate the accuracy of the approximation algorithm too, as a part of the evaluation process. So again, I don't want to go to details about the evaluation, but I want to mention the example we showed is example we use in the testing is a gene we take we basically use this particular gene. We use it because we found there's a high diversity, high divergence of this gene sequence among human populations. So we track the sequence from 5 individuals. So the database contains basically 500 gene sequences, and the sequence divergence among them is between 5% to 15%. So they are quite divergent. So we want to we challenge the teams to develop quite good approximation algorithm in this relatively difficult case. Okay, the third track is a scenario of the secure outsourcing. So we assume that there's a medical institution has a particular, or actually one or many even human genome sequence, and they want to store the encrypted genome sequence on the public cloud. And at some point, they want to search if any of this patient or any individual whose genome are stored in the public cloud to contain a particular or one or multiple genetic markers that relate to, for example, genetic disease. And in this case, we specify homomorphic encryption must be developed in order to allow this search in a secure manner. Okay, I forgot to mention for the track 1, I'll go back. I mean, even though Christine mentioned that it's related to a differential privacy scenario, but actually we did not ask the partition team to must fulfill a differential private solution. We just say you have a solution and we test it can defeat or mitigate the Basman attack. That's already sufficient. It's not necessarily differential private. We will hear if actually any of the solution actually is private, differentially private solution or not. But anyway, that's not actually a standard or criteria we require the team to follow. Okay, the third one, however, we specify it must be a homomorphic encryption solution. So what we are trying to compare here is mainly the speed, so the running time of the solution. Okay, of course we will also ask each team to submit a brief description of their solutions to make sure their solution actually abide basic the security guarantee that we ask them to follow, such as the homomorphic encryption criteria. Okay, so in this again the detail how we evaluate the third track solutions. So I won't go detail about this, but I will now hand to Xiaofeng for results.
Okay, I'm happy to be the first person to somehow, I would rather to say, expose the winner. And it's hard to say whether the first one is the winner or the second one is the winner, right? Just the order doesn't matter. And just look at it. Maybe there's some surprise. Okay, so for the first task we have two participants. The first is Vanderbilt, the second is Manitoba and Iran University of Science and Technology, right? And we have two teams. And because the first time we have this very realistic, vegan, I'm sorry. This, and a competition, and we only have two teams, but we are very happy to see both teams are doing much, much better than what we've done. We've been trying very, very hard and to solve the problem, but it ends up they're doing much better than we do. And so, and for the track 2, we have, just 8 teams to participate. IBM Research and University of Manitoba and Maryland and Indiana University. It has nothing to do with my group, our group. Otherwise, we have conflict of interest, and I promise we haven't detailed any information. And the track 3, we have just and Microsoft Research and just a bunch of other group. And we have a participant this year is really amazing. We have a participant from 13 countries and more than 50 teams in registration. And of course, just multiple teams, they can work together to, to participate in a single competition. Okay, I'm gonna somehow expose the result. And just again, all that doesn't matter, right? But you can find out once I finish presenting of the whole session. You can see who the winner. And for the first task, and we have Vanderbilt. Actually, they did an amazing job, and we don't know how they did that, right? I will leave it to you guys to explain. But the whole thing, so what we found, we just do evaluation. We found, and their approach, their solution for this and the big inquiry, they can successfully answer, 141 and 1,000 queries out of 160,000 queries, and the error rate is is only a point, just 11.5, and it's very low, and until they answered up to 160,000 queries, and using the most state-of-art inference attack, we cannot get any inference power. Right? So this result is very impressive, and they can answer almost 4 times the queries we can answer. Around the similar, just error rate. And the second group is, the University of Manitoba and, Iran University of Science and Technology. And in that case, they can answer, just 110,000 queries, and until they hit the, the power limit, and we set there. And the error rate is 0.509, and they correctly answer, 54,010 queries. So, I think I didn't formally announce the result, but and somehow expose it. Go ahead.
I have a question. Are the queries asked randomly or?
Randomly, yes.
Randomly, yeah. Okay, so just Vanderbilt, Vanderbilt is the winner for the first competition. Of course, you have two teams. You have just winning, but and although it's one out of two, right? But I'm gonna say the result is state of art, because before that, just we tried very hard, and together with JP, we come up with multiple answers, and they did much better than we do. So these are great results. And for the second task, we also have very, very exciting result. And so this I should already present. I'm going to skip this. And for the second one, yeah, unfortunately, I'm somehow exposed the result. And we have IBM Research. IBM Research, they have this secure, tripartite computing. And what they did is within, just around 11 seconds, a little more than 11 seconds, they did amazing things. And they go through these 500 patients, just I mentioned. Each patient have around, just 3,500 SNPs, right? And altogether, there are 500, sequence altogether using added distance. In the end, and they find out, the best match, right? If we're looking at the top one match, they're always accurate. If we're looking at top three, sometimes two, sometimes three, but most of the time they get it right. And we look at top five, amazing, sometimes they get 4, sometimes they get 5, but most times they are right. So this result is very, very surprising. I can tell you what we got in the last competition. Last competition, we also have this, an added distance based, secure two-party computing, right? The result is over 100K, variation sequence, right? And the best team took, guess how much time? Only one sequence. They took 998 seconds. But this time, only take 11 seconds. And the result is the data set is 1 order of magnitude larger than what we had last time. And of course, one thing we learned from last time is you just cannot do these precise added distances too much. And so we published a paper on ACM CCS. We are talking about how to using in added distance approximation, because it's enough for a lot of biometric data analysis. And so this time we have this computing task. We encourage people to do approximation. They did a wonderful job. It's very surprising result. Within a little more than 11 seconds, they can go through 500 patients sequence, each with 3,500 variations, and get mostly accurate result. I think indeed we are making progress in this area. And we will also see other group also making progress. And University of Manitoba, they have 22 seconds. But in the first top one is not cracked, but for the top 3, 2 cracked, and top 5, 3 cracked, right? And Maryland, they always cracked, for the first one, and the top 3, 1 or 2, and the 5, 2 or 3. And the result, I think, is they can do it around 13 seconds. So, I think indeed we are making a huge progress in this area. And there are only a few groups, just only one group, I think, they are disqualified because they decode more information than the result. But in general, I think most of the team, they follow the guideline, they don't decode any extra information, and get a very, very impressive result. I'm really excited. So on the other hand, I show, it's kind of demonstrate, and with this kind of synergistic activity with the biometric community and together with the crypto community, indeed we can move the science forward. Right? So that's just the winner is IBM Research. So I will next one to talk about this.
So I will discuss the result about the third track. So to evaluate the third track, we have designed the following 3 tests. For the first test, we designed one query with 4 variants versus one VCF file with 10K record. then we extend the number of records within the VCF file to see how well each solution can handle the large-scale VCF file. So in the third test, we extended the test to multiple VCF files to see how well each solution can handle the genetic test for multiple VCF files from different patients. And here is our result for the first test, one query with 4 variants versus one VCF file with 10K record. So we test several different attributes. So for the first attribute, we test the setup time, included the key generation, and the database encryption and the database upload. So this is a one-time job. And for the second attribute, we test the size of the encrypted database. The third one is for the time to compare the query against the encrypted database. And also we test the memory usage on the server. So we can see for the first 4 items, the Microsoft team is meeting the performance in the first test. And then we tested the time to decrypt the result. And in this attribute, the National University team made the performance here, and we test the size of the encrypted result. In this case, the ComSys team made the performance, and also we measured the total turnaround time in terms of the comparison over the encrypted data and the transfer time to get the encrypted result and the time for decryption. And we can see the overall performance, for the overall performance, the Microsoft team got the best result for the first test. We can see this is a very amazing result. We can roughly within around 1 second to perform the genetic test with the 4 variants against VCF file with a 10K record. And we can see the other 4 teams are very tight and has a similar performance, but the Microsoft team did a great job. It's the order of magnitude better than the second solution. For the second test, we extended the size of the VCF file to 100K. We try to push the boundary to see how well each solution can handle those large-scale data sets. And we can see in this case, Microsoft team still made the overall turnaround time. But in the second test, so National University team get a smaller encrypted data size, and the ComSys team has a lower memory usage on the server. Still, the National University team had the fastest decryption time, and the ComSys team has a smallest size of encrypted result. And the EPFL team did also a very good job. In this case, is in the 3rd place. And for the master test, we include the 50 VCF file to see how those solutions can handle the genetic test over multiple files from different patients. And we can see the overall performance. Here, the Microsoft team is still leading the performance, and within like 1 minute, we can finish the genetic test over 50 patients with this table is 100 genomic record. And here is the overall performance comparison for all those 3 tests. And we gave an overall score based on the average of each rank. We can see the Microsoft team is leading the performance. And this is a very amazing performance. We can within 1 minute to finish all those tests, which is significantly improve the performance compared to the master years. We need several hundred seconds to perform homomorphic encryption master year. And for all those 3 teams, the National University team, the ComSys team, and EPF team is very tight, so they win the run-up. Finally, we have a call for full paper submission. In this year, we have a special issue in the BMC medical genomics, and all the submission and the peer review, and the submission deadline is December 31st, and within a month, we will give the first decision, and you can submit your paper through this link. Okay, thank you. So we have a break, right? About maybe 5 minutes.
Yeah, I think we have a short break. Thanks all.
So actually, we came across like one of Mark's paper almost every month in our journal club in my group. So, but for this community, let me make a very brief introduction, and Mark is very kind to provide those short introduction from his webpage. So I just read briefly from what he provides. So, Dr. Mark Gerstein is Albert Williams Professor of Biomedical Informatics at Yale University. He's also the co-director of the Yale Computational Biology and Bioinformatics program, and has appointments in Department of Molecular Biophysics and Biochemistry and Department of Computer Science at Yale. He received his AB in physics from Harvard and his PhD in chemistry from Cambridge. He did postdoc work at Stanford and joined Yale in early 1997. His research focused on bioinformatics, particularly in data science, data mining, macromolecular geometry and simulation, human genome annotation, and cancer genomics, and most relevant, genome privacy. He is an elected fellow of the AAAS and also the International Society for Computational Biology. Okay, without further delay, let's welcome Dr. Gerstein. Thank you.
Okay. So you can hear me? Okay, I really appreciate being invited here. I'm very interested in privacy, and this is kind of a new interest for me, so I like learning about this. Now, what I'm going to do here is introduce kind of a bit of motivation on genomic privacy, and then I'm going to go into a particular type of work we've done on it. So we're going to start very broad. I just want to talk about genomics in general, and there's sort of this idea that in the past, people came to bioinformatics and genomics kind of as a subtopic of a subtopic of a subtopic. First they learned maybe biology, and then they learned genomics, and maybe for 5 minutes in the class they learned a little about bioinformatics as a subtopic of a subtopic. And I do think in the future, a lot of that's going to get turned around, and people are really going to confront biology and genomics initially through bioinformatics. And what I mean specifically there is I think what we're going to see more and more is people, for instance, who are sick or have, say, cancer in the extreme, getting their genome sequenced and finding all the variants that are associated with their disease, and using those variants as a gateway to understand biology and so forth. And so I think this is why the presentation analysis of this information is very important. And how are people going to understand what their variants mean? Well, one of the most important ways, as everyone in this room knows, is really through comparing themselves to a larger database. And so one of the most important and powerful things, of course, we have for interpreting the genome is the big database of all the people's sequence. And so it's imperative, as we all know here, to somehow enable those type of comparisons. And now, of course, those comparisons, connect us right up to this issue of genomic privacy. And I'm going to talk, at the beginning, kind of broadly about just some aspects of this, very broadly here. And I'm going to talk about, the problem and also maybe some ideas for a solution. And then I'm going to talk in much more detail about a particular type of work that we've done with making what's called RNA-seq data, making it private and thinking about various specific type of attack on it. And then at the end, I'm going to talk about types of analyses that maybe people do on RNA-seq data that, more as a challenge to people. How would you deal with these in a private context? And the many calculations people want to do that just fundamentally are very difficult to do. And this is, or difficult to do in a privacy context. And I'm just going to say a little bit about this at the end. Okay, so let's just start from this very general description. So, obviously everyone here is very interested in genomic privacy, and one question people might think about a bit, is, well, first of all, is it really a problem? There's definitely some people who would say, well, we don't really care if lots of genomes are on the web, or if they don't care if their particular genome is on the web. And, people are making a big deal about this and so forth. There's other people who feel that genomic privacy is a very important thing and we really have to take it seriously. And I think one of the ideas here is that the genome is about the most fundamental data you have about a person, and so it's something we really want to take very seriously. We often hear about genomic privacy in the context of identifying. We'll identify someone in this study based on their genome and so forth. And that I just like to I like to use the distinction between an identification risk. There's another type of risk that we're going to talk about here, which is a little different. It's what's called characterization risk. And so there's a lot of people, for instance, who are happy to have their identity in a study or their genome be publicly identified, but they don't particularly want to have certain characteristics of themselves available. So I think the most famous example of this is Jim Watson. So when he had his genome sequenced, which was one of the first genome done by next-gen sequencing in 454, he was fine that entire sequence to be put up on the web, but he didn't want his status for a particular gene, ApoE, to be made available, and that's because this gene is very associated with your Alzheimer's disease risk. And so he actually had it cut out of the genome, and it turns out, that sounds like a reasonable thing to do. It turns out it's actually very easy to crack through that, and so people published a paper and they figured out, oh no, you can easily find that out. And now, of course, we've heard and we all know that the issues of genomic privacy are very similar to what happens in many other contexts in society. There's many places that people are dealing with large data sets, and mining is very, very important. And one question we have to ask is the situation we have in genomics, is it really the same as in many of these other contexts, or is it different? And I just like to point out there's some things that I think make it a little different and make it a little interesting what's going on. So one is that, you can get a new credit card, you can get a new bank account number, and that's sort of, you can't get a new genome. And it's even more than that, you give your genome to your kids, right? And they're your grandchildren, and you can't change that. And so if someone finds out something about your genome now, that's a risk that's actually present far into the future, for your children, just even grandchildren in some statistical way. So that's a little different than what happens. And also there's this idea that right now, your genome isn't really that revealing about you, but what's the world going to be like in 50 years? What would we be able to mine out of someone's genome? Maybe different. So something we want to think about. Also, I think there's a big issue in genomic privacy is really a kind of culture clash, frankly. So there's the world of clinical medicine you're probably aware of. It's a fairly privacy-oriented type of discipline where people tend to keep health information fairly private. You probably also know that genomics as a field tends to have the opposite viewpoint. I mean, genomics is very famous for open data and putting stuff out, and maybe you remember 15 years ago to the initial sequencing of the human genome, there was this massive clash essentially between a private company and this public consortium about the data being freely available. And so that's very much baked into the DNA of genomics. And then, of course, the other issue is that genetics as a whole has been a discipline that's been very ethically challenged. I mean, from its very beginnings, in 1850 to very recently, you probably all heard about the controversy associated with the HeLa genome and things like that. And there's all sorts of tricky issues and so forth. And so I think, particularly in this discipline, it's important to be very careful. So that of course means, well, we should be careful. But there's another side of the coin, and that's of course that we want to do large-scale mining of this data, and this is just essential to speed research. And we all know that while we believe in privacy, it's often very cumbersome, and it's just very difficult to implement private solutions for data of this scale. Also, there's this idea that data sharing is important for another virtue, and that's this idea of reproducible research. We want our research to be reproducible, and to do that, we have to share data. And then a final thing that's not as appreciated as much is that having public genomes and public information is really useful for education. So people, if you teach a class about genomics, people are much more interested to learn about Carl Zimmer's genome, which, for instance, he talked about in this recent piece, The Game of Genomes, than they are about NA12878, an anonymous person. So it's just interesting for people to learn about individual people's genomes. And so we want to sort of grapple with these issues. So, and so succinctly, a lot of times you can see the dilemma that happens is you have this kind of collective benefit from sharing all the information, but of course there's this idea that the individual sometimes is harmed by this sharing. And you know, one way I think of thinking about this trade-off is really to think about sort of balancing risks and rewards, and that really calls to the point that this, in genomic privacy, it's not really a black and white thing. We really have to think in terms of quantifying information leakage, and we have to think about what's acceptable risk and what's an acceptable amount of information. Ideally, we'd like to do this almost in monetary terms or some quantitative terms. And it's also important to realize that we're never going to get perfect privacy. I mean, just if you look around the room and you look at people's eye color and their skin color, you get alleles, okay? I mean, it's, you have to share some genomic information. So we're never going to have perfect privacy. We're going to have to figure out some way of setting a meaningful threshold. So what do we do now? Well, there's sort of two approaches now in the genomics community. One, of course, you're probably aware, is this sort of closed data idea, and there's this idea that there's this data set, it's private, okay, and so this idea that there's a consent, it's stored in some private repository, it's encrypted, you're supposed to download it, keep it safe, and it sounds all good, but the problem with this is that the consents are very non-uniform, and they are different in different countries. When you try to aggregate data with very different consents, it's very, very complex. What you can do with this data, what does the aggregation mean, and then dealing with encryption and all the computer security issues for many terabytes or petabytes of information is often a massive challenge for people. And many of these schemes, as I'll describe to you, just get hacked, and of course the harder people try to lock these things down, the more they make themselves a target for this type of thing. And then, of course, the opposite is these idea of, well, maybe we should just let all the information be out there, freely available. And there's definitely this notion of kind of genomic test pilots. People who, often celebrities, who've just put their genome up there. The Personal Genome Project is a good example of this. And I think this is a good thing. But we have to really ask, is this kind of test pilot mindset the thing that's going to scale? If we want an unbiased view of the American population or the world population, is this approach going to work? And I think not. I mean, I think that first of all, I think it's going to be kind of biased in terms of the people who are willing to do this, and second of all, it's just not clear if this type of thing would meaningfully scale to millions of people. So how should we think about going forward? So this is just a straw man idea, just to get people thinking. So my personal belief, which you may or may not agree with, is I don't believe there's any technical solution that will solve this problem, nor do I think that we should be oblivious to technical ideas. And I think there's some sort of hybrid of having a new legal framework for thinking about these things with technological things that make it easier to work in this legal framework. So people talk a lot about maybe licensing genetic researchers, sort of similar to maybe a driver's license or medical license. So you shouldn't give out information. This is a little more complicated. You think this has to be fundamentally international, okay? And people have very, very different ideas of privacy throughout the world. So how are we going to do that? I'm not so sure. And then we really want technology to make things easier. I mean, of course, there's this idea of doing computing in the cloud and enclaves and things like that. Genomics England, I think, is a good example of maybe where the future is going. And then I think I'll talk today about various technological ideas about how we might quantify things, how we might also think about building data sets kind of to separate the more kind of radioactive private part of the data from a more publicly accessible, less radioactive part that we can do computing on, maybe also developing kind of stub or test pilot data sets that are representative of a bigger set, again, to ease the software development. I think there are a lot of simple-minded, practical things we can do to make it easier for people to deal with large amounts of private information. Okay, so that's the general dilemma. Let me tell you just a little bit about some just practical kind of hacking that is just useful to think about. So first of all, a while ago, this is now a while ago, I got very interested in this. I just wanted to know practically, was kind of maintaining secure computers a big impediment to sort of doing genomic research? And I just, I put computers there and I looked at how often it got attacked and so forth, and graphed it and so forth. And, I didn't do this. This is a while ago, and I continued to do this years after. And the bottom line is it's a lot of work. Maintaining, at least for people in the genomics community, maintaining kind of their own servers and doing this, it costs money, it takes a lot of work, and it's something we should think about. Another type of act that sort of sets the background for this is there's been a lot of initial studies that have mostly focused on identification risk as opposed to characterization risk. But the most famous one is this study from David Craig, where he basically showed that you could identify a participant in a kind of a mixture of genomes from one of these GWAS studies. And this was kind of an eye-opener to people and really led to a lot of changes in the way people thought about these studies. And then subsequently, there's been a lot of these kind of stunt-like studies. Maybe you've all seen the Gimrick et al. Study where they found that some of the people in the 1,000 genomes where their data was available freely, but their identities were hidden, could actually be found out. And these are fairly well-known things, and they sort of set a background to what I'm talking about here. And now another important background, which I think we should talk about, is a non-genomic attack, which is very interesting, which you probably all heard of, called the Netflix challenge attack. And actually, this is the specific type of attack that I'm going to talk about with genomic data. So let me give you some background on this. So Netflix, a number of years ago, put out this database as really a good for the machine learning community. They made this database available, and it was really a wonderful thing. And they not only did they make the database available, but they actually organized a challenge in a sense like this one, where they had a massive monetary prize. And so in truth, they're trying to be incredibly nice and good. But of course, people figured out how to take their database that they released in good spirits and kind of crack it and reveal who the people were. And so let me tell you how they did this, and it's fairly simple-minded, but it sort of sets the basis of what we're going to do. So Netflix essentially released a database like this, where they had anonymized users. They had movies that weren't anonymized, and you could figure out what these movies IDs. When the anonymous person rated the movie and their rating. That's what they released, okay? And this, it looks very innocuous, like what's the problem with doing this? So what did people do? Not very complicated thing they did, but let's look at it. They found another database, this IMDb database, where there were also people not anonymous that rated movies, okay? And the key thing is you know what the movie names are, so you can connect them up. And they also do this on a particular date. And what people were able to do is they were able to realize, and not perfectly, this is more of a statistical or rough type of matching, a very sort of simple idea. They realized, a person on this date who rated this movie a 3 in Netflix, we don't know who this person is, it might be the same person as this. And you're like, well, big deal, we know this person's already revealed themselves over here. But the thing is, now once we know that this ID is associated with this, we can go in the Netflix database and see another movie they've rated, this movie I've called Netflix 666. And maybe this person, who knows, maybe 666 is not a movie this person wants to reveal they've rated. So the privacy breach here is finding out that this person has rated this movie a particular way. Okay? And depending on that movie, it might be a good thing or a bad thing. So that's, and the term that people use for this is a linking attack. So we've linked these things. Okay. So now what I'm going to do is I'm essentially going to talk about linking attacks to do with RNA-seq data, and I'll use that as a background. And first I want to introduce RNA-seq data. Probably you've all seen this, but the thing there's lots of this data. Okay, this is related to genomic data, but it's not quite the same thing. It's on human subjects, okay, and so forth, and we want to build tools and approaches to interact with this data. There's many large consortium that have built functional genomics and RNA-seq databases. You've probably all seen this. I've personally been very involved in a consortium called the ENCODE Consortium, which has developed a lot of these databases, but there's also things like the GTEx Consortium and so forth. And I think what's interesting for this discussion is that RNA-seq data has a kind of interesting yin-yang quality to it. So, genomic data, in a sense, it's only like the gang or something. It's got to be private. It's just the variance, right? There's very little there's very little idea of how part of it could be publicly released. Okay, I mean, there's some ideas, but in general, we want to protect the variance. RNA-seq data is different. RNA-seq data has this. I mean, the reads, as I'll describe, have variants on them, and there's a lot of stuff related to variants, but there's also a lot of stuff related to general biology. What genes go up in cancer, what genes go down. And historically, that information has been made available publicly. You can just download, the genes that go up in cancer, the genes that go down, genes are associated, that genes that change expression level when a person gets an infectious disease. This is usually public information. And the fact that it's public is a great virtue because it makes it much easier to deal with. And so the sort of issue is we want to think about, can we continue to release that public information and separate that useful public bit away from the sort of more radioactive variants, okay? So first of all, a little bit more, maybe people have all seen this, but just a little bit more about what RNA-seq data actually looks like. So if you run the sequencing machine, you get reads, of course, and those reads contain variants, okay, obviously. But what people do to quantify RNA-seq is they overlap the reads, they get a signal of where a gene is on and off in the genome, and then they might just collapse that onto genes. And at the end of the day, a lot of the information turns into just expression levels of regions of the genome, exons, and then genes. Okay? And so the first thing you can do to think about how to deal with RNA-seq data is very simple, is you can just think of a better file format for it. And we've thought about this for a bit. It's a very simple idea. Maybe we can just separate the reads, which contain essentially radioactive variants, from the quantifications. And so, so you can imagine a format. We worked on this thing called, we call it MRF. It's very similar to the CRAM format that you probably all use. It's also kind of related to kind of a compression idea, where you just store the read and you store where the read maps in the genome. And where the read maps in the genome is completely sufficient for building up the signal file, for doing the quantifications and so forth. But we've put in a separate linked file all the variants. And so there's this notion that you could download one file publicly, do most of your compute on it, only if you needed the file with the private information. So this is a sort of simple idea. This just shows a little bit more detail of how you would actually build this file format. And we spent a little while, there's, when you get into RNA-seq, there's tricky things you have to deal with. So often reads span, for instance, different exons. And you have to allow the file format to allow a mapping across a split. And there's various issues like this. And to some degree, like I said, CRAM does this. Now, CRAM doesn't think about the notion of splitting the file. CRAM is just purely a compression format, where you're storing the alignment positions purely because they take less space, not because you want to anonymize it. And what we're suggesting here is to do something like CRAM, but really to, in a very principled way, split the two files so that one is essentially has more radioactive private information. Now, the problem is you might say, well, that sounds great, and that sounds, you might say, so semi-obvious, and it's a good idea, let's do it. And you might think we're done. Unfortunately, not. So what I'm going to talk to you now about is, even if you think that's a good thing to do and we should do it, there's still a lot of variant information left over in that public file. It's kind of like, you take your plutonium away from your radioactive waste, you still have some like iodine there or something that you don't want to ingest. So where does that stuff come from? Well, it comes from what's called EQTLs, which basically link our quantitative trait loci that link the levels of gene expression to the genotype. So we can, of course, go from the level of gene expression to the genotype. The idea being that maybe if we have a high expression of a certain gene, that relates to a particular genotype someplace else. And abstractly, that's the idea. Traditionally, EQTLs look like this. I don't know if people have seen this, where you have, essentially you have three genotypes, homozygous, alt, heterozygous, or reference, right? Those are your three genotypes, and you have, say, overpopulation, you'd have the gene expression levels, and you'd get something like this. You could describe this as a correlation, or this multidimensional probability distribution, okay? And that's an EQTL related to a SNP, okay? And you can see there is information about that genotype in the expression, obviously. So now, of course, what we want to do to drill into this is to try to think about how to quantify this. So first of all, we wanted to quantify the predictive information here. Now we can, traditionally in EQTL world, people just describe this with the correlation rho, but for a variety of reasons, correlation is not the best quantity to describe the relation of this information. People obviously know that there are other information theoretic quantities that might be useful in this context. So one thing we decided to do is use this kind of conditional entropy, which basically is how much entropy is left in the distribution after you fix the expression level. So if you say, if you say my expression level is here, how much entropy is left in that cup? You know what I'm saying? Versus in another place, okay? And now what the advantage of this, the great advantage of this description of the EQTL is that this formula is additive. So I can take a number of EQTLs, or I can take a number of things and just simply add them up, and I'll show you why that's really useful in a second. And then we want to, now an EQTL relates expression level to a SNP, and so we also have to have some notion that some SNPs have more private information than others. As we've heard in earlier talks, rare SNPs obviously contain more private information than common SNPs. So we want to quantify that, and we're basically going to quantify that by some sort of information theoretic surprise of log 1 over the frequency, which you've probably all seen. And we call this the individual characterizing information of that SNP. And now, of course, the nice thing about using these information theoretic things is this, of course, is additive as well. So we can just add up the amount of leaked information just by summing up these things. And then to start playing with this, we're going to take this publicly available data set called the Giovanni's data set, which is related to the 1,000 genomes data set. So we have publicly available genotypes, publicly available gene expression levels on the same individuals, and we're going to basically figure out if we can kind of crack that. So let me show you what you get. So this is just sort of very simple-minded. This is all the EQTLs and Giovanni's, right? And now I'm graphing their predictability. Actually, let me start with this one first. Their predictability versus the amount of leakage. Okay, so these ones are leaking more information than these. These are more predictable. You kind of see there's a rough relationship, but obviously the really bad ones are the ones over here, which are pretty predictable, but they're actually leaking a lot of information. These things are colored by the EQTL correlation. Obviously, there's a rough relationship between predictability and correlation, obviously. You can also ask how much information is here relative to just a shuffle if I just randomly made up EQTLs, and so that's this red dotted line here. So you can see the information leaking is really the blues, obviously. And then, of course, I can exploit the property of the additive property to talk about if I take, like, for instance, if I take the best EQTL, and I say take the best EQTL for all the people on average, I'll get this much information leakage. And the best EQTL has a predictability of about 0.8, okay, on average over, say, this population. Then now, because this is additive, I can just take 2 EQTLs, I can add up their predictability, and I can add up their leakage. So I can say, well, how can I do 2? How can I do 3? So if I have 3 EQTLs, I get 5 bits of leakage. Now, if I go to best 5, you know, I'm getting a reasonable amount of leakage here. I'm getting up to 10 bits of leakage of information, you know, and on and on and up and so forth by just taking a few EQTLs. And so you can see just in a very sort of, I shouldn't say precise way, how much information is leaking out as I use more and more EQTLs on that population. And of course, I can compare this to what my randomly shuffled EQTLs would leak to. And obviously, a lot more information is leaking. So now that's the kind of theoretical leaking idea, but now let me show you how you might instantiate this into an actual attack and how this would actually play out in the world, which is not obviously obvious. But it's going to play out in the framework of a linking attack. And so let me tell you how this attack goes. So I imagine that there's a publicly available gene expression set. Now this is a little more abstractly described, where I describe just as a phenotype data set, but for these purposes, let's think of this as a gene expression data set. So I have people that have IDs, anonymous IDs, and they have a status. Let's just take HIV status, because that's fairly sensitive. So there's people with HIV, people who don't have HIV. And then we have the gene expression level. This is publicly available. I can download this from NCBI. This is the traditional type of thing. And the belief is that I will never be able to figure out who that person who has HIV is. That's the issue, right? Now what happens, and this is a little counterintuitive, the way I actually do this attack is I steal your SNPs. So I actually have your genotype. So you might say, how do I do that? Well, I get your genotype from another test, or I just walk around the room and I get your drink, I get your cup, and I take some SNPs off the cup. So now I have some of your SNPs. Okay, so you might say, well, they already have my SNPs, who cares? But I don't have your HIV status. Okay, so that's what I'm trying to get at. It's not your SNPs I'm trying to protect here. I'm trying to get at your HIV status. So now I have your SNPs. And what I'm going to do is I'm going to invert this database in a very statistically noisy way using EQTLs to make noisy, wrong predictions of their genotype for all the different variants, right, for these people. And then I'm going to match this up against the noisy sort of things I got off your cups, right? And my hope is that I'll be able to get some rough matches, okay? And those rough matches, again, I'm not getting your SNPs. The SNPs are freely given. What I'm getting is some of the people in the room, I've got off their cups, I've got their HIV status. That's the tactic. So it's very much like the Netflix. It's essentially, it's the same as Netflix. I'm getting that someone watched this movie, not who that person is, okay? Or their HIV status. So it's a linking attack, just like Netflix. Let me tell you a little more about how I would do this attack. So in doing this attack, what I might imagine doing is starting off with the database, and then there's a lot of things buried here. Exactly how am I going to predict those genotypes? I'm saying from the gene expression level, right? So I have to have a genotype prediction method. There's many types of methods we could use, and I'm going to talk about them. And then there's this idea that I can use auxiliary information, their sex, their population, their age, something like that to help with this. And then, there's this notion of once I've linked someone, I want to have an estimate of how well I've linked them. And I'm going to talk about these things. So first of all, how do we talk about my genotype prediction? So the genotype prediction basically is how I invert this function, right? So now I want to go from the expression level, and I want to get a 0, 1, or 2, right? So how do I do that? Well, you can think of different ways. One thing I could do is I could fit little Gaussians to the expression level with standard deviations. I can assume standard deviations are all the same. But actually what I could do, which is even more kind of extreme, is I could just say, I don't care about this complicated function here. I'm just going to look at extremes. I'm going to say, if you have an extreme expression level, you're going to be, one of the homozygous alt or rep. You know what I'm saying? And just forget about the heterozygous. I'm just going to, very simple. In fact, I can make it even simpler. I'm basically going to say, if your expression level is higher than a certain thing, you're a home alt, otherwise you're this. Just really simple-minded. Now you might say, well, that's stupid, but actually it works perfectly. Okay? Because we only need enough information to do a noisy match. And let me just show you kind of what I mean data-wise. So basically, I'm just looking at the extremes. I'm basically saying, if you look at a lot of databases, you'll get extreme gene expression levels, and when you have those extreme gene expression levels, it's the usual. This is the outlier attack. You can pretty trivially take the outliers, and that person has to have that SNP. Okay. Now, a lot of SNPs I can't call, but who cares? I only need a few to do the match, right? So now, let me tell you how well this does. So how do we think about how well this attack does? Well, what we can do is we can sort of look at it on this plot. Now this is a plot where I have sensitivity and kind of how well my EQTL is here. So imagine I take really good EQTLs, okay? But I only have a few of them. I'm obviously going to get less people in the database. And then as I take more and more EQTLs, I'm going to get more and more people in the database. Now I'm not talking about the specificity here. I'm going to make more mistakes as I go up this curve. But I'm just talking about the sensitivity to start off. And of course, we can think about when we do this, if we do genotypes only, if we add in the gender of the population. And there's a technical point, we might think to ourselves of separating the database we train for the EQTLs out versus the individuals used to a bigger database. And so there's a more technical point of how you think about that. So now imagine you picked a certain number of EQTLs and you say, you make predictions, and I know after the fact that 70% of those predictions are right. But how do I know kind of at the beginning which of those predictions, which of those individuals I predict confidently? What statistic can I use for that? So we found this statistic we call the first distance gap, and this is very simple-minded. It's essentially the distance between the best matching thing and the second best matching thing. How close are they? And the idea is if there's a big gap, I match the first really well, and then I have to go a long way to the second, I'm more confident in my match than otherwise. So simple-minded. And let's see how that does. So this is a little bit weird of a curve, but this is positive predictive value, which is some measure of specificity or how many errors we're making versus sensitivity. And now I'm going to ramp down this curve, right, with the decreasing sort of spacing between the first and second things. And so obviously when I start out and I have a very big spacing, I'm not very sensitive, but I'm not making many mistakes. And then I start making more mistakes and so forth. And then I can compare that, of course, to some randomly shuffled things. And the other thing that's kind of interesting, which is a side point, but is interesting, is in addition to looking at this distance gap, between the best match and the second best match, I can ask, well, who is that second best match? And it turns out, you probably can guess this, of course, the second best match, if you happen to have a relative in the database, the second best match is going to be the relative. And that, of course, is kind of interesting too. And this is the preponderance of the best matches to be relatives. Okay, so that's, how much time do I have? Okay, so I'm going to take a minute or so more to just talk about one other type of thing we could do with RNA-seq. So basically I've talked to you about the general problem, talked to you in detail about RNA-seq, how we can anonymize this, and I just wanted to introduce you to the notion of, well, maybe we could take away the EQTLs or the SNPs with very strong EQTLs, or maybe we could use this MRF format, but I just wanted to give you the notion that there are a lot of calculations that people do with RNA-seq that more intimately require the variants. And I sort of putting these out more as a challenge in some abstracted way to people here to think about, well, what can we do with these types of calculations? So the extreme calculation is allele-specific expression. And basically what that has to do with is, as you know, you have two copies of every single gene. And most of the time we assume that those two copies of those genes are doing the same thing, but they don't have to be. So your mom's copy can be doing something different from your dad's copy, and so on and so forth. And that broadly is called allele-specific expression. There's other phenomena called allele-specific binding and so forth. And now the really neat thing is that the RNA-seq experiment has in it a beautiful control, or it's completely worked out to measure this, right? Because the RNA-seq experiment actually has the sequence of each of the things being transcribed. And if mom and dad differ at a particular position, for instance, I'm showing this position here, we're saying mom is T and dad is C, you can just immediately see that mom has had his genes being expressed a 5-fold more than the dad's gene, okay? From looking at the RNA-seq data. And this phenomenon is called allele-specific expression. And it turns out there's a lot of very complex technical issues with reference bias and things like that I'm not going to talk anything about. But the end of this, what you end up with is, we're interested in this obviously, is you can make databases of allelic SNPs, SNPs that are seen in particular experiments to have differential expression levels, and we have a database we call AlleleDB that does this type of thing. And this is just a little picture of some of the things it has all these. So once you browse the genome, and some SNPs are allelic in a few people, some are some are in a few people, some are consistently allelic in many, and you can find bits of the genome that are fairly allelic. I'm just zipping through this kind of quickly because I'm not going to spend a long time. And so the point of that last bit is, what would you do with that calculation? How could you think about that? That's a calculation where the variance and the expression are much more intimately related than the normal thing we do with RNA-seq. And so maybe that's you can't deal with it, but it's something to think about. Okay, so let me summarize what I've talked to you about today. So we talked to you, my title was Genomic Privacy and Individual RNA-seq. Is it incompatible or feasible? So how do we think about those things? And so we started off, And I told you about some general ideas I have about genomic privacy. You know, the degree to which genomic privacy is different from privacy in general, and the degree to which it's similar. I think some of the issues are, you know, this inheritability of the genomic information. You know, makes it a little bit different, very, very fundamental and so forth. And you know, what can we do with it? You know, there's where we are now, where it's a very burdensome thing on the medical research community. Of course, dealing with privacy of the data is very important, but it's also very burdensome. We have the complicated consents and so forth. And I talked a little about, well, what we can do going forward. We have to have a legal framework for doing this, international legal framework for doing this. We also have to develop technology to help make this easier, whether it's doing computing in clouds, or I was focusing mostly on quantifying information leakage. And then I talked about some of the attacks that sort of form a background, particularly the Netflix leaking attack. And then I really zoomed in on this RNA-seq data because I thought that was a really interesting example of where we tend to have it has a public face but a private face. And can it continue to have the public face and not leak any private information? And I talked about that a little bit. You know, well, maybe we can just essentially release quantifications, which people do, and there's a better way to do that maybe in the framework of these, like in a CRAM file or MRF file, where you separate out the kind of radioactive variants or reads from the quantifications on the genome, and that removes a lot of SNPs and a lot of information for sure. But I wanted to point out that even that buried in the quantifications, unfortunately, there is still private information, and that of course leaks out through QTLs, which obviously link the expression levels to the variants. And so I talked about how we can quantify them using ICI and predictability, and then I talked about how we can use those notions to instantiate a practical linking attack, sort of pretty much like the Netflix linking attack, where we can phenotype people using noisy genotype linkages. And then we can quantify the accuracy of this prediction, develop statistics for quantifying them. And then at the end, I talked a little about this allelic activity as an example of a type of thing that just wouldn't fit into this paradigm. I mean, this doesn't fit into this paradigm of kind of quantified information, separating how you need the two things to be more coupled, so that it breaks this kind of paradigm I saw here. So I'll just acknowledge the people that have worked on this with me. I've for many years I've worked on the sort of social issues of privacy with this Duff Greenbaum, who's a past student of mine. He's subsequently went on to do a law degree. He's very interested in this world. We've written about this. The more technical stuff, I developed this EQTL thing with Arif Ramanchi, who's a research scientist with me. We have a little bit of software available for that. And I developed this file format, this MRF, in the framework of this RNA-seq tool package. And this was done by Lucas Habiger, a graduate student a number of years ago. And the allele calculations were done mostly by Jeremy Chen, who's a graduate student, and he worked in the framework of this allele database. And with that, I'll thank you very much for your attention.
So we may have time for a couple of questions.
How many SNPs do you need on average to do this indication?
Not that many. I mean, what actually, so what you probably saw from the quantification, for instance, is if I take, I think it was like 5 or 6 EQTLs, I get 10 bits. And if you think about it for a second, how many bits do you need to disentangle all the, obviously bigger population, you need more bits. But, with a reasonably sized database that we have now, looking at say a few thousand gene expression levels, you don't need that many EQTLs. You have to be very precise. You pick the best amongst the EQTLs you have, but you only end up picking maybe 20 or 10 or 20, and you're fine. You can match the people in the database. Well, that's the idea. That's what I'm proposing. So the proposal sort of is that, one thing you could do, which is, this is a challenge to people. I'm not sure this will work. This is almost like, Watson covering up his APOE. I'm not sure this will work. But the proposal at the moment is that you do this, obviously. You do what you just said. We just cut, those out, right? We just remove those, right? So the idea is if we just cut out all these good ones, you know what I'm saying, which is actually, this is a tiny amount of information. I mean, we're now talking about cutting out 30, 50 SNPs or something like that. If we cut out that information, maybe we make the database a lot safer. You know, that's the idea. I mean, now, is it really true? I don't know. I have, you know, I'll leave it to people here to figure out if that really works. Any other questions?
In this MRF format, I'm not so clear how you define the assemblies that you're going to move from the...
You mean the variance?
Yes, because if the sequencing machine, it makes errors, and if your coverage is high enough, you basically have at least one difference on every position.
Completely correct. Let me go through it. I mean, this is a little, oops, hold on. So I don't know if you can see this little cartoon thing here, but the idea is that, so the sequence machine runs, okay, so just let me say it out very slowly. The gene is expressed as a transcript. RNA, that's sequenced, okay? That has the underlying sequence of the genomic DNA. Its sequences make a read, let's just make it up. 500 base pairs, 250 base pairs, okay? Now, in that read, okay, now the read, I wouldn't say the read has the variance. I would say if you have many reads together and you put them together, you can make a variant call. But buried in the read is fundamentally the actual difference between that person and the reference. The SNV is in that read, okay? So in MRF, what we're proposing is the read, just the raw read, just comes off the same machine. It's given a index number 10, and it's stored in a database 10. It's radioactive, private, sealed up, okay? But what we store, what we give out to people is this. We say, there is a read, we're not gonna give you the sequence of that read anymore, that maps onto the chromosome at these positions, and that read is number 10, okay? So you can download that freely, okay? Now, and with this information, this is all you need, this information to now you have the map, you can make the quantifications, you can perfectly quantify on the genome, you can quantify gene expression levels, you're done. For a lot of the stuff in RNA-seq, you're done. Now, of course, if you want to do the allele calculation or you want to do something else, you have to go back to the private database and ask for read 10. You have to do that, right? Because you need that variant. But my argument is that for much of what you want to do, you would be happy with that half a data set. So that the proposal is that if you think of a data, like I say, I do think the radioactive analogy is useful in the sense of, I don't think you're ever going to get a totally unradioactive and a totally radioactive part, but I think the idea is on many data sets you can put the plutonium in one part, you know, and most of the data set is very removed of that information. So that's the proposal.
I have a question. Sorry. So the question is, what if there's a variation happen at the splicing site that could change the splicing pattern when you do the MRF? Could that be inferred from the MRF format?
Correct. No, correct. I mean, that's the next level that we want to get to. I mean, yes, that there's other. I mean, the process of RNA sequencing just or gene expression complicated. So you're right. Conceptually, by looking at just the splice variants available and which should be obvious in MRF, if you had I guess it's a splice QTL now. This is not as opposed to an expression QTL. You could then invert that. And we haven't, that's an idea, and it's a good idea. We haven't actually seen what is there. I don't know.
Your previous slide.
Oh, you mean with this thing?
That one. The public anonymized data, you still could cluster that information and find out individuals that are related to each other, because they are likely, if there is like people that are parents and children and so on, they might have certain changes, although you are hiding actually from the private data, you could still cluster them and say, well, this group will have a propensity to be kind of.
Well, I agree with you. You're right, but what I would say is that the word clustering, I think, is done, that's what the EQTL essentially does. That is the EQTL. And the clustering of the same expression levels together, the different ones together, associated with the variant, that is exact. I mean, in a sense, that's exactly what's going on in the EQTL calculation or something like that. It's just, you know, it described in a little different way, but in practice, that's essentially what's going on. It's a little, you know, played out, described statistically a little different, but essentially that's what the EQTL
So
is.
you would find populations that are similar?
Yeah, no, I mean,
either by relation or...
That's right. I mean, the parents and children, you probably certainly find that, but that just simply reflects the fact that they have similar genotypes and they'll probably have similar gene expression levels for certain genes. Fair enough, you certainly see that.
All right, so thank you very much, Mark, for excellent talk. And for the sake of time, we are going to move to next section, and we are going to have the presentation from the team of the track 1, and our first speaker is Zhiyu Wan from Vanderbilt University.
Hi everyone, I'm Zhiyu Wan from Health Information Privacy Lab from Vanderbilt University. It's a great honor for me to be the first one to present solutions as a competition participant. And, my solution is for the first task to mitigate the genomic privacy while sharing the data through beacon services. So for those who are not familiar with beacon service, I will first introduce a little bit for the beacon problem. This is from the aspect of the paper which Singapore and Basmande wrote in 2015. Basically, the bacon is holding a genomic dataset and sharing the aggregate genomic informations. So they're tracing back to 2008 and 2009. There is attacks show that if you share the aggregate genomic statistics, people can infer who is in this dataset. So as a countermeasure, the Bacon project is only sharing the the Bacon project only sharing the existence of the minor allele. So that, like a user or an attacker will query the Bacon saying, do you have a minor allele in a specific SNP position? And the Bacon will respond yes. The represent that the Bacon has that minor allele. No. So there is only two answers. This is a screenshot in the current website of the Bacon. Right? So you can cover like this the chromosome and the position and the minor allele.
and the response is like this. So what is a Bustamante attack? So we can see from this picture, the red block implies that the individual has a minor allele in a certain position. And the red diagonal pattern implies the beacon dataset has that minor allele in that position. So, like for this first individual, if you ask the enough queries, then you will be very certain that this individual is in this beacon, because all this query is yes, so it looks like he is in this beacon. And for another example, for this individual too, there is two queries that responds no. So the attacker is quite certain that this individual is actually not in the beacon. And however, for this individual 3, the response has one no. And so at this time, the attacker is kind of get a false positive result, because he is not so certain that this individual is in the beacon or not. So this is a summary of the Bustamante attack. The attacker knows the genomes of the individual, like the and SNP positions, and a sufficient statistic for the attack, which is based on the likelihood ratio test, is the number of yes, which looks like this. The xi represents the i's correct response, and the attacker will predict that the individual is in the beacon if and only if that the number of yes is larger than the threshold, and this threshold is set according to a maximal allowable false positive rate. So the attacker don't want to get too many false positive. So the objective of our solution is to mitigate the Bustamante attack, which I split to two parts. The first part is protect the privacy of the participants of the data set. So people will say, okay, what is the best solution? I would say the best solution is to share no SNPs, share no information. But of course, this is not a good solution, because we want to keep the utility of the genomic data. And in this scenario, if we make a constraint that the defender has a very, very simple action, which is he can only alter the response from yes to no for a combination of SNPs. Then our solution space will looks like this. Will look like this. When there is actually this is utility. So it depends on how we define the privacy and utility. We can define the measure we can define the privacy and the utility as measured from 0 to 1, and we want to find a solution that is in the upright corner of this space. But actually, in most cases, depends on how we define the privacy utility. In most cases, the ideal solution does not exist. So we would want to find a solution that is in that area, in that red area, that has a pretty high privacy and a pretty high utility. And we can see that if you share you share nothing, then you end up with the left up corner. And if you share everything, you're in the right, but have a very high risk and very low privacy. So here's my solution. It consists of four steps. The first is sorting and mitigation and noise addition and optimization. The first step is sorting. So I will first sort the SNPs according to a certain measure, which can be the 3 measure, but can also be other measure that you can define by the users. So the first one looks like a very simple one, which is the minor allele frequency. This is based on the intuition that the real allele is very useful for the attacker. So if this is also like the baseline is related to you just say the baseline that you are sorting it according to minor allele as well. And the second measure is the absolute difference between the absolute difference of minor allele frequency between the pool and the underlying reference. What is a pool? Pool is that data set, and the reference is another public data set that we sometimes reference, like we always use the heat map or 1,000 genomes. So as the intuitive is that if the pool has a very biased minor allele, then the attacker would use those very biased allele that give him the best attack power. And actually, in the results section, I use the third one, which is log likelihood ratio correspond to each SNP. This is based on the fact that the log likelihood ratio is additive across the SNPs. So every SNP has a log likelihood ratio, which means if the attacker has only this one SNP, then what is his detection power? So we want to see what SNPs give the attacker the most powerful, most information. And the second step is the mitigation strategy, which is how the defender choose which SNPs to flip on the altered. So, like we have already sorted the SNPs according to a certain measure, then we can set the parameters. The first criteria is we always flip the top K SNPs from yes to no. And the second one is we don't fix the number of SNPs, but we fit a threshold that, let's say we want to we do not want to share like the real SNPs that only 2 or 3 people share in this data set. And the third one is similar to the first one. And actually the K, how to set K is a problem. If the defender has some case data set and some training data set, they can then the K from the training data set. Like if you set a K and it turns out it is too large, it loses too many utility, then you can decrease it. And the third step is to add a random noise. It can induce some uncertainty into the result. and also it increases accessing costs and false positive rate to the attacker. We denote the sigma from 0 to 1 as noise level, and the Fi is the minor allele frequency of SNP-i, and the X prime I is the beacon's final response for the SNP-i. So if the correct, so this is the probability that you flip a SNP. So the first strategy is you add the same noise to the other SNPs. So like a 5% chance you flip the answer from no to yes or yes to no. And the second strategy is you alter the SNP with the more a larger allele frequency than the SNP with less allele frequency, like the picture on the right. And the fourth step is to optimize according to the evaluation metric. And because as long as the defender has an evaluation metric and he has enough computation budget, he can run this several times to explore the search space to get to the global or local optima. Like random work, like you can add some noise and to see if this give you a better evaluation metric. But however, this strategy, based on that, the defender is provided with a case data set. So it's very limited. Sometimes you're going to be overtraining or something. So the data set I use for the experiment is provided by the organizer, which is one-cell genome phase 3 data set, the chromosome 10, and it has about 2 million SNPs. The test data set has 500 samples in the baking, and then the case data set has 500 not in the baking. So here's my interpretation of the evaluation measures. It is defined by an organizer, which is the number of queries the beacon responds correctly before an individual is identified by the baseline data. So the utility is defined as the number of correct queries or the portions of correct queries. And the privacy is defined like this: if no individuals are defined, if no individuals are re-identified, then the privacy is 1. Otherwise, it's 0. So we can see it's actually it changed the optimization problem with two objectives to one, that you only want to optimize the utility while you make the privacy to 1. And here is the results. So the baseline is you don't do any mitigation strategy. So you publish everything as it is. So the true positive rate is 100%, and the false positive rate is below 5%. And here is one instance of our method, and the query is run randomly. So this is just one instance. We can see initially there is no attack that can success. And then there is a little success. But the success disappeared because of some noise we added to the responses. However, when there is more and more SNPs that the attacker queries, then they got a very relatively high detection power. And here I present the incorrect response, which is the noise we added to the system. How many times the defender lies about the response. We can see that when there is in the point there, the attacker got a very high detection power. There is very a low trend of the incorrect response. And this is another run for the for this experiment. We can see these different runs. They have very different results because the order of the query really affect the experiment a lot. And this is the result for a different data set, like a different sample of the data set. So in this run, you can see there is our method can result in zero detection power. And the conclusion is that the privacy risk has been mitigated substantially and the data utility is kept in a high level. We can see that only 5 to 10% SNPs need to be flipped to mitigate the detection power. And if you see the details, you can see actually for the two data sets, the case and test data sets, their log likelihood scores are very close to each other. And here is some future directions. We can consider there is a smarter attacker that can change his attack strategy according to according to the defender's strategy, and we can change the noise addition model to be a better one, like use some differential privacy techniques in it. And we need to improve the computational efficiencies. Right now, to run through 2 million SNPs, it takes about 1 hour. So I cannot do too many experiments. And the fourth one is we can consider the defender has other actions, like not only altered from yes to no, we can also alter it from no to yes, and we can also we can consider that if the defender can mask the SNPs, like the response is done to no instead of no yes. And we can also add some accountabilities to the defender, like the defender can know who the attacker is, like the attacker has to set an account to get those information. And also the evaluation metrics can be other, like the utilities, the measure of the utility can be not only the number of SNPs, but also we assign a different weight for different SNPs, because some SNPs they apparently are more valuable than some others. And also for the privacy metric, we can tolerate some risk, we can not only one individual is re-identified, we can set the number of re-identified individuals as a measure of the privacy, then the results will be different. Okay, that's it. Thank you. Questions?
I may have only take one question if there's one. Okay, if there's no question, let's move on to next speaker, just to catch up the time. Thank you. Okay, our next speaker is from also the class 1 participant. Okay, so speaker is Moni Aziz from University of Manitoba. From Canada.
Hello. Hi, I'm from University of Manitoba, Muinul Aziz. It's actually a little hard to give the presentation when you know the results, but I had to do this once and maybe in the afternoon as well. So let's get on with this one. This is Bustamante attack on beacon services. So I will give a little bit of introduction because the previous presenter actually gave some bit of it. So what is a beacon service? You see this kind of like queries in a beacon. For instance, do you have this allele or do you have this A, T, G, or C in a specific position like that on some specific chromosome? So what the beacon service does, it actually tells you like whether, yeah, I have it or no, I don't have it. And what I can add to the previous presenter is actually if you go to this link with the hashtag, you can also like query the beacon mentioned in this one. There's like 200 or I don't remember, like it was presented earlier, how many organizations is there in this beacon service. So moving on, this is their main paper where they address like these beacon services and all that. And why this thing is more like popular right now is mostly because this is a federated approach in a sense, like where each data owners give their data to the centralized system telling like, yeah, I have this data. It's kind of like aggregated data. So it's a little easier approach to do. And also the one other thing that I'm going to mention is like it's a faster access to the data, meaning you have an API which you can access for doing research and all that. And here is the diagram that they gave on this paper mentioned here. But if everything is good on this category, like in a beacon service, what is the wrong and why it's not that much harmless in a sense. So this is the Bustamante proposed attack. It's in 2015. What they proposed is like if I have some part of your genomic sequence, if I give an unlimited amount of query to give to the beacon service, I can give answers like, okay, yes, I have you on this data set, or no, I don't have you on the data set. So it's just like a relinking kind of attack, de-identification kind of attack. So what they did is they took two hypotheses, null one and an alternative one. So in null one, they told, okay, if this hypothesis is true, that the person is not in the beacon service, and in the other one, vice versa, it goes on like that. And they have this xi, which is the result from the beacon services, and this dn is the probability that you already pre-compute when you have specific terms. I will explain this dn. And also I will explain what the task one was a little modification from the original Bustamante attack because it's a little important, I would say. So this dn is calculated with this equation. It's actually equation number 69 on the main paper. So by that term, you already know how many equations that paper already has. So it's a little mathematical paper, I would say. But this equation is a little bit important because this A and B, what you see, is what they assumed is the alternate allele frequency follows a better distribution. So this is a big assumption in my opinion because we actually can know the specific frequency of each position. So this will make this problem a little more harder in the future, because this re-identification what they did is only this n will change. This n is the database size. So if you have a higher n, your probability is going to get low each time. But if this frequency is now going to change in the thing that's proposed earlier in the task one. This whole inference thing is going to change. So you'll have a better and modified attack on the beacon services. So we did evaluate the code that we were given by the committee. Actually, it was on the modified attack. But mostly I will give my solutions around this original Bustamante attack, because like the authors actually shared their code. This guy now, the Suya Singapore, actually works in 23andMe right now. He graduated, so it was grateful of him to just give me the code, and it's actually a like pretty big implementation of over what they did. So over here, what they showed is the number of SNPs that were being queried. Like after this 2,500 queries and these 5,000 queries, you can actually get, okay, the person is in the database. I have a power of 1 over the LRT, the log likelihood ratio. And this is the thing for the relatives. Like for instance, the 1 is that person, 0.5 is their parent or their direct connections and all that. So you also like we identify their siblings and all those stuff in this one. So this attack is a little, I would say, a little different from the second and third task in a way. It is more about privacy. It's more about the privacy of the participants, and you can't really handle this thing with the crypto solutions in a way. And in future, in my opinion, that doesn't really matter, but you will see this kind of problems coming up again and again, because most of the secure solutions we have right now can be implemented, as you have already seen earlier, is very efficient and fast and can be done in clouds and all that, which we will talk in the afternoon as well. The proposed solutions. So I believe the first participant, what he did, he proposed a solution based on the data set. If I'm not wrong, correct me if I'm wrong. And the method that I'm going to propose is on the output of the beacon. It's only because my approach to the problem was I need a solution which is kind of a lightweight thing and also can be implemented on the central thing, like on the output only, not on the data, because you have many organizations giving their data to the service. So you can't really actually tell them to comply with the thing or say, okay, change your database and add noise to your data or something like that. But what I wanted to do is I wanted to change only the outputs, nothing else. So the perturbation of the outputs, does it help? So the proposed solution that I made was first the randomized response with biased randomized response, and the second one is a sparse vector technique, which I'm going to show later. I'm not going to show the privacy utility graphs or anything like that, just the basic solutions for the time. And also some solutions are already, I think, being proposed in some journals I've seen. It actually utilizes the access control, and also it's coming in the literature again and again, the access control and policy that we need around this beacon service, which is because it's a publicly available data, publicly available aggregated data. So we need some kind of access control to this data as well, some kind of tired system, whether you have access to this data set or that data set and all that. So moving on, randomized response. Randomized response is a pretty old thing, and we all know it's been around there in the statistical phase, like to remove biasness from the whole study and all that. Initially, I had a different example, but let me give an example of this kind of randomized response. It's like, don't hold this example against me. Like 2 days back, if I asked you, like, do you vote for this guy or that lady? So back in your mind, this is a serious privacy preserving question. So in your head, you do a random coin toss, and you come up with heads, and okay, then you tell me the right answer. Or if you come up with tail, and you do another coin toss and give me another answer, just quantifying that people actually voted on this election. So moving on, there's another thing to this. This is a bias. So we do a random bias coin toss in this thing. So the bias coin toss is thing, you have a specific, like it's 50, not a 50-50 probability, it's a different one now. So if you have a lower bias, there is more like true results that you're going to get out of the system. So it's a very lightweight implementation. So what happens if we do this on the original paper? So this is the original Bustamante. As you can see, this is the original graph, and this is with the bias 80, meaning like I did it actually vice versa on the implementation. Like I will give 80% of the time I'm gonna answer you correctly, like the bias is 80 on the whole thing. So this thing actually goes in 4,000 quid. I actually couldn't run this for 1,000 more. It's actually, I ran this on the Canadian cluster of the Westgate, but still I had computed this yesterday, so I'm just putting it yesterday. It was not on the original slides. So with bias like 90, you actually can get it around like 0.9 or something. I don't know, it's in 40,000 quid, I believe. And in bias 85, that's there. And theoretically, what is the graph? It should be around here in 5,000. But with randomized response, you can actually go for that fast, because it's also another thing about randomized response. It's a very lightweight implementation. You just say, okay, I'm gonna answer it yes or no, just quantifying the privacy on the output. And sparse vector technique is, on the method I also gave this is the basic algorithm taken from the book, Algorithmic Foundation of Differential Privacy. So what in this algorithm is actually the plain vanilla, or what you can say the sparse vector technique. So what it does is like, my intuition on the whole, I don't work really in privacy, there's a disclaimer at first, I will mostly talk about a security thing later in the afternoon as well. So what I wanted to do is like with Laplace mechanisms or any other mechanisms you have on differential privacy, with more queries that you do, your privacy guarantee actually lowers down with more queries answered. So in sparse vector technique is a really good fit in my opinion, correct me if I'm wrong, but the main theme of my idea is the sensitivity of these queries are not same. Like for instance, some positions of some answers that I'm giving is actually no, I don't have the data. That one is not that sensitive. But some of the answers are really sensitive, like, oh, I have only one person with that data, so that one is really sensitive to me. So this is a plain sparse vector technique. So I didn't actually give this one I don't have any graphs for this one. But as you can see, you can also have a manage a threshold of some kind of, I will always answer 5,000 queries, which actually like tops my threshold. So it's there. And finishing up, the modified attack scenario, I will return, as I've said earlier, I will return to this one as initially what the assumption was made on the main paper, actually the implementation was different, like the experiment that we had to do on the task one is different from the original paper. So what's the difference? The difference is this beta distribution thing. What the original authors, Bustamante and Singapore, what they assumed is only the adversary knows the total these parameters, A and B, the beta distribution. If you have an allele frequency and all that, you see some kind of, it follows a distribution, right? So this distribution, what they call, okay, I have this database. Okay, this database follows these two values, this beta distribution. And what they did, they actually calculated their probability with this A and B, nothing else. But if you have specific frequency, okay, for instance, I have this AMT frequency 98.02%. So now I have a better inference thing on the whole position. And now there is only one person in the data set who has that thing. So this thing is a little hard. So that's what's the difference between the Bustamante, original Bustamante, and the modified attack scenario. Actually, the solution that both of us gave is actually on the modified attack scenario. So with this, I'm gonna end the talk. Actually, I think I'm on time. So with that, thanks and any questions.
Thank you very much. I could take again one question if there's one. Yes, Brad.
So just a quick question about the sparse vector technique.
Yeah.
So is this really appropriate in the situation when your responses are binary and you're not really asking questions on a continuous level?
That's one thing I was also wondering in that direction. Like sparse vector is also all the differential privacy mechanisms is actually you have a continuous variable kind of thing. You have a certain threshold. If you hit that, and you go down below. What I wanted to use the sparse vector mainly because it has a certain sensitivity issues. Like you can tell, okay, these positions or these queries are more sensitive. So if it goes that way, so I have a threshold, so I have a count, and I will cut those down.
So if you fix your sparse vector, if you amend it so that it's guided by like
the frequency,
discriminatory capability of the SNP in question.
Actually, the data.
Say that one more time.
So if you have a query, for instance, beforehand, so if you have a query, so some queries I already know, okay, these are more important.
Important to whom?
Important, like to the adversary. Like I have only one data.
For his attack.
Yeah, for the attack.
Got it. So that's how you would reweight it.
But in my opinion, randomized response is a better approach in my position because it's lightweight and you don't have like all those privacy things. But for the modified one, I think like I only use the vanilla. I didn't explore into that category of differential privacy because you can also use it on the data itself because you have a different structure on the data. You can actually cut those one which is higher sensitivity. So.
Okay, we can take one more question.
I have
Another quick question on the randomized thing. So, if you consider that the attacker has information of the correlation between variants, then he can essentially understand which ones are wrong, right?
Yeah. So one thing is like, for instance, if I got your question right, let me put it in this way. For instance, I query a specific position 2 on chromosome 2, and the thing is A. So in randomized response you get, no, I don't have it. And he also asks for T. He also says, okay, I don't have it. And for another query he says, I have yes in both of them cases. So you can't really infer which is what. Like you have to run it a whole lot of time if you want to. Like
if you use the same parameter for the
yeah, if you use the
response
same
for
parameter
every SNP, in aggregate over time, you will be able to learn
yeah.
the correlation.
So that's why there is a bias, specific bias that you can change. So if you change the bias, you'll have more false results. And if you have less...
But my question is more on the correlation between genomic variants. So for example, if you ask genomic variant 1 and you know that it's correlated with 2, so if you get a yes answer for 1, you're expecting to get a yes answer also for 2.
Oh yeah.
But if you get a no,
like
probably
kind of LD-like
you can infer
like
that what you get was wrong, right? So
yeah.
you can reverse engineer the thing essentially.
Yeah, actually on the one thing I didn't show is like there is a specific delta involved in all this equation. Delta is like the sequencing error in all this. You can think of like, okay, there is an error on the, we can discuss this offline.
Yeah, please discuss offline. Okay, so we now have pretty tight schedule. We have 1 hour for lunch. I think lunch is outside, if I'm correct. So, but we'll come back and start our afternoon section at 1 o'clock. And of course, you feel free to have lunch here and discuss with the poster authors. Thank you very much. Thank you.
Before we disassemble
great. No, I mean, there are whole concepts of the much it's very exciting. Like, in terms of how we want clarity on how you make that decision. We're not going to give you the autonomy to make that decision because we have to pay for it for this. But it's hard because, I'm not, I mean, if I can't, I definitely think there are very hard, very hard to do. The only way now, that's why I think I'm so far.
All right, priorities. America first. Oh yeah.
That's what I was
Hello everyone, maybe we can start our afternoon session. So for the first session in the afternoon, we have our keynote speaker, Dr. Michael Steiner from the Security and Privacy Research Lab at Intel. He will present us the collaborative analytics in genomics of abstraction and alternatives. Dr. Steiner is a research scientist at Intel Lab. Previously, he held a position at IBM Research in India, USA, and Switzerland. His work ranged from cryptographic protocol designs, analysis over secure architecture, implementation to penetration testing in the domain as varied as electronic commerce, payment system, compliance management, Web 2.0, cloud, and smart grid. Most recently, he is focusing on using hardware security as a foundation to enable scalable multi-party computation. So let's welcome Dr. Steiner to present us this work. Yeah.
Hello, everybody. Thank you for the introduction. Well, okay, to make our lawyers happy, some disclaimer. Now to the real content. I guess for the general motivation, I'm clearly preaching to the choir here. We all know analytics on genomic data has a huge potential, be it in the study of diseases, the drug development, with the ultimate vision of precision medicine and the like. But we also know that data sharing is an essential component of that. For example, well, because just we don't have all this data at a single place, and we need to get powerful analysis, we need them collected at multiple places. And lastly, but not least, of course, given our background, security and privacy is a paramount aspects of that. Now, okay, so what we really want to have is some secure and private collaborative analytics. And so the somewhat simplified view on that is we have parties A and B, but of course in practice it could be much more than two parties, which want to do some analytics function F jointly, and they want to do that over some sensitive data A and B. And that should be obviously correct, so the integrity should be guaranteed. But also we want to do that without undue privacy leak. So I guess the simple approach that some of us, you just say, well, okay, we identify this data, we give it out to put it somewhere together, and then we compute our function F, and good things happen. So that certainly should, well, actually, it's a good question to what extent this gives you the correct result, because the de-identification might give you some loss of utility, but there are also, from a security perspective, aspects that it's usually a brittle security, because context might allow you re-identification afterwards. And you can somewhat optimize that, maybe doing it very specific. But still, ultimately, another big issue is that you have the loss of control. And if you give up the data, there's a lack of governance. So well, what are other ways you can do? Kind of the better way is you essentially exchange now your function, you revise your function, or you analyze your function f and look at the privacy property computation of it, or kind of change it in a way that it's privacy preserving, and you do that, for example, using differential privacy and the like. Then, if you have such a function f prime, you give the data to some place, and then you execute this f prime on this data, and then the property of this function f gives you the desired privacy properties. Well, that looks kind of good, because now we have a better defined privacy and better controlled privacy loss. I also switching to this more function-oriented kind of definition rather than a data-oriented privacy. But of course, there are two big questions. On the one hand is who computes now this function, because the privacy preservation of the function f prime is only guaranteed on the official output. But obviously the inputs still have to be private, side effects of the function have to be private. So who could you do that? Well, of course you could use something like fully homomorphic encryption, and there are certainly ways how you can do the standard homomorphic encryption, which is not really, it's only a two-party setting, a multi-party setting, and for general computation, but it's definitely not super fast nowadays, and there's also technical challenges to do that. Of course, we can also just give it a trusted party, that solves it also, but who is that party? So the other aspect, of course, is also how do we decide what is the acceptable privacy loss? What should be this function f, and what are the properties? And this is certainly an important question, but it's kind of somewhat orthogonal to the first part, and so in the following I will focus only on this aspect of secure computation. So, well, traditionally, and all of you are aware, because in this workshop there's a lot of works based on that, also in history, well, that's where secure multi-party computation comes into the play. And that is very nice, kind of, because we have very well-defined security properties. It composes also quite nice with privacy preserving, kind of. It makes it somewhat simpler. I mean, you can do custom protocols which will be distributed and somewhat more efficient, but that way it composes nicely. And we also know, like from a crypto perspective, we have protocol which can do it essentially everything and fairly practical. And as all of you showed in this workshop, it works very nicely on genomics data too, at least in principle. But as usual, there's always a but. And there are two aspects which I think are a challenge in that space, and that's on one hand scalability, on the other hand is ease of use. So when I mean scalability, kind of, you obviously have shown already results on pretty reasonable use cases, but on the other hand, if you look at some, look at the bigger picture, that if you just would take, like for example in the cancer research space, if you would want to sequence everybody, just new patients from 2015, and just look at the data we would have generated there, that would be 4 exabytes. On the other hand, it's also kind of at various studies, obviously you don't always need this 4 exabytes, but I mean there are cases where we're definitely talking about terabytes and more, kind of. And the other aspect is regarding kind of the number of parties involved, and in particular also where these parties are. They're potentially on a national, on a global scale. So there is certainly communication, wide area communication is involved, and many of the crypto protocols, if not most, do have some pretty big challenges if you combine kind of this wide area network and the number of parties. The other aspect, of course, is also the ease of use, kind of. So the people ultimately using these tools, they are not experts, kind of. They already have a lot of existing tools, kind of, and they want to reuse that because there's a lot of intelligence in the past on that. So kind of, can we satisfy that with where we head in? So, okay, now I guess I'm getting to more, or you see, well, if it's not obvious before where I'm heading at. But multi-party security is in its essence really an abstraction. I think that's a key part. And it's formalized via trusted host, and the realization, as we usually say if we talk about MPC, it's a realization rooted in cryptography, cryptographic protocols, secret keys, and the like. But this being an abstraction, there's of course the question also, are there other realizations? Can we do better differently, and hopefully better? And the answer is obviously yes, that there are other realizations you could do, and I think a promising one, if you think at these two problems I mentioned before, is a realization which is rooted in hardware security, or rather than, or actually, rather I get there, cryptography, and essentially exploiting trusted execution environments. So what I would call now like a hardware MPC, rather than what traditionally MPC is called, which is really a crypto MPC. So okay, let me give you a bit more background about the foundations, or what does a TE mean? Okay, it's an execution environment, not necessarily that kind of execution environment, although that might be trusted too. We're talking about an execution environment, which means like a processor with some memory, potentially some storage, and peripheral. And what makes it trusted, or is that this environment is now isolated and it's integrity protected and isolated from the normal execution environment. By normal execution environment, it's like our applications, operating system, actually firmware, our aspects. And all of that protection is now enforced by hardware, and it's tolerant to software, to some extent hardware, side channel attacks. I mean, that varies depending on the actual technologies, and we get to that a bit later. And in particular for this space of multi-party or also for cloud deployments and the like, an important properties these execution environments have that they can prove, again based on hardware, their identity. And identity means here not like a normal end user, but it's like the hardware component, the code and the configuration running in that TE to remote parties. So that's called remote attestation. There's also a somewhat related aspect that it also allows you to do locally encrypt storage called sealing, which only this particular code identity can access. And there are a number of examples ranging way back in history. There are like smart cards, Java cards kind of has some form of a TE. Then Intel's TXT, or particularly the TPM part of it, so it's known to a number of people of you. There's ARM's Trust Zone, which is also fairly widely existing hardware, and lately there is Intel with the software card extension SGX. And so let me go a bit more into detail to SGX, kind of because I think it's at this moment the most advanced technology in that space. So traditionally, we have kind of if you think of an application which has now sensitive data, the attack surface is fairly large because it's the application, it's the operating system, it's the VM, potentially there's some hardware. And this actually, to some extent, holds also for some of these TE technologies I mentioned. Like kind of in Trust Zone, you only have the secure world, so now you have really flexible TEs, multiple ones. You also need the form of a VMM, and with TPM, TXT, that's the same. So what we change now with XGX, that kind of the TE is an enclave. It's essentially a kind of a sub-process in a normal application, which has controlled access to secret, and it also has flexible ways to do attestations. Given that we are talking here also about privacy, it's interesting aspects of that. There's various degrees of anonymity you can have, either pseudonymity or also unlinkability, which depending on your use cases, and which is also stronger than the properties we had from TPM before. So, but the key part now by being just this sub-process of this application is that you drastically reduced the attack surface, and I'm getting more to that. So there's much less code. Primarily there's the application code, which ultimately some application code has to be kind of exposed to the surface at some level. So that's kind of one dimension of it. The other dimension is that kind of the whole philosophy is that it should be as familiar in your development and deployment environment as everything you already do before, so it works with the standard operating system and programming model. It works kind of in a single application environment, and it builds on existing ecosystems and expertise, at least to a large extent. Well, yeah. And kind of given that it's this familiar environment, then the deployment model is also easier because it's not that much a bottleneck. Because actually, probably most of you have several, one if not several devices which already do have some of these T in hardware, like in your cell phone and in other places. But actually, very few of you probably use them. So, which is clearly there was a barrier to entry because kind of it was not so easy to use them and to deploy them, and that we hope to improve with that technology. So just from a high level, kind of what's the life cycle of such a TE, kind of the application starts. It's built, it's decomposed in a trusted and untrusted part, kind of, which then at runtime the untrusted part creates this trusted enclave in trusted memory. It defines a well-defined set of entry points. And then it can call the trusted function, but as I said, only exactly through these well-defined entry points. They are all executed now in this trusted environment. And you return, but kind of all of that computation is done in a way that now kind of privileged systems, codes, software, VMM, BIOS, SMM, all of that has no access to the memory because the hardware prevents that, any other software to access, or even our enclaves to access kind of that enclave. But not only does it give you security against software attack, it also gives you security against hardware attack, which I think in this kind of cloud setting or multi-party setting is even more crucial. Because the whole computation and the state of this computation in memory is essentially kind of secured inside the CPU package, which means like kind of data and code will be unencrypted inside the package, but everything outside of the package will be completely encrypted, so secured, and not only encrypted, but it will also be integrity protected, including strong integrity like replay detection, which otherwise actually open up a lot of very powerful attacks if you don't have that replay detection. And by doing all of that, there's a lot of physical attacks from the outside are prevented. There's still some like more side channel-like attacks are still possible on that level, and then get to that a bit later also. Okay. Well, okay, yeah. So then from a development perspective, kind of, as you said before, you have to split your application, you have to define these kind of boundaries, but there's a lot of tooling which already helps you there, kind of to once you made the design decision, what is trusted, untrusted, and to decompose this application. And there are libraries for primarily now from SGX from C++, but they also integrate in your standard development environments, kind of which do the heavy lifting of this interaction from the application and well, the untrusted part of the application and the trusted part. And so essentially you can use mostly your existing familiar tools to develop, build, and debug your applications. So the SDK is what Intel offers, but there is also now quite a bit of work going on all over industry and academia, who builds additional richer runtimes, more powerful runtime environments, like libOS variants, also container systems, various distributed runtime environments. So to summarize what we get from terms of properties in SGX, we get certainly protection against software and firmware attacks, also hardware attack in that sense, also prevention from operators and administrators. This in a programming model which has very well identified entry and exit points, which makes also building the software somewhat easier, robust software on top of that easier. So I mentioned side channels. So there is a priori in the base hardware, it was not a big design goal initially to prevent side channel, and also there were papers which showed up that there are actually, like if you're an untrusted operating systems, there are a lot of very powerful side channel attacks you can do on playing around with the page tables and the like. But there's actually also in that space a lot of ongoing research. I also work from Intel on preventing that, and there's actually a very interesting or promising technology or approach to that, which will be presented in the NDSS 2017 on actually using existing hardware. You can mitigate certainly the controlled side channel, controlled channel attacks fairly effectively. It's also from a more code vulnerability, of course. Code integrity is a crucial part of that, although I mean that's true even for the crypto part, code integrity. But there is also there's lots of hardware help which will come. There is now the control flow integrity technology, which Intel is working on. They just published a preview on that, which should help you making your software also more resistant to the standard kind of bugs. Anyway, so that's kind of the background on TE and in particular on SGX. So let's return back. What does it mean now, kind of, if you go to a hardware NPC based on such technologies? So you would think, well, right away, okay, it's all done, but it's a bit more complicated. It's not completely for free, because if you think of an NPC perspective from the abstraction, clearly you get the isolation and of the TE and T-Tech is a key part, but there is the ease of use aspect, so you probably want to have a runtime which can allow you to run existing programs, and also like the lifecycle management is an important part. You want to have kind of properties like in a Docker or container or like. So you need some runtime environment which is customized for that. More importantly, you also want to confine the function f, kind of like even if there is a bug, or well, actually before I get there, I mean there's one part, of course, there's this function. It's actually in your trusted host, you have multiple entities giving different types of input and outputs, so you definitely want to make sure that is followed, and that you want to do by somewhat separated the policy on who provides which input and who gets what output somewhat, and to the enforcement of that also in the runtime. You probably want to, yeah, I mean that's what I mean here by correct connectivity. You also want to potentially shield even in case of failures, you want to, or potentially bad application, you want to protect the cloud environment or the host of that TE also from the application, and so you want to have like a dual-sided more isolation. I mean, usually these trusted environment, they protect only the inside from the outside, but in this case, you actually want to also have the outside from the inside, and you need some technologies like Minibox or things like that. Yeah, so, and definitely we want to leave the control with the data owner. So given that we're here talking about a lot of data, so he probably still will prepare his data, he will encrypt it, he will send it to the cloud environment, but he will give out the key only if everything looks good and fine, and that's where we get now the crucial part of attestation, where actually we have to solve now also a number of problems in that space, which kind of, to make it somewhat usable, kind of is, we want to structure layer kind of the application code, so we also need a layered form of a composable form of attestation. Then the other part, I think it's also a bigger challenge in practice, more in practice than in theory, is kind of now this code, kind of this attestation just gives you some code identity in an abstract form. Ultimately, it's a hash of your code or something like that. But ultimately, you want to reason about that code, you need certain properties which you have assured. And this has to be done that multiple parties can reason in a single party case, it's kind of easy. You build your own code, you develop it, you compile it, you send it, you know what's in there. But now this is shared code, and from the infrastructure as well as from the function. And actually, I would argue some aspect of that applies even if you just think of privacy preserving computation on top, even of crypto MPC, you need such properties also for the function, that whatever privacy preserving function on top is implemented, does it really have the right properties? And is it exactly the function or the implementation of that function which you have? Well, and so based on that attestation, you really want to have now a mutual agreement that all parties involved, they agree on the policies, on the function, and only once everybody agrees, kind of, you will really release the secret to that. So that's kind of for the single case, but in practice, again, if you go to the genome case and we want to scale, then actually you really want to you want to have this abstraction of, or you want to scale across machines, because it's not a single machine will not be fast enough, kind of. As at least in some of these computations here, at least with what I've seen now, they might take days even on kind of in an insecure environment on multiple machines. So you definitely want to have a distributed environment. So you need kind of some distributed programming model, but ideally you should, well, okay, I guess I get there to the next state. Well, hold that with the model. So you want to first of all probably partition your environment. Not everything has to be multi-party computations. Kind of, so having any tooling which decomposes that, and there's also quite some interesting work, actually quite a way back, kind of, which more from a crypto perspective looked how can you decompose applications so that only kind of minimal parts really have to be secured, and because certain parts can be decomposed and they touch only individual entities part, and so they can run it themselves. But the other part to the, or actually the second part to the model computing, so you need kind of a programming environment, but you also need that in a way that you can kind of outsource as much of that environment or the orchestration out of it into an untrusted part, that you really have only to have a minimal chain kind of which does that. And kind of what we do, and this control, kind of how we envisioned it, how we do it now in some of our own projects. I mean, it could be somewhat implicit, but in our case, the explicit was easiest. Is kind of, you have this single MPC controller, which ensures, like, kind of now this distributed system still ensures the information flow and the control flow integrity, like the contract, which we kind of mentioned on a previous slide. And to some extent also this indirection, as kind of a usual thing in computer science, indirection solves an additional layer of indirection, always solves problems. Kind of it gives us better layering and also certain transparency to the outside, because the people interacting with the cloud, they don't want to know, or certainly the cloud provider doesn't want them to know about individual machines and where they are, or as much as possible, so it gives us transparency. Okay, so let's bring that back to how does that compare to crypto MPC? So I think it's definitely from an ease of use, programming, and lifecycle support, quite better. I mean, that said, I think, I mean, there is a tremendous and good work in the crypto space to have toolkits and library and adapt to also standard tool, but still, I think here it's much closer right away what people are used to and can use. I think there is also much less inherent scale bounds, kind of in particular I would raise the communication aspect if you have the wide area network, kind of, which is really a large limiting factor for many of the crypto protocols. There is of course now an essential difference in the trust model. I guess I would ask you here, I think there's no true answer, so it's a question of it, pick your poison. Of course in kind of this case you have to trust the manufacturer, you have to trust Intel, you have to trust the hardware security, some tamper resistance or of that, versus in the other case you have to trust crypto assumption. But even if you put it like that, I think it's actually not a black and white matter, because actually both of it's a matter of degree, because even for crypto we rely to some extent on hardware. Of course, their individual parties have the choice which one you trust, but in most cases it's the question, do you trust Intel or AMD? It's not that you have that much of a rich choice there either. On the other hand, of course, even if you have the hardware, there's a lot of security which relies again on crypto, kind of, so it's really not that black and white. So there's, of course, also a lot of challenges in that space. Kind of, there are two, I would say, is like the whole code security and the TCP size. I think we certainly reduced that drastically, but there's still kind of, it's a concern. Although that, but the bigger one is maybe the side channel part. But certainly for some of the single node aspect of it, as kind of, there's lots of promising techniques, and I think also Intel will in the future come up with some protection from a hardware side on things like control channels. There's of course also things like, which are kind of, as far as I know, not much is done kind of from a generic cases, like things like cache side channel, but they of course apply to the crypto MPC part also. There's also, of course, probably the biggest challenge if you go to the more distributed space in the TE. I think there's still a lot of room for improvement. Is kind of how to deal with side channels. If you have a distributed environment now, they interact with each other. There's all this network communication is, of course, some side channel aspects also. Yeah. I mean, of course, this is also not really mutually exclusive. You don't have to pick one or the other, because I mean, you could mix and match. Let's try. I think there, I guess, what has to be a bit, well, or kind of to do that better, you probably have to formalize some of that aspect. And universal composability or something like that is certainly an interesting aspect. There's some initial work I know which kind of looks at that, kind of what would be the right way to integrate SGX in that, but there's certainly more to be done. Yeah, okay. So let me just get to the end, and I'm just getting anyway out of time soon. So what did we do? I propose here, okay, that there are alternative approaches to do multi-party computation. You don't have to do everything crypto. You can do that also with the help of hardware. And I would argue, at least for certain problem in the genomic space, given just the size and the number of parties, I think it's certainly for probably for quite the near or not so near future, the more promising venue to get to kind of the scale of that. It's also more kind of easier to consume, certainly for non-experts. And for all of that hardware, MPC SGX seems a very promising foundation. So also there's maybe a little less to hardware MPC, but still around SGX, kind of there's a lot of, well, even to multi-party computation, there's a lot of exciting work, at least in the research and academia also going on. So I think it's an exciting area which will evolve and will bring more interesting things in the future. So certainly this hardware MPC also complements nicely with the privacy preservation technologies, something like PINK, which was mentioned earlier, or like kind of differential privacy frameworks, which inherently assume, okay, yeah, this single entity, you can run that now in this, okay, haven't done it, that runs PINK, but still it's kind of easier to deploy as such technologies onto an MPC framework. Still, we need a more systematic and generative integration. I think there's also, just from a usability aspect, I think a key part is also kind of that we work on fail-safe abstractions and aspects of it. And, well, I mentioned that earlier, this kind of public verifiable code properties. How can we prove, how can we convince somebody, just given a hash of a binary, that it has certain properties? That's still a big problem. And applies actually, as mentioned before, also to the privacy preserving function. So one big open question, kind of, besides technology questions I've mentioned, of course, is kind of what is the regulatory take of such an approach, or actually, I guess, in general, what is MPC? For that, in particular, as ultimately we want to talk about transnational kind of of settings. And unfortunately, there's still a lot of uncertainty there. There are some case studies, certainly in Europe, which looked how multi-party computation would fit in and kind of whether it would alleviate some of the requirements. The jury is still out where that goes, kind of, and well, the whole privacy aspect and big data analytics kind of is also a big open question. I guess some of that will also come later in the panel out to the surface. Anyway, so that leads me to the end. Only 3 minutes too late, too long. Anyway, okay.
I think it's thank you for the talk. I think it's very interesting. But there's one fundamental problem for this hardware-based security. And so I'm just wondering, what is you guys' adversary model? So what kind of capability you assume that attack to have? You know, just obviously there could be two types of adversary, right? You can consider operating system level adversary. And another adversary is is the administrator who can touch the system, who can for example monitor the memory bus, for example. So and for your design, so what kind of adversary you guys trying to defend against?
So I mean, certainly from a software perspective, it's not only defense against operating system applications, hypervisors, but also things like the BIOS, SMNs, graphic cards, device drivers, firmware, also on these things.
So essentially the administrator. And
certainly the software administrator also, I think where really SGX differs from, for example, PPM before. Okay. It protects now also against certain types of hardware attacks. Okay. Because like if you watch like the memory bus, you don't see any data. Kind of course you still can kind of destructively wipe the hardware and extract potentially some secrets. I mean, there's a limit how much you can protect there. I mean, that's also for smart cards where I guess most of we rely in some form or the other. Also, they also have some of this issue kind of destructively, or they also. Then of course the big elephant in the room is kind of side channel. Kind of that was not that well. It certainly was in the mind of the designer. It was kind of certainly not the first level of goal which was protected.
And fundamentally, the fundamental cost of side channel is sharing of resource. So if just in the enclave you want to use some resource, you want to ask the operating system to help you do something. If you have some shared resource, shared interaction with the operating system, side channel fundamentally is inevitable. And although the page-based side channel, you could come up with some way to defeat it, but there will be many other side channels.
I think ultimately, as you say, side channel will be there, but that's not a hardware security problem alone. I mean, that's true also for crypto. If you say even sharing, I mean, like some of the most powerful side channels you have is like electromagnetic emanation. And there you don't, you share the chip at some level, and they're very powerful against crypto also. So I mean, there are ultimately, of course, you can now improve on the algorithm, but certainly for human, certain things it's actually very hard. So it's, I mean, there's nothing absolute secure, but I think at least certainly the low-hanging fruits, I think, we certainly raise the bar.
So let's shift this to be a bit more pragmatic. When you spin up your enclave, you're allocating a certain amount of memory for processing, right? And when you reach the boundary of that environment, of the amount of memory that you've allocated to run a computation, what happens? So you have to offload information that's within the enclave out into the rest of the unsecured RAM. Like, do you encrypt it and push it offline? Do you?
I mean, in a way, it's like any object. I mean, this happens without enclaves also. Eventually, you run out of RAM. So if you have to decompose your application, you have to start to paging, and there is support for secure paging, although it's not very fast. It's also, I mean, if you right now get SGX from the market, it actually has a fairly small amount of RAM, but this will improve in the future. So certainly you will not be as bounded. I mean, eventually you will have to go and go to a distributed system. Kind of.
Well, I'm asking because on one of your slides it said privacy and big data. So I'm kind of like wondering, how does SGX play out in a big data scenario? I mean, like, are we talking about SGX nodes in a map-reduced environment?
I mean, you certainly will not do the distributed system, all of that in hardware. I think it's also a design goal. I think where SGX has succeeded, at least in my opinion, fairly well. It tries to be fairly minimal in what it offers, kind of as powerful with as minimal. I mean, if you look, for example, what TPM and the complexity of the TPM spec, it's very complex, but it actually it's not really some of the complexity, but you will need some trusted software at some level, kind of, that to get beyond the single machine.
So just play this out a little bit. We're talking about genomics, right? We're talking about terabytes, right? So what, like, how big is SGX going to support eventually in this space, like in a not scalable but at least efficient manner?
Well, okay, and if we're talking about things like paging, or let's assume now, okay, the memory, you get as much memory as you have, then certainly the crypto you need to page or encrypt and decrypt. I think now you have hardware assistant for that. That's probably not the big concern. Kind of, then, okay, if you go distributed, if you have now a runtime environment, and if you do something like Spark, or also what we did with Control Whittle or things like that, there will be some part of that which is in the untrusted space, so you don't care. That's more or less you decompose it. There will be some part which will do some network computation. Again, there's a crypto part of it, which is, but as long as you do standard crypto, hardware helps you. Of course, if you do just the standard one, then you get the side channels potential from the network traffic. So there it's, of course, the question how perfect privacy do you want to have. Kind of, so I would argue, but then also given these data sizes, you probably can sacrifice some privacy, because if you're sending gigabytes and terabytes data on a network, doing all the statistical, it's maybe not the lowest hanging fruit to break some of the system. I think ultimately it's probably more the software part, or even the end user. I mean, yeah, okay, no, but I think ultimately it's the software probably more the end users, I guess, more like administrators, which maybe somebody gets now some result and or authorizes a policy which he shouldn't have, so the user will also be there. So I don't. I mean, it's kind of early, so it's hard to say how big scalable you can do, but I think it clearly has lower hurdles to cross. There are lower fundamental hurdles to cross than if you want to do it purely with crypto.
Okay, it's a research opportunity.
As you mentioned, we need to trust the Intel calculation, Intel calculation service. Is that possible to trust the service provider and Google to provide such a calculation?
Well, okay, I guess there are actually two different questions. I mean, ultimately, you have to trust Intel, because Intel builds the hardware. And there's a lot of proprietary secrets there, how SGX is implemented. You have to trust them that this analysis, and there's a lot of formal analysis also involved in making sure that it. Then regarding the attestation service, well, and it also has to be bootstrapped somewhere with Intel, because Intel manufactures the chips, so somewhere the root trust has to be with Intel. Now, this attestation service, if you talk about that, is currently also run by Intel itself, so that might actually change, but still at the core, like something which identifies as a piece of hardware. I think there's no way around that you can trust the hardware manufacturer, but yeah. As I said, I think you will trust the hardware manufacturer at some level anyway.
So when, just to follow up the question, yes, when you declare your memory enclaves, the user level, is the address space a virtual address space that you could remap that into virtual memory or disk, some space or so on, or?
So it is, well, I mean, you map it in virtual memory space, but the hardware under the cover prevents the operating system to map that into our space, which it then can access. So kind of it's.
In the case that your process is swapped out.
Well, actually, right now you cannot that easily. I mean, to swap out kind of you. Well, okay. I mean, I left out some details. Kind of there is like this EPC enclave page cache model, and that's really hard. Well, kind of a completely separate part of your physical address space, which is kind of protected, and the operating system can swap that out only using a special paging operation. So the operating system has no access to that.
Right, but if it is swapped out, when you put
But then it's encrypted, kind of.
then it's encrypted in this.
And encrypted uniquely for that particular enclave. So, and again, with this code identity, this particular kind of code and configuration.
And the keys for the encryption are held where?
That's in, I mean, it's bootstrapped with some secrets in the hardware. So there is some master secret somewhere.
So it's a symmetric encryption.
Yeah, because I mean, well, I mean, only this machine can encrypt it, so there's no reason why you would want to use the expense of a public encryption. I mean, at the core, there is a single, well, actually, there are two keys, really, but, and then the different keys derived from that. Actually, in some cases, even some public keys. But for this case, it's also not encrypted.
And how close or not so close are you to solve this side channel problem?
Well, as somebody well said, I think ultimately we will never solve it. Kind of it depends now which side channel and to what degree, kind of. So I mean, as I mentioned, like the page, this controlled side channel, that's certainly kind of the most kind of effective one. And there are now a number of software proposals. Some of them are fairly generic and fairly effective. I mean, they have overhead, but I think for some of these cases, an overhead of even 50%, something like that, is acceptable. I would argue, at least.
Yeah, we can save the question.
Yeah,
yeah, we can save the question for the panel discussion. Dr. Spooner will be a panelist in the next session, so we can still ask those questions. So we have a next session first.
Okay. 3 tracks. Still only got through one of the tracks. So to prevent this from getting onto track 2, we're going to have a little bit of a side channel, for lack of a better term. So we put together a little bit of a panel that we've tentatively entitled How Ethics, Genome, and Privacy Scientists Meet Up. All right. So what exactly is this? There's 4 people here. You're first. So Mike Snyder, Knox Carey, Stephanie Dyke, JP Hubal, all coming at this from different perspectives. But these are people who are working at the interface of various socio-technical situations. I posed several questions to these panelists to try and prime the pump to get us all started and on the same page. So here's where I've asked them to address. Who are you? What are you working on? And I want this in a very general sense, okay? Don't get too technical. And how have you gone about or planned to go about building bridges across your disciplines? Okay? And what do you see as the major challenge moving forward to accomplish this goal? That's very generic, right? So you've given us a lot to talk about so far. So you're more than welcome to take as much or as little time. No more than 7 to 8 minutes, because I want to leave enough time for discussion if we can have some. Okay. Oh yeah.
Keep clicking.
Well, I guess most of the background you heard already in my introduction before. Kind of, I'm in industrial research since quite a while. I guess it's now almost 20 years, and I've been there all over the map. But from theory to practice, crypto to even up to penetration testing and stuff like that. And it's only very recently kind of I got now into this space, kind of genomics and the hardware multiparty computation. And kind of there, coming to the kind of the interdisciplinary aspect, I think I'm working in some collaboration with the Broad Institute of the MIT and Harvard Broad Institute. Correctly, kind of, and with the kind of trying to move hardware APC to the real world. And there's certainly kind of interesting aspects of real world means, kind of like some of the, I mean, we're working there in this kind of around GATK and Chromel and stuff like that, and the real world means that this is heavily evolving and faces huge efficiency changes even before you get into security. So that makes it kind of interesting. There's of course also lots of regulatory hurdles we have to deal with, like internally about indemnification of code and externally of privacy. So kind of there's some of these exposures. So the focus in that work is more on the system and the scale aspect. But we also try to look at some of the more end user requirements and with studies kind of for the stakeholders from an operational aspect, but also legal, business, and in particular kind of the end user side who would deploy such systems. So that's kind of the background. Now from the more challenges, coming back to the title or maybe the last question, and as you noticed before, kind of I'm relatively new to that field, so maybe my thoughts kind of it maybe shows, but I think there are kind of three areas of things I would raise there. I think in general, kind of just privacy in the age of big data, I think is a big problem, because kind of the old, at least the regulatory model of PII, where it's well-defined over credit card or a name, or that's bad and everything is good, really doesn't apply anymore. It's too simple. But this is not genomic specific, I think. I mean, it's true for many others. Think of like IoT. I mean, just the implication of having a smart grid with very fine-grained measurements on what you can infer by these kind of information is actually pretty interesting. I think the problem there we have is kind of the threats. There's really fundamentally different perceptions of these threats. I mean, there's some people who look at it and then there's some nice media kind of articles say, which makes you, the sky is falling, everything kind of be revealed about you, and you can even throw up your hands and not. And then on the other hand, there's probably a much larger proportion of people have no clue what they're exposing themselves with. So I think in that sense, having some real threat assessment and public education and getting a grasp on what is good or bad, what is acceptable loss or not, it is a big issue, which brings now kind of to the ethics part, and I guess that's maybe then more genomic specific, is that, well, privacy is a strong requirement, but there's also, if it's contradicting in some cases, also like the greater good. Doing these studies, we benefit all of us, so there is probably in some cases we actually should sacrifice some privacy, but whatever is the right way is not clear. I guess another part in that dimension is also kind of given the user control and consent is only a desirable property, but also given what I said before, that people don't understand the things, and maybe you also don't have that good tools, can we even realistically enable them to make educated decisions? Isn't that even a fair choice? Kind of, I think to some extent sometimes also contain on the user. It's like with security policies, also it's like, oh, a user could have changed policies, but in most cases they actually cannot realistically do. So I think the end user is really here a big problem, and the challenge there is kind of to find, well, on one hand, intrusive and non-intrusive, and in particular fail-safe abstraction. We should make the life end user here now in the more generic sense, it should be easy for non-experts for how to define policies, how to use tools. And I think a challenge I see there for us as technologists is often that we want to be perfect. Kind of, we want to make this ultimately, we want to touch all corner cases, and we come up things with our complex, they're comprehensive, but they're complex, and then ultimately they're often ignored because they're too complex. So I think it's often good to be simple, even if we sacrifice security, better something which is used than is insecure than nothing. And I think also, let me
Perfect. All right, thank you. So let's hold off on questions until everybody has presented themselves. So I've asked Knox to go second. We'll eventually set up in this area, but for now we'll just introduce ourselves. All right. Get that first. I get that. They did that second. All right. Perfect.
Hi everyone. So my name is Knox Gary. I work for a company. I work for a company called Intertrust, and G-Cloud is the name of my project. It's been going on for about 3 years now. And this year, next year I'm going to have revenue expectations. So we're kind of in that transition space between prototyping and building out a system, designing a system, and people expecting me to make money. This is my day job. The goal of our system is to enable people to do science without worrying about the kind of stuff you guys are talking about in this room. So you can look at a company like G-Cloud as a customer, potentially, of the output from this type of activity. Most people don't want to worry about these kinds of things, and so I want to make that really easy for them. So that's my day job. Now switching to the interesting stuff. I'm also a member, as a hobby, of this organization called the Global Alliance for Genomics and Health. And this is a really interesting standards organization. It's an international organization. The idea is to create standards to facilitate data sharing. So everybody who shows up at this meeting is there to somehow help data be shared, and many times across international boundaries, but be shared as broadly as possible. And a big aspect of what we do there is to sort of understand, as we share data, to understand how we can respect the rights of research subjects and patients, including the rights to privacy, and Stephanie, I think, will probably talk a lot about that. I wanted to say, though, that privacy, if we solve this privacy problem, I believe it can unlock a lot more data sharing. So this is my hypothesis. Privacy issues tend to be create a chilling effect for data sharing. So people say, well, I can't share this because I don't know what's going to happen to it over there. Or, what if they do X, Y, Z with my data? What if they publish something based on this data that I shared with them? So it ends up being, privacy issues end up being an excuse for not sharing data. So I posit that if we want to create more data sharing, we need to definitively address this problem. So I'm a member of the security working group at this organization. We're in with the Bustamante attack, we're kind of wading into the privacy area. I think you'll see a lot more of that. I would invite everybody in the room to participate in this organization if possible, because here you're going to see what people are doing on the front lines. You're going to see people who have data sets distributed across multiple countries, where sometimes the data can't leave this country, sometimes it can, all sorts of configurations, but you're going to see what's actually important to the users. And so this would be a great source of requirements for this community, I think. So we mentioned the Beacon project. This project started a few years ago as, again, a way to just sort of test, are people willing to share data even at a very simple level? The assertion at the time, I think it was Steve Sherry maybe from the NIH who first proposed this idea. When they first proposed it, I was sitting in the room, and the assertion was, it's not much, there's really nothing important there. Nobody's going to infer anything private from this simple question, right? I mean, tens of thousands of people in the data set. And my spidey sense went off immediately, and I said, no, that's not going to work. And lo and behold, a couple of years later, we have the Bustamante and Singapore attack that starts to poke at this abstraction. Anyway, the Beacon project itself is very successful. There are about 50 live beacons in the Beacon network. There are beacons on every continent except Antarctica. So this is really a worldwide a worldwide effort. And again, repeated queries leak information as we've shown and allow for re-identification. So this, when this attack sort of came across the wire, I started to talk to a few folks, including Heidi Sophia from NHGRI, about what can we do about this, and she kindly referred me to this community here. And so some of us sort of got together and started talking about these things, and looked at different aspects of this problem. I think it's stimulated a lot of interesting research, and I'm really excited about the stuff that's happened here today. I think this will continue. I'd like to see this graduate into a more consistent effort around data privacy for the GF4GH. So I'd like to see the creation of a privacy working group sort of parallel to security. In security, we tend to deal with things like authentication and authorization, more, I'd say, workaday security problems. There's some really interesting questions on the privacy side that are relatively unaddressed. I guess my primary interest, personally, although I'm very interested in homomorphic encryption and SMC and the like, I'm really interested in this concept of quantifying information loss and quantifying information leakage, because no matter how well you protect the abstractions, at the end of the day, you have to answer a question. And that question contains, if it's a useful question, it contains information about the inputs. And so looking at the mutual information, actually this is technically how I like to think about it, looking at the mutual information between the inputs and the results of a particular computation, I think that's a really rich and fascinating set of questions as we generalize these beacon queries. Collusion and side channels, a big issue that we tend to sweep under the rug, but those need to be addressed directly. I think on the ethics side, I would mirror what the previous speaker said, that the consent and how we allow patients and subjects to control the use of their information in a way that's intelligible to them and not just an overwhelming sort of alien spaceship full of controls. How do we do that effectively? I think that's a huge challenge. That's, again, one that's being addressed in the GA for GH. Okay? So.
Thanks. Okay. I wasn't going to say it, but I guess I'm going to say it. There is a privacy working group, because I'm part of the privacy working group.
As a part of the regulatory and ethics.
Correct.
Okay.
But it's not explicitly called privacy.
I think we should change that.
That's fine.
I think we should change
And let's start the bar then.
Yes.
All right. We're switching. This is called switching between PowerPoint and Mac users. You can be a PowerPoint user on Mac. All right.
Thank you so much. Does it still work?
It should start.
Hi, okay, thanks so much for the opportunity to be here today. It's my first iDASH meeting, so I've learned a lot and really excited to become more familiar with the overall structure of this competition and the efforts of all of you. You might not have ever met me. So I started out my career as a biochemist, and then I trained in science communication as a science journalist and in communication theory and the sociology and philosophy of science, which led me to work as a researcher for National Bioethics Council when I was starting a career in science policy. So I worked on GM crops, stem cell research, and some projects on the control of pandemics and the development of biometrics technology. Before moving to genomics-specific science policy and research ethics, I worked at the Sanger Institute as their policy advisor and at the Francis Crick Institute. For the last couple of years, I've been at McGill's Center of Genomics and Policy in an academic position working on ethics and policy research, so bringing a lot of the professional experience I had and also the training from earlier on in different disciplines to my research. So I just want to quickly mention a couple of projects that I'm focusing on right now with the Global Alliance for Genomics and Health, which Knox has already introduced. So these are a couple of projects that are aimed at addressing some of the privacy challenges of international data sharing. So the first is looking at models for data access. So the very established, open access model and controlled access, which is used a lot by the genomics research community. And we're trying to develop an improved, streamlined data access model, which we're calling registered access. And this is the model here. This is not working anymore, is it? Yes, it is, sorry. So I won't go into the detail, but there are two main differences with controlled access. The first is that application and approval would not be on a per project basis, so it wouldn't be access is provided, for a specific research use. And we think this will be very beneficial, especially for access to many data sets and for research generally. So access will be based on the roles of users, and within those roles they'll be entitled to be accessing all kinds of data shared in this way for all of the functions that they carry out within that role, so researchers or clinical care professionals. But we're also thinking about other potential groups of users. And the second big difference compared with controlled access, which we think will save a lot of time and really streamline and improve even accountability and so on, is that it will not be based on a contract between host organizations and data providers. The access will be based on a direct declaration, which we're calling an attestation on the part of the registered user, agreeing to things such as what is currently the norm in controlled access, so agreeing to abide by ethics conditions, etc. And the second project I just want to quickly mention is working on a method to assign levels of data sensitivity to health-related data in what I hope will be an ethically and also legally coherent way. And this is leading us to develop a data sharing privacy test, which will serve as a kind of a privacy impact assessment for data. So we'll have, on one hand, hopefully, we're going to be having some improved data access mechanisms, but we'll also have a better way to decide which data need to be shared with more or less protections. So, for example, which data can be open and which would need to be shared through registered access or controlled access. And the biggest challenges, I think, are really what has come up already, integrating all of the sometimes rather sophisticated solutions that are being developed in all of our different disciplines, so that we can have efficient and multifaceted solutions that work internationally to the privacy challenges. And secondly, I'd say the educational consequences of this. So how are we going to reach and teach other experts, but also members of the public, to use these solutions and some of the tools that will come from it? I know certainly for the data sharing privacy test, for example, a big part of it allowing consistent assignment of data is that many people should be able to use it very easily. So I think that's all I have. Look forward to the discussion.
One more? Yes, if you could switch back, that would be wonderful. JP?
Yes.
Come on down.
I'm here.
Or
All right. Good afternoon. Right. So just a few slides. So this is my slogan. So the ultimate frontier for privacy and security, digital medicine. We're working on this topic with many people when mentioned here at the bottom, and many other who I'm going to mention after. So the research efforts to introduce what the approach we take in my own group, because one of the questions was who you are or what you are trying to achieve. So our goal is to continue to lay the foundations and developing the tools to protect privacy. As such, we are problem-driven as opposed to a discipline-driven group. Right? And this requires to deal with many topics: information security, applied crypto, networking, statistics, machine learning, genomics, name it, right? And many collaborators, which of course leads to a risk of dispersion. So to avoid dispersion, we focus on 2 or 3 research topics for several years each in order to maximize impact, and then we move on. So it won't stay too long on a given topic. We try to publish at top venues, so conferences and journals, and we try to also, in spite of being in academia, we try to have a connection with an impact on the real world, right? So my group is a medium-sized group with 2 postdocs and 7 PhD students plus myself, plus interns and visitors and so on. I've worked with my collaborators a lot on location privacy over the last 10 years or so. And here the question is, people leave traces with smartphones, etc. And these traces leave a lot of information. And information can be very sensitive. And so what do we do about that? So we have tons of papers on this. And if you want to know more about this, here is the URL. Now, about coming closer to this workshop, the avalanche of digital medicine is coming, as we all know. So this is unavoidable. And generic privacy and security is a grand challenge for mankind for reasons you know, right? The size of the data, the duration, the amount of time for which the data has to be protected, the noisy data, the correlations, the fact that we have to go with several semi-trusted stakeholders such as sequencing facilities, the hospitals, and so on, right? And the diversity of applications, healthcare, medical research, forensics, and ancestry. Now, we collaborate with many people, so the GA4GA that has been mentioned by several speakers before, in the US with a number of institutions, mainly at universities, and in Europe, yes, Europe does exist, Bilkent University, which is the borderline between actually Europe and Asia, Southern University, and UCL. But I think we are probably one of the very, very few groups in Europe that has, let's say, established connections with let's say, CS groups and with established connection with the biomed researchers. What we do, and more locally in Lausanne, so Lausanne, by the way, is in Switzerland. Switzerland is in Europe. Yeah. Just in case. Sometimes we believe Lausanne to be in France, right? It's a big mistake. Okay, so we work with the Swiss HIV cohort studies. We have produced here solutions to protect essentially it's a data, it's a cohort that is managed by 7 hospitals throughout Switzerland. And so this is highly sensitive data. So we have deployed a prototype that is based on homomorphic encryption to see how MDs can, how can these kind of solutions can be introduced in real settings. We're also working with the main hospital in Lausanne on the protection of a biobank, so a collection of blood sample sequencing is going on there, and we are working on the appropriate protection of this. And then we're working with a company called Sophia Genetics. I'll come to this in a minute. Papers we try to publish in both CS venues and biomed journals, which is a very disturbing experience because the principles or let's say the expectations are very different. So we have a paper in Genome Research that is coming next month on a so-called solution called CCRAM to do secure, let's say to have security, compression, encryption, and selective retrieval on the equivalent of BAM file, so for raw genome data. We also paper in genetics in medicine that came out earlier this year. You probably know it. And then we had papers in more the CS side. So GenoQuad is an attempt to find a solution that would make it possible to resist the unavoidable weakening in the long time of cryptography. And then a somewhat older paper, qualification of kin genomic privacy, to see what the implications are when some people start revealing their genomes and their relatives are not actually happy about it. We have a website, it's a community website, genomeprivacy.org. This is maintained by Jean-Louis and by Chichong, who is in the room, to publish this within my group. And this provides essentially tons of resources to the community, including all the papers that have already been published on the topic of genome privacy in general, by everywhere in the world. And there are something like 160 or 170 papers so far. You find also all the research groups and companies involved. If you see that your name is missing, please let us know. We will be happy to complete this. And by the way, there is also a workshop, GenoPride. Who is coming tomorrow to GenoPride? Well, surprisingly, some hands are not raised. So what's wrong with you guys? So this is going to take place in Chicago, a few blocks from here at the Hilton, starting at what, 8:30. So please don't miss that important event.
genome privacy. Okay, Sophia Genetics is a company where we have been working with, founded in 2011, is almost Californian growth, 120 employees nowadays, with operations in 35 countries. Yes, success stories can happen also on the other side of the pond. The main product what they provide is secure storage, visualization, and integration of genomic data. What we've done with them is what I mentioned before, the so-called CCRAM solution to protect bound files. And we're also working on privacy-conscious aggregation of medical data, probably based on, surprise, surprise, Internet's GX technology. Thank you, Michael, for controlling us. Okay, very good. And you can find more on their website. I'm not a co-founder, by the way, but I'd like to collaborate with them. Okay, the three of collaborating with biomed researchers based on 5 years of collaboration. So the biomed researchers, from the CS point of view, they understand statistics. They have a hard time understanding crypto, just because of different preparation. They publish in ways that are very strange to us and vice versa, in terms of paper structure and publishing game, etc. And they have, my impression that they hardly understand the papers of our own community. So it's actually, there's a kind of asymmetric situation. And they're happy with MS Word and don't use LaTeX for some reason. Okay, conclusion, so medicine is getting massively digitized because of genome sequencing and editing, EHR and so on, Watson, DeepMind, blah, 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 telemonitoring, emergence of P4 medicine, so precision, personalized, predictive, participatory medicine, the PMI initiative in the US and equivalent efforts elsewhere. So medical confidentiality is in jeopardy, I think. And this is the battle we cannot lose. Of all the battles that the privacy community has to face, this is the most crucial one because these are the data that are the most sensitive. Right? And the security privacy community can bring a lot, but this requires to fully understand the complex requirements of medicine and to establish more connection with the biomedical community and invent or adapt software/hardware tools. And you find more on our own stuff at this website. I'm done. Thanks.
All right, so if you're on this panel, come back up, drag a chair with you, sit up here, there's no table to sit behind, I don't want to use this, it's too much of the environment hidden by that wall. So, we've assembled them all. This is audience participation time. That's the wonderful thing about a panel. So I will open the floor to any questions that the audience may have. These can be hot burning issues. They can be things that have been addressed by the panel or things that have not been addressed by the panel. I will bring you the microphone. You just have to raise your hand. Oh, Dan. I would ask you to introduce yourself also before you issue your inquiry.
Thanks, Brad. I'm Dan. I'm from Cybernetica. We do privacy stuff these days. We used to be focused on secure multi-party computing, but we've branched out due to customers coming to us with problems that were not secure multi-party shaped. My question was about how much in your practical work are you fighting against customers who are just saying, but we'll just ask for blanket consent?
This is going to be fun.
Thank you.
Anybody want to start?
Yeah, consent is something that we hear again and again mentioned by the people we deal with in the hospitals. And there's a tremendous temptation to say, okay, let's go for blanket consent because it is much easier. So kind of a general agreement. The person who provides the samples is going to be sequenced or even non-genomic data in general. And so these data are going to be used for various research purposes. So there is high reluctance so far to introduce something that would be a kind of dynamic or selective consent, because the concern is that the administrative load that would be involved in doing so would be simply too high. Also considering the amount of time over which this can span, we're talking about not just months, it can be over decades, right? So it's a very tricky problem, And even nowadays, just managing the static concept, consent, which is essentially pushing around the PDF files with the signatures of is already complicated from what I see. And so there is also not much awareness, you have time to change that, about what would be doable with modern computing, because one can go way beyond that, but it's, there is a routine, there are procedures that are well established and that work to some extent, and so I think there is some inertia to be met, to be fought. Yeah.
One thing I can mention from work with the Global Alliance is we're trying to develop a list of standard consent classes or groups that have that account for the current consent provisions that exist in the genomics community. So with the data sets that have been archived already, and building. So this will simplify a lot of the transferring the information about consent permissions and restrictions, and we hope that can be an approach that can help encourage the inclusion and sharing of data sets where there are such restrictions. And going forward, we'd like to think already, according to today's standards and regulatory standards, and then also social expectations, etc., what such groups might look like, and whether it would be potentially a shorter list of the usual consent information that can be represented this way, and also thinking about what an ideal set of we're calling them consent codes might be. There's quite a bit of work to be able to support this that we're all also working on with the Regulatory and Ethics Working Group of the Global Alliance. Broader forms of consent need a lot of supporting structures in place for that to happen, and definitely there are a lot of people who are calling for that. But currently we are trying to focus on at least making consent information more shareable so that it doesn't hinder data integration as much.
I'd just like to add that I think that the reason people seek really broad consents is the researcher doesn't want anything to get in their way of answering their question, and it's very cumbersome to go back to the subjects and ask them if it's okay. It used to be. It isn't anymore. And so I personally am very frustrated with the idea that we just ask for this broad consent, because we can do a lot better. I mean, anybody who can go on Facebook can consent to a new research purpose. And there's research that shows that, one of the predominant attitudes of people who participate in research is that, I'm willing to share my data for lots of reasons. I just want to know what's happening. I want to know who's touching my data. I want to know what's happening. I won't say no. I want the option to say no, but most likely I won't. And that, I think we can do a lot better on this question than we currently do.
Well, so you just mentioned something that is fundamentally related to provenance. So you want provenance of access to your data. So have you guys considered blockchain at all?
This is something that I think a lot of people are looking at right now, including us. I don't have anything to say about it at the moment. I don't know if JP, do you want to say something?
But the thing is that the topic is so popular nowadays that one has to be careful, right? Because people are essentially trying to solve the problems of the world with the blockchains. And there's been a lot of talks. Pardon?
Just a problem of provenance.
Or just problems, but there can be also other ones. And there's currently, indeed, I mean, as Knox was referring to, there's been currently, even in the, let's say, community that deals with the protection of health data, a lot of thoughts on how to do this, etc. It's difficult to find really in that field, I mean, in my opinion, an application that would be really, that would show that blockchains are strikingly superior to things that are maybe existing and are maybe a bit easier or more mainstream. But you may have some examples of your own mind.
I've been working quite a lot with it, so that's why.
Yeah, but I mean, in the case of protection of health-related data.
Not necessarily health, but
right.
in terms of keeping provenance
yeah, right.
of the transaction, because what you want is if someone touched your data, what did they do with it?
So traceability and accountability also in terms of, yeah, absolutely, yeah, that indeed could be an application area. Yeah. But there are also other solutions to do that, right? It's not the only one, right?
No, not the only one, but
well, in particular, some which are much cheaper and don't spend as much energy.
Yeah.
I think it's also, like, at least in the original blockchain, I mean, it works only because you have a certain incentive structure.
Blockchain's not Bitcoin, right? So once you have the ledgers already generated.
Well, okay, if you see it as a consensus problem, or you can see like notarization, which actually goes back to the 90s with Haber's Sonetta and work like that, then I'm also agree. I think I liked what you said about the registered consent. I think accountability is an important part which can help a lot with relatively little, well, I mean, it's not so costly, kind of, but you know.
Sorry, I just wanted to add one more thing on the blockchain question. I think it boils down to what the trust architecture is. You know, it's useful in certain trust architectures. It's not obvious to me that those trust architectures necessarily apply to the problems that we need to solve immediately, I guess.
No, it's more to do with the immutability of the ledger. So if you,
right,
that is very okay.
So I have a question. We have been seeing the vulnerability of those public data sharing services such as Beacon, and the attack today may be improved tomorrow, so current solution may not prevent a new attack. But we also want to enable citizen scientists public access of these kind of data. So what do you think? What kind of protection should we put to those kind of services? Should we restrict them, or should we provide access as of today?
Let's caveat this question.
I think your question also is asking, in one of your slides, somebody used the term bona fide researcher. What's your definition of a bona fide researcher in this context? In the context of citizen science and trying to make data much more publicly available, like the European Medicines Agency now is trying to do.
Okay. Yeah, so I quickly want to say that for the, for any kinds of restrictions to Beacon, etc., I really think we're thinking about the future phases, so where we will be sharing a lot more than just the existence of an allele in data sets that are participating in the network. So, we would like to make health information available alongside that, etc., and that's where a combination of, I think, the data sensitivity assessment method that I was presenting will help us assign some of that health information, like HIV status, to potentially access controls like registered access, but we do still need to see. It's incredibly useful to have a better understanding of the quantification of the risks of their identification, as well as the solutions, which I think we'll be able to use in many contexts, but especially going forward. Beacon wants, the plan is for that to really grow and to be sharing a lot of information in that way, and we'll keep pushing and adding mitigation and layers of protection to ultimately share very large amounts of information for practical uses, but in a protected way. Bona fide researcher for registered access, we are still right now, and it would be great to have you involved, Brad, if you have some time in these discussions. It's a really good, registered access is probably the project where personally I've made the most progress in having an interdisciplinary sort of expert discussion to try to have a solution that really brings in the security and technical experts along with the ethical legal people, and it's not straightforward. Right now there's a lot of debate about so how we really define those categories, how they can be checked realistically, both programmatically as well as manually, and how they are authorized to have enough, a strong enough level of identity proofing, as well as authorization that the lawyers are happy to sign off on. So generally speaking, though, the citizen scientists, we are thinking about, I'm thinking about them as having to be in our third class of registered users, which will be members of the public generally. So citizen scientists would be, something like journalists, groups of patients. I don't think it makes sense, at least the way we're looking at it now, to have them in the same group as professional scientists. So they would have much less to attest to commit to. And I think, for a lot of data, we are just getting to a place where this access is replacing freedom of information requests in many situations. So for example, the European Medicines Agency access to clinical trial data, that is publicly accessible data. It's not data that's being shared within expert communities. There are massive challenges there to set something up which gives people enough confidence to be sharing the research data. That does present some risk publicly with members of the public who are not going to be necessarily trained, and citizen scientists aren't necessarily trained, or accepting that they can provide, can do interesting things with the data, but that they might come from very different backgrounds, and it would be great to have you involved in those discussions too, and hopefully in the next few months, for at least the professional scientist groups, Bonafide will be set up.
Just chopping that video, but Lucilla wants to get a word in.
Well, I'd like to think about this in a little bit of a different way. We worry about citizen scientists out there potentially getting access to data from our data sets as inputs to their research. So they're accessing data that they're going to feed into their research that they're running, wherever they happen to be, and they're going to come up with some conclusion. I'd like to see us turn that question around, and let's look at the outputs of their query. So if I had access to, if I had a virtual machine, for example, that could run their query directly sitting there with the data, it can interact with the data however it likes, completely freely. We don't look at what's returned until we see the output of that computation. So if they send a query that involves a single individual that's highly identifying, that's a certain level of danger. If they send a query that involves tens of thousands of individuals, and it's much, much harder to do a re-identification based on that output, that's much safer. You can make that evaluation before you return the answer, because no one's privacy is violated until you print an answer. So I'd like to see us, and this is why in my introduction I said I think it's very important for us to understand how to quantify the information leakage of a general purpose computation. So I'd like to see us move more in that direction, so controlling the results as opposed to the inputs.
I see the point why you want to go toward quantifying, but I think it's also potentially a risky strategy, because not all information is equal. It's also kind of, usually you rely on assumption, you rely on these kind of things, and then maybe models. And so you might actually have a very imprecise data. So I think at the very least we would have to capture the certainty or the uncertainty you have, because I mean, certainly we have seen this week kind of some effect where numbers can be horribly wrong, and unfortunately.
So can I ask a question? And Brad, I need you there because I need an odd number of answers. So here's the situation. Let's say I'm a millionaire and I can pay 5 consultants to let me know whether I should share my genome and my electronic health records for science. And the thing is, you can only answer yes or no. You cannot go in between, and then I can ask a follow-up question, but you cannot ask a follow-up.
Can we make this a more realistic question? Ask us about babies. Do you want us to give up the genomes of our babies? It's a real situation at Harvard right now.
So ask for you and ask for your babies. So
just
say yes or no. Okay. So
well,
just the baby.
Want to be us or our baby?
Well, the reason I'm a millionaire and there are people there claiming to be my babies, right? It's a terrible situation.
Okay, so this is you giving up your genome.
Yes, yeah, and I have 5 people, and you're the experts, you know the risks more than anyone else, and I want the yes or no.
Okay, you start.
You can ask any questions.
There's no such thing as maybe, depends.
You don't have to say yes or no. You just have to put your thumb up or thumb down. Because
Yeah.
that'll work.
Yeah. Okay, thumbs up or thumbs. No, there's no such thing. Okay, you have to go. God, my answer.
Good.
Okay, I won't even follow up
Any other
on why,
questions?
because it's self-evident here. Okay, got it. Depressing.
Well, but
Why
so
just one little caveat, because this is exactly is what's happening up at Harvard right now with Bob Green's project on baby-seq. Almost nobody is allowing for whole genome sequencing to be run on their babies and having the data be given to them and be used for research purposes. Nobody's taking it.
It's actually 7%.
7%. Margin of error of 8%. Sounds like the polls. All right.
But I mean, this is consistent with what Knox was saying before, that if the question is, binary, right, all or nothing, etc., without context, without explanation, people would say, then in that case, just no. But if there is explanation, if the purpose is developed, right, and if some guarantees are provided, then it's a different question, right? So I like very much the exercise, and I like you. We all know you are a millionaire anyhow, but I like the fact that you said okay, you have to just provide one bit back, which is yes or no. Right?
I have no time to discuss.
Yeah. No, that's fine. But in that case, one should one should expect a negative response. That's, I think, unavoidable. That in a way is unavoidable because the level of risk that is involved is too high and is very difficult to apprehend.
Play this out.
Yep.
So we all went thumbs down.
Yep.
Maybe there was some leader follower issues going on here, but we all put thumbs down. You say because there's uncertain risk, right?
Yeah, because there is no context. Context.
Right. So for all of you, so context is important.
Yeah.
Absolutely. Until you tell me numerically, quantitatively, what are my risks, and you can tell me what the risks to my children are, I don't want to answer the question.
I mean, risk management depends on benefits also. It's a trade-off.
Yeah.
So it's like a secure system. Do you want to tell me it's a secure system? Well, probably the way it calls it is secure. But it's the context which makes it the real question.
Not that I expected a split vote.
But you got even stronger.
Are there other burning questions? Because if not, I'll pose one other question to the panel. So this notion of risk, it has come up again and again and again. You talked about SGX, and you talked about how you shift where the risks actually are. You make decisions on where you allocate the risks. JP, you guys have certain types of risks that you deem to be acceptable, certain things that you don't deem to be acceptable. We've seen examples where risk gets pushed onto the legal requirements and the contracts. And sorry, Knox, I don't know where you guys have your risk. But
my customers have risk.
Okay,
right?
wonderful.
I have to be responsive to their assessment.
Okay, so risk, utility, many different types of utilities in the system. How do you go about making a determination of what's the right balance? Is this a technologist's job? Is this something that you have to do stakeholder engagement? Do you have to do participatory design shops? How many? How many use cases do you see here for genomic data, and at what point do you stop and just say, we know what we need to know? Now I'm going to go cry in a corner for asking that question.
Well, I think ultimately it's the stakeholder who has to make the decisions. I think as a technologist, essentially your role is to help them. You have to be as straightforward with the risk you see in whatever technology you provide them, so you can guide them, but you definitely cannot make the decision for them. Yeah.
I think you have to be careful there, because I think they are looking for you to make the decision for them. I hear this time and time again, where people say, they're not the experts. You are the expert on the technology. They don't understand the technology, but you are, and so help them. That's, I don't know, I think it's passing the buck if you say that.
This is what I'm observing, well, say, more in the Swiss and South European context, is there is still a problem of disconnect between the people who are more legal scholars and don't understand much of the technology and are not necessarily highly motivated to learn more about it, and then the technologists who say, ah, well, here are you can do this or that, or there are pros and cons for each of them. Nothing is black or white. So essentially, they depict a situation that is relatively difficult to grasp, and then there is the ethics people and the politicians and the hospitals. So it's a very complicated zoo. And in addition to this, what makes the problem even more challenging, and this is something that has not been addressed, I think, enough today, is that we have in front of us decades of uncertainty and instability in this area, I think, because it's going to keep evolving extremely fast in terms of what medicine is able and willing to do, what technology is able to do in order to protect the data, what attackers are able to do. So the landscape in 2017, 2018, 2025, 2030 will keep changing, and we will have to keep adapting the tools, both on the side of the legislation and on the technology. Right? And we are not, no one in this room probably will know a world where we reach a kind of a plateau. We say, well, after all, things don't move too fast anymore, and we can cement a very, very precise legislation, and we have the appropriate tools, and the GFOGH has issued all the recommendations, and the work is done, and everyone can go home and enjoy an extremely long life thanks to precision medicine. This is not going to happen in the foreseeable future, which means that we need to accept the idea that the decisions we are making now in 2016, when we look back 4 years from now, we say, well, this was wrong, we have to modify because the landscape has changed, etc., etc. And which of course contradicts the fact that genomic data has the long-lasting values that we have mentioned before, and in a way it leads us to a slightly frustrating situation. So it's, voilà, and we'll have to live with it. That's it.
So I'd say as an ethicist, and for example for the demonstration projects of the Global Alliance for Genomics and Health, these projects were really, these are cutting edge and pushing the bounds of what has been done normally. But even though I take a rather conservative approach actually to a lot of the ethical issues, there is so much that can be achieved while having a very conservative position on the participant protection side of things. That I've heard things like this is radical ethics. It's not. It's just there's so much that can be moved within a very protective ethical framework. It's just the reason a lot of data sharing has not taken place has to do with much more than just ethics. And the second point is the balancing issue is a very, very challenging one. I collaborate with a lot of legal scholars because the law is a very good place to look if you want to see a very generally very accurate reflection of a social consensus, so a balancing that has taken place in the debate and the approval of those laws. So, for example, in the areas of privacy, but also discrimination, and a lot of the areas that we're thinking about. So, for that, and because there's a huge amount of depth to the philosophy that underpins a lot of the values that are put in contest sometimes when they're being discussed, or we're looking at one aspect in particular. So the legal frameworks, and really, there are international declarations, in this area, but also in a lot of the countries in which we work, the laws are very, are very robust and sensible, so a really good place to start.
And I would just follow up on what I said before. From our perspective as a solutions provider, we have to care about risk to the degree that our customers care about risk. We have to be at least as secure as our most conservative customer and provide them the ability to comply with the law in their jurisdiction. So it tends to make me personally more conservative in thinking about risk because I have to be sort of as strict as my strictest customer.
Okay. I think we're definitely out of time at this point. The experts are here. Use them. They're not going anywhere. JP's stuck in America for at least another day, I know that.
Absolutely.
Okay, so let's thank our panelists. And we were scheduled for a break at 2:30 to 2:45. We're now at 2:45, 2:47, so I recommend we go to 2:55. Okay, 10 minutes. Stand by your posters. People will come and talk to you.
There's some actually cupcake.
Okay, and so in these sessions, and we have 4 speakers, and there are 4 winning team, and for the competition. And the first one is our winner for the track 2, and from the IBM team. Let's welcome the speaker.
Thank you very much. Thank for the organizers. I'm going. Thanks also for the old team. The old team is a collaboration with Bar-Ilan University, which has the SCAPI Secure Computation API, which you can all download. It has many primitives that you can use, OTs, and all these building blocks that you use for designing secure computation. Just reading their names, so it's joined with Shai, Shalev, Nital, Yehuda, and Tom. So what is the task that we were tasked of? Track 2. So we have a client, he has some he has his sequence genome, and we have a database with many genome sequences, and the task is to compute using the closest genes in the database for that query. And we want to get the identities of the k closest sequences in the database, and closeness we mean by eddy distance or closeness. Okay, we want to perform this computation in secure computation. The query is not revealed to the database, and the database doesn't reveal anything about these sequences to the query, to the client. So using just some parameters, what was the task? So the database consists of 500 sequences. Each sequence is it's a segment in the genome that is about 3,500 symbols. The client has one sequence, and we wanted to find out was the k closest genomes in the database. Now, if we just the straightforward solution, how we do it with secure computation, so usually have a circuit that computes this functionality for us, and then run some general secure computation protocol. So just to understand how huge is this circuit, so just doing single eddy distance, it caused this amount of comparisons, which is about 1 million comparisons, and this, in order to be implemented, you need to do it with something like 65 million gates. This is just a single comparison between one query and one entry in the database. Since you have 500 eddy distance to compute here, this is going to be something like 32.5 billion gates, which means that if you use the state-of-the-art, the most efficient general protocols that we have now for secure computation, it's going to take you several hours to compute this task. And of course, this is not something that we want. So we designed an approximation protocol, approximation algorithm for this task. And approximation is very accurate. It's also very fast. We managed to push most of the computation to the pre-processing. Each one does many of the computation only on its respective data with no interaction. And the interaction itself, the circuit that computes comparing the query to the old database, is about 80 times smaller than the circuit for a single eddy distance that we had before. So the overall circuit that we're going to compute, the online, is about 30,000 times smaller than what I just showed in the previous slide. So after the pre-processing, which takes about something like 12 seconds, each query is going to take us something like 2 seconds, and even faster. Okay? So this is what we got. So overview of our solution, I'm going to describe our approximation protocol and talk very little bit about the cryptography. So what is this, the overview of our solution? If you have two sequences, you want to compute any distance, then it's going to cost you, the general computation costs you something like n squared, or if you know some upper bound on the distance, then you can reduce this to n times d. Now, our first observation is that if you break your sequences to blocks, and then compute each block separately, do the distance of each block separately, so you have n over b blocks. Each block causes you to do at the distance O b squared, order of b squared, which means that the overall at the distance between these two sequences is now becomes linear if b is very, very small. However, this is very inaccurate. Why is that? Because if you have just a small shift, a small deletion in one of the sequences, then everything is shifted, and you recount this error again and again and again. Okay, these two examples. If you just break the blocks like that, we are going to count this deletion over here that was between these two letters. We're going to count it many times. On the other hand, if we know somehow how to break it differently and allow some variant block sizes, we allow some blocks to be greater than b, some others smaller than b, then everything becomes more aligned and the computation becomes much more accurate. And the whole question is how to break, or where to break sequences. So we developed an algorithm just say, align. We compute any distance between our sequence and the reference genome, the full accurate distance. This is going to happen in the clear, no secure computation. Everyone knows its sequences, it can do it, and can do it during the pre-processing. Now we are going to break the reference genome into blocks of size exactly b, and we are looking at the alignment path of the computation. We know where to break this sequence that we are looking at. So in some sense, we align the sequence to the reference genome. So as you can see, the sequence sometimes has blocks that are greater than the size of the block of the reference genome. Sometimes it's even smaller. Sometimes some blocks disappear. But we align our sequence to the reference genome, and then this provides with approximation. So how is the protocol? The protocol, we tell the database, take your old sequences and break them into blocks. And after we did that, we found out that because in genomes we don't have a lot of variation, the number of values that we have for each block is there are no much, the number of different blocks that we have for each possible block is very, very small. In fact, all the values repeat, and we have only 5. We don't need to compare our query to 500 queries. We need to compare them to something like 5% of the actual values. This is the actual values that we have to compare. Moreover, it turns out that also the query, when it does this pre-computation, it does this breaking into blocks. After it breaks to blocks, it turns out that almost all its blocks also appear in the database. It's namely, the value here most of the time also appears as one of the possible values that the database also has in its one of its sequences. And therefore, there is no reason whatsoever to run any distance in the on-off phase. What we do all the edit distances in the pre-processing in the clear, and the database, the server, does all, when it takes all these possible values, compute all possible edit distances when it sees for each one of these blocks. And then in the online phase, all we have to do just takes block by block and to compare which one of the possible values we are, and that's the information that we have to compute during the on phase. So since this is the protocol, pre-processing each one block is all sequences into break all the sequences to blocks. The servers also compute some edit distance tables for all these possible values that they sync for each one of the blocks. And then in the on phase, the circuit that computes these comparisons, computing comparison and not any distance. Just comparison is a very small circuit. Just the number of AND gates is about the number of symbols that we have in that query, in that block. And therefore, the amount, the computation that we do during the on phase is almost nothing. And using some cryptographic tricks or morphism of secret sharing, we can use these values, these bits that we computed, whether the block QI, which one of the possible values it is. Using these bits, we can compute the actual approximated edit distance. And deciding the k-mean is done in a straightforward way. Okay, so let's talk a little bit about the accuracy and performance. So the performance really relies heavily on the block size, what is the size of the blocks. So we see, this is the block size, we see the possible values for each one of the blocks. Namely, after I break two blocks, how many values I have in each one of what are the possible values. It's very small, it's less than 20. This is because we don't have much variations, much diversity inside this genome, this region. So we chose for the competition to use block size of size 12, which means that overall we don't have much blocks, and it runs very fast in the competition. The solution that we submitted, I think the query was less than a second. And the accuracy is very nice. I mean, when we look at, take the top 5, the average rank that we returned for the 5th one was almost always the 5th. The average distance, what we return, how much is different from what we should have returned, is almost always the same one. The maximum K, however, where it is in the accurate set, the maximum that we found is something like that. And then we asked the organizer, let's see how good is the algorithm. What happens if we, let's test it in a more challenging setting, more sequences, and also, so they provided us database with much more diversity. The maximum edit distance now is not 180, but something like 350, which means like we have 10% of diversity. And it turned out that now the number of the blocks, the non-possible values for each block, it's significantly increased. It's something like that. And thus we had to move and shift our algorithm to work now with smaller block size, which means that we have more work to do in each block. Accuracy is less. We have several other, using some leakage, we can also solve this and we can get more accuracy. This is not what we submitted, it's just discovering what is the potential of our algorithm. And we do reach very good accuracy with something that doesn't need much information. We think it's even very, very secure. And performance, so for the database of size 500, our online time is less than 2 seconds. When you go to databases with more and more sequences, we still can return the result in a scale of seconds, which is very nice. Thank you.
Time for 2 questions maximum.
So how the public reference is treated?
What?
How the public reference sequence is treated?
The public reference for the sequence. How do you choose the sequence? I'll talk about the reference genome.
This is the reference genome. Oh, we have here, we do generate new reference genome from the database. We did not get into it. But using different reference genome, we can get better accuracy. Still, this is not what we submit.
So we generate a public reference stream from the database.
Yeah.
Publish
We generate something, it does leak something about the population of what is in the database, but it doesn't relate anything about any individual, because the way we choose it according to the most frequent value in each block. This is going, and we just aggregate them. This is going to be the synthetic reference genome. This gives the best results. Hybrid reference genome is when the server breaks its blocks according to this synthetic reference genome, but it does not send this reference genome to the client, because maybe it does leak some information. But what it sends, we're not getting into it, but if you remember in the edit distance, the way we break into blocks, we need to know where are the breaking points in the reference genome. So it's like change the breaking blocks for the client, just sends different breaking points, and the client, what it does is just compare itself, each one of its queries, to the public in general and standard reference genome, but it breaks it a bit different. That's the only leakage. So the only leakage is where to break, just different places to break the two blocks.
Question. How do you decide where is the breakpoint of the blocks?
So that's what, that's what I want. I said. So the reference genome, usually we just break it into even blocks.
You just break it
even blocks, and then everyone aligned according to these blocks.
So
now we know.
So you have to align every genome sequence in the database with this reference. So on average, how long do you spend to do this alignment?
We do edit distance, full edit distance between the sequence and the reference genome, and then you look at the alignment path and know where to break.
I mean, how much time do you spend to do this alignment?
Oh, it's few seconds. It was the pre-processing for the old database. It was something like 15 seconds. Again, you do it only once, now you can run how many queries of you in less than 2 seconds.
Okay. Thank you for the speaker. Okay, so the second speaker from the Manitoba, University of Manitoba.
Hi, it's me again. I'm from University of Meghalaya. Just shorting out the introduction. The previous presentation that I had, that you guys saw, is actually a very good approach to this kind of problem actually. I mean, we're also going in a similar direction towards the end of my talk. Actually, a little bit primer on the edit distance, as again, like we already know the edit distance is a really hard thing to do, even on a plain text when you are in context of genomic data. And so what's the main problem of the genomic data is like it's big, and most of the people that actually talk about edit distance and approximation of it, actually they always go for the length of the data, which is really big. But if I give you like shorter sequences like this, and tell you what's the distance between these two sequences, and you will most probably answer yes. So it's 1. But what about these ones? And you'll have to most probably compute a table like this, which is the plain Wagner-Fisher algorithm, which is like pretty like 70s, I think, is proposed. So the main problem was this one is it has a quadratic runtime, as you can all see, and it's on the theoretical side of it also. This problem is being handled like differently between the theoretical guys, because in the last year's talks, I think there is also a paper between like how to do this even in a lower kind of, you can do it in subquadratic time. If you can do it in subquadratic time, what else can you do with it? And they also said some assumptions, which I will get back into later, because this is a really interesting problem, and most of the time it's been coming up again and again. But one thing that's been different on genomic data is, from my point of view, is the construction of the data. As you can see, it's only like kind of like a quaternary data. You can only have A, T, G, or C in it. So when you are doing it, most of the solution, when you see an approximation of edit distance, most of the guys will go for this. Like even on reference, even if you use reference or not, most of the people will actually go for this structure. Because if I am doing an edit distance on your email, so then this problem would be totally different, and it's not totally the same anymore. So this is why edit distance on a genomic data is a little bit easy, I would say, but there is the fact that the data is too big. So what do I propose? I actually worked on 3 different methods, but this one is the only one which is, I actually made it like clear that my evaluation will be done only on this one, the shingle-based approach on the private set intersection. But I mostly will show 3 of them here today, because it's a good place to have some feedbacks on these ones. So the main thing approach about this method is you have a big database of genomic data. Like it is millions of genomic data on like billions of columns and all that, and it's a big search space for a top K query. So the first method, what it does is actually reduces the search space in a, for instance, in a managed position, so that I can use this one, private set intersection there. And then it reduces search space even smaller, and then I can go for banded alignment on using Gödel circuit. So it's 3 different techniques built one on another, but mostly my evaluation were done on this one. So moving on, how to do this. So you guys, this approach is kind of like the main thing that I'm going to be proposing is, it's a genomic data. So when I give you an image, it's actually on this, if I tell you this is a genomic data, you're going to be, okay, what's that? Why I am going for image? Like I have a single dimensional big representation of genomic data, A, T, G, and C, and it's running on forever and ever. But why I'm going for 2-dimensional data, that's the main thing. Why? Because there are like structures involved in this data which you can see when you are going to an image-based thing. And what is the best thing about images, that there is a totally different approach, like you can graph from computer vision side to this one. And this one is like really intuitive to me, was like finding out, like for instance, these 2 sequences are similar. So you can see there are some structural similarity over it. And you can use and retrieve features from it. I mostly, in the beginning, I used convolutional neural net from deep learning to use this stuff, but there are like pretty simple approach to this one as well. So how is this relating to security or privacy? So that's the main issue. Like whenever I'm going from this 2-dimensional data to a feature representation of the image, for instance, do you have this kind of structure? And you don't know which position you have the structure, and you can't really go back to for main sequence after I won't have these features. So that's one key motivation for me to go to this image and then coming up with some kind of pre-processing and use any kind of feature representation for this. And there are like plenty of computer vision algorithms that you can run on these things. And it's a totally different approach. And like I use DCTs, recently I'm totally exploring on this topic right now. So there are different techniques that you can do. Also, another thing I'm going to mention is like this thing. Like, can you really learn how to compute edit distance? That's one key important thing in this one. Can you really tell a machine, okay, can you even see after seeing these many sequences, can you learn what could be the edit distance? It's not about what could be the edit distance, what is the most similar one. In deep learning setting, what we usually do is like you have plenty of data and you actually tell it to learn what is the top k things that you have. So can we do the same thing on the genomic data context, and also in a sense like after you retrieve the model from deep learning or any other learning algorithm, you can't really go back to the data in a sense like you have a kind of deconvoluted sense of the data. You don't have the original one anymore. So that's that. There is a security discussions can be done on this, but moving on to the second method, the second protocol I said. So now my search space is really shrunk down, and I now can actually I will be using shingle-based approach. So now for every sequence that I can have, I will have a specific value for W and take the substrings. And you will also see this approach, I think on the last KMR, is also a synonym, is a kind of thing. And this thing is used in data mining a lot. So you have these shingles, and if the data owner makes these shingles and he points these out like you have n records with m columns and all that, and you make them a fixed size database. Like now you have like W is your shingle size and S is bigger than the n because you shrunk them down, and you only take the unique stuff from this sequence. So now you have a shingle representation of your whole database. So what you do, the researcher also makes a shingle set of his, and the database already has these shingles, and the database actually comprises like this shingle is present in these 3 sequences, for instance. Now what you do, they go into the private set intersection, which is kind of a fast in a sense. I used the 2015 paper from Benvinkas and others, and it's really quite fast, and they have like hashing-based approach. It's mostly an OT-based concept. So what they do is they do this private set intersection, and they retrieve the top k sequences, measuring how many intersection was the most popular. Like for instance, in this one, number 1 sequence on the database was the most one that was most matching. So in this way, what you at the end of the day you have is like top k sequences which has the most matches. So this thing is actually the security discussion of totally this thing is like belongs to this paper actually, because it's actually they tested it on, and it's really scalable, as you can see on the results. That even if you have a higher k, for instance, k is changing like 5, 10, 1, this thing will be always fixed because you have the same representation, and it's just outputting the sequences which has the highest intersection on the database. The final one to refine the results, this one wasn't evaluated, but this one is a little trick which is actually not computing the whole table. So in a genomic data, as I was mentioning earlier, the dimension of this dimension is the construction of the data is a little small, like it's a ATG or C. So where I'm searching for addition, substitution, or deletion, I don't have to go that deep in the table. I can find it in a certain kind of band. So I won't be computing the total table in a sense. I have a fixed band to compute. And for instance, for this position, I only considered these regions. And there is a specific band, like for this G, there is always 2 from here and 2 from next. So what you do, you kind of create a band and don't compute these other values. And this is done on the Gerber circuit. So in one single system, you have 3 different things. So the main thing about it is like, why so many stuffs going on into this problem? It's like, why breaking this problem that you have to do so many stuffs? It's like, it's not even necessary, right? But the main thing is about this edit distance cannot be computed in like strongly sub-quadratic time. This is a Stokes 2015 paper. The main problem, I'm not going into this thing, the main thing that they assumed and they actually proved in this thing is if you can compute edit distance in a sub-quadratic time, then Seth will be false. Seth means like strong exponential time hypothesis, which is a different thing, it's a different context. But the main thing is if you can do it, if we can reduce the runtime, and it's done from the MIT TCS group, the Piotr Indijk, and like Becker Sarters is like Piotr Indijk actually did a lot of work in edit distance back in 90s. So this work is actually, it makes some sense in a sense like if you can really do edit distance in a much lower runtime, then we don't really need that like this kind of format for handling this problem. But mostly in this competition, this method is like the one that's been evaluated, and thanks for that.
Yeah, we have time for 2 questions. Go ahead, JP.
Yeah, so can you elaborate a bit on so you mentioned this analogy with the images, but you haven't, you lost it. So how do you convert from the one to the other?
How do I compare this one and this one?
No,
does that
become
a
K-mer? So where are the genomes?
Oh, okay, the construction of this image.
Yeah.
So there are 2 things that you can do to construct this kind of images. One is this is a self-representation. For instance, if there is like, now it's really, sound a little crazy, but it's there like, this is A, T, G, and C running on like your sequence on one end, on your columns. And on your rows, on the first one, you also have the same thing. So the matches are white, the mismatches are black, and you can scale it down as it's an image. And also you can like keep only the matches and do plenty of stuff you can. And also you can put a reference in here as you have seen earlier. Like for instance, you take the average of all the sequences and keep the reference in this one. But it still is it's not something that is, if you want to use, for instance, this thing is already millions longer. So this image size will be million into million. So why image? The main thing is about you can shrink it down, you can scale it down, and also after this construction of the image, you just keep the structures and remove it. And then on this structure, you do the similarity and all that.
What kind of
Can
structure?
so this was my question. Can you expand on this? Because I don't understand. So I'm trying to think and talk at the same time. Never a good thing. So your K-mer model, right? The second one that you were talking about. You're doing this off of a sliding window, right? How do you take, so the Schickler model. So if you were to take your self-similar image and you were to translate this into something that you could build shingles off of, you're saying that you would do feature extraction off of the image?
Sorry for the abstraction. These 3 things that you see, these are totally independent approximation of edit distance. Like this one has a different accuracy and different running time. It's a little fast. It lowers your search space. Now, for instance, you had 1 million sequence to search. Now on this one, you have only 1,000 to search.
Okay, so these methods are just not related to each other.
Not related to each other. It's just build up on it.
On the image side, do you generate one model per sequence or one model per marker?
Oh, for this convolutional neural net, you say?
Because you're going to have to train a neural net.
Yeah, so training the neural net was like, I grouped the sequences, for instance, using a reference, or for instance, you take for instance, in general word, in deep learning what we do, this is a bird image, so there is a category to each. So I categorize all this image to a specific number.
Right.
So after that, those models actually try to learn, for instance, this, if it has this kind of structure.
You label each image differently, and then you
Yeah,
to predict
and they go to certain groups, and those groups, the similar groups will go into this one.
Right. But how do you cope with adding or deleting entries in your database?
This thing is the last one.
On the image side?
On the image side, this is just reducing the search space, and you are like, this is why this is a pyramid kind of structure. The more accuracy that you want, the higher that you have to pay with time and all that.
Well, no, you would get reasonably good accuracy with the image processing, depending on how you encode it. But then you're stuck with adding and deleting.
Yeah, it's mostly like kind of like goes to the Hamming side of things. But the main thing, like one thing I can say, like for instance, this structure is here. For another image, it's here.
But
so
you can
so
find a
it's
match depending on how to segment your image.
yeah. So one key thing also in this, like for instance, substitutions, for instance. So these are matches, for instance, T and T matches is a white string, for instance. And A and A match is also a white string. So when you are substituting those things are gonna be interchanged, and these will represent to a specific structure.
Yeah, but once you have your model, your labels are defined, you're gonna have so many outputs.
Oh, okay, there is not so many labels, like I already categorized it. For instance,
Okay, no, we always kind of work offline.
You could combine two there, because if you can do that,
yeah, I
you
can
could use
like this approach.
a quick image analysis to reduce your search set.
Like my primitive intuition on all this problem was using RNN at the first, not even images. Because RNN makes more sense, you have a recursive thing. But it's also at the end, you have to say something, okay, you have put a model which is, describe the security of that thing right now. So that's the main issue of this thing. That's why I went for images and CNN. But I would say like DCT and other image-based approach, which is not that much computationally expensive, works better on this problem because they actually do the cosine transformation. And for instance, even if you use filter-based approach, Gaussian filter on this image, only this position will remain, the white ones will remain, and then you do the thing. So CNN is a little bit far-fetched, so that's why I didn't give it to the competition at all.
Okay, so I guess we're running out of time. Let's take the question offline.
Stefan, can you just say, so you use K equals 4 in your solution?
Yeah.
K equals 4?
K equals to K. Shingles.
Oh, no. It's I actually did some experiments and I actually set it at 10. Like,
thank you.
Thank you. Let's thank speaker again. So the third team is University of Maryland. It's work. Your email.
Hello.
Okay, I guess let me just use the keyboard. So sorry for the wait. Hi everyone. My name is Xiao Wang. I'm from University of Maryland. So it's a joint work with my advisor Jonathan Hart. So just first of all, our implementation used the new EMP framework. I'm going to talk more about it in the later slides. So like I think everybody should have get an idea what problem we are trying to solve. So let me just directly get into the solution. So here we have a patient holding one genomic sequence and a database holding like a set of genomic sequences. So our approach works in two stages. In the first stage, we are going to compute an approximation of the order of the edit distance and fill out most of the genomic sequences that are not relevant. And then we are going to compute
more accurate edit distance on the small set. So in the first step, we are going to compute some hash on the data. The hash is a special form of locality-sensitive hash. And so after two-party compute this locally, they are going to do a two-party computation based on Garble circuit. So inside of the Garble circuit, the two-party will first try to recover the approximated order using the local hash. And then they are going to review the ID for the top C times Q genomic sequence if we want to find the top Q query. And let's say if we set, let's say C equals to 2 and Q equals to 1, it's going to let the hospital know 2 ID, let's say 2 and 5. And then after hospital know 2 and 5, hospital is going to select privately, locally, the second and the fifth genomic sequence. So now instead of computing 5 edit distance, we just need to compute 2 edit distance. Then the two parties is going to compute some restricted edit distance and find the Q smallest genomic sequence. So as we can see here, so the most expensive computation is done locally. Is these hashes, and so instead of doing them in online, we do them locally offline. This is going to give us the top Q result. So the first part of the technique is how to compute the locally sensitive hash. So it's done like in few stages. Let's say if we have a genomic sequence, we are going to first compute the k-mer set of the genomic sequence. So it's essentially the set of all possible k-length substring of the original genomic sequence. And after we have the set of k-mer, we are going to compute some sketch on this set. So in this, so in our particular, for the submission we compute an approximation on the Jacquard similarity of the two sets. So so Jacquard similarity is a very meaningful metric in the bio community, and the way to approximate Jacquard similarity is done by mean hash. So in this slide, when we want to compute the approximated distance, we essentially use the Jacquard similarity as the metric. And then the next step is to compute the edit distance. I believe you guys have already seen this table multiple times. So the very original edit distance works on arbitrary edit distance. It's well known. And there is it's also very popular to have a better solution if we only have, let's say if we have a bound on the edit distance. And similar to the submission mentioned previously, we can, so here, so for the bounded edit distance, if there exists the best solution that is covered in the shaded area, then there won't be any error. And if the best result ever get out of the shaded area, then there will be an error in this case. So in order to think about how to make it further even better, we want to first take a look at the best edits between the two sequences. So let's say, so if we have a horizontal error, this means that there is an insertion happening here. The diagonal means that there is a substitution, and the vertical error means that a deletion is needed. And if we actually rotate, I mean, you can rotate the neck or we can rotate the slides. So if we use the diagonal as the baseline, we can see every insertion brings you far away from the diagonal, and every deletion brings you back to the diagonal. So what essentially matters is not the edit distance, but how far we can go from the diagonal. So this means that we can actually, I mean, let's say in this case we just need to compute the dark part. So essentially, but how to, so the height from the furthest point to the diagonal is essentially the bound that for any substring of the two sequence, what's the maximum number of insertion minus deletion? So we find so we have a public bound on this number, and we only use this bound in our submission. So I want to talk about like the leakage of the whole problem. So we leak something, but not not a lot. So let's say all these gray points are the data. Let's say imagine we are in a hyperplane of genomic sequence, and this gray point are hospital's data, and so this star is patient's data. So if we find the best result, let's say we are going to find let's say the top 2 result. So the leakage, however, from the hospital's view, instead of just having the 2 entry, we're actually giving kind of a larger circle of it. So the hospital's view is this green circle. So from some sense, we want to see if hospital is actually able to simulate this view given only the output without patient's data. So we are arguing that it does not leak a lot, because even without patient data, the hospital is still able to find this kind of circle with given the circle of the output. So our implementation is done using our new EMP toolkit framework. It's open source here. It provides both semi-honest and malicious execution, and is able to gobble like 20 million gate per second. So here is some performance result. So we ourselves just tested on top 5, 10, and 20 with C equals to 1 and 2. So in the case when C equals to 1, it essentially means that we are not going to compute edit distance at all. We're just going to use the approximated order as the final result. So we can see actually. So in the case where we don't compute edit distance at all, the time is almost does not change, even if we are computing like top 20 best result. So before I go right into the accuracy, I want to first raise the problem of how to choose the best metric for the approximation algorithm. So let's see. So I think the way to measure the accuracy in the computation is to find the number of entries that hit the top k. However, so in our solution, we actually measure the accuracy in another way. So let's see. Let me just have everything here. So let's see. This is the patient data, and this blue circle represents the accurate top 3 result. And the distance between the patient and the furthest furthest accurate result is this blue arrow. And let's say this red circle represents the approximated result, and the red bar represents the longest distance from the patient data to the approximated result. So let's say if these 2 bars actually are the same, it means that we are essentially returning some result that is as good as the accurate top k result. If this is actually longer than the accurate result, it means that our solution is slightly worse than the accurate result. So this captures some other properties that is not able to be captured in just counting how many genome sequences in the top k. In the sense that I want that even if I cannot hit the top k result, the remaining result still gives me some meaningful result. Let's say if I want to compute top 5, I mean 3 of them is in top 5, but the last 2 is actually the 6th and the 7th closest, then it's still a very good approximation. So our accuracy is measured in this sense, and for top 5, the exact result, the furthest distance is actually 68. And in our case, if we use C equals to 2, our furthest result is like 71, and the faster version is 72, which is slightly worse. And even if we compute like top 20 result, the exact result, in the exact result, the furthest distance is 73, and in our version 1c equals to 2, it gives the worst result still gives a very close result compared to the exact result. Okay, thanks, and I'm happy to take other questions.
I'm just gonna have questions for everybody. So I'm a little confused. You revealed additional information in the process, right?
We reveal the ID to the hospital. I mean, this is the case for all the algorithm, all the approximation. We only reveal the ID to the hospital, that ID can actually be obtained, can be computed even if you already get the output.
But so the request is to get top K, and you're basically revealing more than top K in terms of like a reduced set, and then you're getting top K.
I think you need to imagine like this. If I already have top K, even if I don't know anything, I can already know what is going to be the result for K plus 1, because top K kind of gives me a region.
How does it give you the result of the plus 1? Let's say I have 100 records and I'm asking for the top 5. Show me what the top 5 are. How do I know what the 6
No, I mean, we only like the hospital. I mean, the hospital. So in our solution, hospital obtains the ID for the first to the fifth, and just using this result, the hospital gets some idea where the patient's data is, right? Okay.
Yeah, I think I can take it offline. Another question.
Okay. It's looking at you are choosing C equals to 1 or 2.
Right.
Yeah. Can you increase this to improve your accuracy?
Yes. C can be tuned arbitrarily, but we just wanted to give a cleaner interface to the submission, so we just choose C equals to 1 or 2.
Another question. If you increase C to large enough, can you make sure your answer is always 100% correct?
If we are assuming that C is large enough and we have a bound on the difference in the insertion deletion, yes, it's always correct.
Okay, thanks, speaker again. The last talk is from IU Bloomington.
Good afternoon, everyone. I'm Yue from Indiana University, and this solution is done with my advisor, Professor Yan Huang. I think you guys have seen a lot of approximation solution, but our solution is straightforward and simple. Our pathway is first use some scanning algorithm to identify the most promising candidates. Like if we want to find the top K, we suggest you to find like 2K candidates or 3K candidates. Then with some special garbage scheme, we can securely compute the precise edit distance between these candidates and the query. Based on our special garbage algorithm for computing the edit distance between two genome sequence takes only like 4.74, less than 4 seconds, only 3.74 seconds for a pair of genomes of more than 3,000 nucleus. And if you're using EMP2 or the classical garbage scheme, this number will be like 10 times larger. And based on our test onto Amazon machine, our solution spent like 40 sub-seconds to compute the edit distance between 10 candidates and the query. And This relationship is that our solution always gives accurate edit distance. This is not an approximation solution. And I think you guys must be interested in our special governance scheme. Let me show you the details. First, we fix a large prime, and then we will always do the calculation based on the module of this prime. Then we randomly pick a secret delta. Of course, this delta will be co-prime with this modular p. Then a y label will be denoted. A y label that the y label that denotes a signal x belongs to z mod p. Note that this is a very, very large space. And this label is denoted as p0 plus delta times x modulo p. And this, sorry for this. And this p0 is served as a mask. So if you don't know this x and delta, this key looks totally random to you. And this is 88 bits, and we add another 40 bit tag here as an identifier for the correct decoding. And this whole thing is 180 bits, which is exactly the length for AES block. And in our scheme, addition is free. You know, in order to calculate the edit distance, you have to do a lot of addition. But in our scheme, addition is free. In order to do addition, like we have two Y labels, W1 and W2. We only need to do an addition of this key 1 and key 2 as the appending the tag. This is all we need to do the addition, and this is very cheap. Second, do the minimum in our scheme is also very cheap in the context of the edit distance. Because if you want to do the minimum of A and B, you can use A plus A, the negative part of the negative of the A minus B. This negative part means if A minus B is negative, gives if this A minus B is positive, gives is the opposite. If it's negative, gives 0. And this will help you to calculate the minimum of A and B. Notice in our scheme, this addition is free. And in edit distance, this A minus B can only fall into 4 different values: -2, -1, 0, and 1. That means we only need 4 rows of ciphertext to do this minimum circuits. And with the label, Y label of A and Y label of B, we first do a substitution, which is exactly the same cost of addition, and use the output to decode one of these 4 ciphertexts. Then we add the decoding result of this ciphertext to the original Y label A to get the minimum of A and B. And in each iteration of our edit distance protocol, it requires 2 calls to this minimal and 1 cost to the comparison, which will cost overall 12 ciphertexts. No matter how large the integer is, how large the problem size is, we only need 12 ciphertexts. And this version is like 80-bit security version. This can easily be upgraded to a 127-bit security version by choosing a larger prime and using a different encoding scheme. And this will cost our, give us a 100 addition cost compared to the 88 scheme, because we have to double the cost to the AES encryption. And of course, we have to use this technique with so-called bounded distance, because we already know this is genomes, and we already know that our candidates are very promising. They are very, very close to the query. So we are assuming that the distance between the candidates and the query are very close, so we can use this bounded scheme we only need to compute this dynamical strip on the dynamical programming matrix. And this is what we use, the special gapping scheme for our solution. And now I can make some explanation about our fast scanning scheme. First, we have to use the public reference genome, and the database server align each database genome with its reference, and the client aligns the query genome to its public reference genome too. And they compute the Hamming distance about the edits of these genomes to give a first idea of how close between this database genome and the query genome. And we use uplift sorting to get the most promising result of the top candidates. And the ranking in this Hamming distance are roughly consistent with the rank of the edit distance. And we just pick 2K candidates in the database for later precise scale edit distance protocol. We find the top K close genomes. However, according to the evaluation, sometimes 2K is not good enough. For example, we only got 4 out of 5 for finding a top 5 candidates qualified close genome. So maybe the database owner want to set this 2K maybe to 3K or even larger. But please note that computing the edit distance in our protocol is really, really fast, like less than 4 seconds per pair. So increasing this 2K to 3K or 4K doesn't result in much more cost. And here is the proof for this bound. I don't really think that it's suitable to explain the detail of this technique here. So basically, I'm done.
One question regarding your fast scanning approach. Doesn't that leak information that wasn't supposed to be leaked?
Yes. Actually, I think all of these solutions will somehow leak kind of this information. Otherwise, you have to compute either the precise edit distance or the approximate edit distance between the query genome and each database genome. Suppose you have a database with millions of genomes, you have to compute millions of edit distance, which is not actually practical. So you somehow have to allow some leakage of this kind of information. It's not really questionable. Besides, if you have the output of the protocol, you have already know the top 5 or top 6 close to genome, it's not very, very easy, really very, very easy to use some simple machine learning algorithm to find top K+1 or top K+2, and it will be very, very accurate.
Go ahead.
Small question. Same question I asked earlier. How do you get to pick K? Right? So
yeah.
Who picks the K and when does it happen?
Say it again.
Who picks the K?
This is a pre-decided before the protocol starts. The client and the server set the value of K before they start the computation.
So you have to reveal the IDs
yes.
to the server.
Yes. I have just explained to you that you have to allow some leakage. Otherwise, you have to compute the edit distance, which in our Blazing protocol, you have to spend 4 seconds per computation. You have to compute millions of them.
I'm invoking the Bogdanov rule from last year. I'm saying these are cheating.
Barrett.
Okay, sorry, I take it as
it's a trade-off. It's a balance. Okay, that's all for the session. Let's thank the speaker again.
Due to the time limit, let's give up the break and let's go to track 3 directly. And the first team is Microsoft. So please come. So we have 15 minutes per team, and I'll count time to make sure that we stay in time.
All right, so it's my pleasure to start this last track of challenges and explain our Microsoft Research Group's solution. So this was actually an intern project almost. So we had plenty of interns, Gizem and Peter and Susan this summer. So we worked on this together. So let me just explain the task first. So the idea is that you're an individual who gets your genome mapped, and you discover that, okay, I have these and these mutations at certain locations. Well, you could certainly store all these things locally on your computer, but why do that? You don't want to lose your files, so instead you want to store it in the cloud. So you want to upload it into the cloud, but of course you don't want to reveal your mutations, your SNPs to the cloud, to the server. So instead you want to encrypt it, and now at a later point you somehow want to retrieve information. You want to know, did I have this and this mutation? But well, to do this, if the data is, for example, AES encrypted, you would have to return the entire file back. And I mean, you actually don't want to reveal any information to the server really about this. So what do? You have to come up with some other way of retrieving this information. And for this task, we used homomorphic encryption. And because homomorphic encryption is this technique that allows you to perform some computation on encrypted data. For example, if you store your mutations in the server, you can run the computation that compares the stored data to your query data that you submit. And the query data is also encrypted. In this way, the server doesn't find any information about it, but can still do the computation using this homomorphic encryption. You get an encrypted result, or the server gets an encrypted result that it sends back to you. And now hopefully the server is sending you only a little bit of information back. It's not like you have to retrieve the entire data set. So that's like some of the goals. And in particular, the sort of first challenge here is to return just a result match or no match, depending on whether your query was there. And then there was an escalation of this challenge where we perform a multi-query. But let's do like 5 queries. Then can we do this more efficiently than just like repeating 5 queries? So the mutations are in this VCF format, where essentially the list of mutations is like 100,000 rows, and each row is 40 bits. And the 40 bits is, it consists of the chromosome number, first 5 bits, the starting position in the genome, the reference and alternative, which are ACGT, and then we encode one last bit, which is this an SNP? Because this VCF format also contains all kinds of other things, mutations, than just SNPs. So the key concept here is that first of all, we use some kind of hash tables. You have this 100,000 entries long list of mutations, and each of the mutation consists of like 40 bits, and you have your own query, which your own query is also like a 40-bit string, and now you want to compare this to this thing. So the first thing we do is we insert the 100,000 mutations into a hash table. And we use this for cuckoo hashing, which is a very well-known technique. This permutation-based hashing for cuckoo hashing is a very well-known technique in private set intersection protocols. Because this allows us to actually do this hashing, but at the same time, it's done in such a way that like the location where you insert each item, it encodes a part of the string itself. In this way, these 40-bit strings that I just did here, they in fact become 30-bit strings. So that's very nice because now we get this homomorphic encryption sort of scales not very well with the string length. So now we get some improved performance from these shorter strings. So I'm not going to go to the technicalities of this, but we do basically actually explain a little bit more detail in what we do. So we have these 100,000 rows. We don't, in fact, just form one hash table. We form 14 hash tables from that. And from your query string, you create one single hash table that you now need to compare to each of the 14 hash tables that are in the encrypted data set. And this has to be done using homomorphic encryption, and then the point is to somehow aggregate those results using homomorphic multiplication and return the result to the client who can decrypt it. So that's why, in addition to having the data set being formed into 14 hash tables, the query also becomes one hash table that you then compare to it. So here's a nice thing that we get from this hashing also. If we want to do multiple queries, because you have a huge hash table also on your client side, you can easily insert one query there, but you can insert multiple queries there. So this means that these 5 multi-queries and 50 multi-queries, we can just put all of them into one hash table and submit that, and it all goes in one shot. So there's no extra overhead in doing these multi-queries. So we get it all for free. The comparison itself is doing this kind of compare, add, multiply technique, which is super simple. Basically, you just do homomorphic subtraction of the query hash table and the dataset hash tables. And if you have a match in sort of any of these items in the bins, you get a 0 as a result of the subtraction, otherwise you get a non-zero result. So this is how you can detect a collision, a match in one of these hashed slots. Well, the nice thing with homomorphic encryption is that, because I said that on the server side we had in fact 14 hash tables, well, you can actually do this with just additive homomorphic encryption. You just compute the difference between your hash table and the dataset hash, the 14 dataset hash tables. But now the result would be 14 sort of differences. And in this sense, when you would return this back to the client, the return data size would be the same as the encrypted data size. So you would in fact return the entire encrypted data set back. So that doesn't really make sense. But with homomorphic encryption, we can aggregate these results by computing the product of the results from all of these 14 subtractions, all of these 14 differences. And because if in one position in one of these hash tables, you have a match, it appears as a 0 there. And now when you multiply such things together, the 0 kind of carries through the entire thing, and you have a 0 in the product, which is now just one hash table. So now you just return one hash table back to the client, and you can see where there were matches in any of these 14 hash tables. There's some technicalities here, but because in reality, I said that even with this permutation-based cuckoo hashing, we could shorten the strings to 30 bits. Turns out that 30 bits is still quite a lot for homomorphic encryption, depending on how you exactly do it and what you do. But we kind of want to split that 30 bits into chunks of 10 bits. And that's why we do this kind of extra partitioning. You can see the difference being computed there for each of these 14 hash tables. The difference is being computed, but then we add together the results squared for each of these 3 blocks that we do, because the strings were 30 bits long, but we only wanted to really compare 10-bit long strings, so we have to do it 3 times for each of the 14 hash tables. And because we compute the difference on the square, that then zeros stay zeros, and everything non-zero just adds up to something more and more positive. Well, what does the client have to do? The client now receives one hash table. It's encrypted, so they have to decrypt it, and they look at where they have zeros in these bins. And if they see a 0, they know that it's a match. And they can, I said that we can do these multi-queries where we pack many things into the query hash table easily with this hashing technique. So in fact, the client can see also exactly which ones of its queries match. I think in the problem description, the question must only answer match or no match, even for like multi-queries, like where all of them found or where not all of them found. But we can in fact tell exactly which ones were found in the data set. So to implement this, we used our homomorphic encryption library Seal, which uses this Feinberg occurrence scheme. It's an ROW-based homomorphic encryption scheme, so pretty standard there. We used encryption parameters like this. So to some of you, they probably mean something. And these are estimated to give around 90 bits of security, according to Albrecht player Scott 2015. So pretty good in that sense. So what do we get in performance? Well, we did these 5-fold multi-queries. Like I said, there's no difference in doing 5 queries and 1 query. So we could do this in 2 seconds on my desktop computer. The query size is 2 megabytes, so that consists of 3 ciphertexts. And the return size is just 1 ciphertext, so that's 600 kilobytes. The size of the unencrypted dataset, so this is the pure list of mutations, 100,000 mutations, 5.5 megabytes. And now when we encrypt it, of course, we're going to get a significant message expansion, because that's what homomorphic encryption does. So we get this 25 megabytes there, and then there's no message expansion in that. So if the client would, for whatever reason, at one point want to return their entire dataset, then they can certainly do that by downloading back this AES encrypted thing. But it's kind of interesting to see here that like we could get this result return size to be 644 kilobytes, and that can still be improved. So it's much less than having to download the entire dataset. There's actually a lot more interesting things in this direction to explore. So, for example, here we see this annoying thing that the query size is very large, because it consists, in this case, of these 3 ciphertexts. There's actually a way of compressing that into just 1 ciphertext, which is kind of important, because now the query size is like 1/3 of the unencrypted dataset. But we can compress that to 644 kilobytes also. We didn't have time to implement it though. This kind of technique can also be used to construct some private set intersection results, so that's an interesting direction. And another very good question is, okay, well, our technique only allows to do like exact matching, so how can we do better partial string matching or some post-processing of the results? Thank you.
We have time for 2 questions. Yeah.
So, Cam, excellent work. Entire team and you. So the result that you return, that you actually end up encrypting, what does it look like? Is it some sort of packed result, or is it a single polynomial that you return? Or what's the format? Because I'm kind of curious if there's anything that you're leaking in there with extraneous information?
In the return side,
Yeah.
well, the return is just one polynomial. It's like a batched homomorphic ciphertext.
Yeah.
So it's not. See, the security model here is kind of interesting because you're the owner of the data, also. Like what we could do if in some other kind of security situation is to like apply some masking multiplication to these slots that didn't match.
Yeah.
But here there's no need to do it because you're already the owner of the data. It doesn't matter. It doesn't matter. You're only worried about leaking information to the server.
Yeah. So you're doing the computation on the side, having the result come back in one slot of the polynomial, that happens a bunch of extraneous information in the other slots.
That's true. Yeah, I mean these slots do reveal information about the data set, but that's okay. And like I said, it's easy to mask that if we wanted to.
Yeah, you're right.
Yes.
One thing, you only consider, so in this project you see slips, you can only search for slips in the database, or do you project for other?
We can search for other things too. I mean, it's just
increase the size, because like, so for example, if you use like a normal encoding, so slips are always that specific size, so when reference or alternate, but when you have like, there are for example the files and test files, they're like big enormous substitutions that you have enormous sets of things, so when you have an enormous set of things, you get make it bigger.
well, in fact, it's not really that bad. This behaves kind of well with the longer string size also, because as you can see, the homomorphic computation consists of essentially 3 parts. First, you have to do the comparison, which is the difference. Then you have to do the squaring, well, some numbers, but difference, squaring, addition, and finally you take the product. So the product is the noise-wise costly part. So here you take a product of 14 ciphertexts together. But this K here, like I said, we had 30-bit strings in this case. And I said that we don't want to directly like compare those. Instead, we partition those into sets of 10-bit, 3 sets of 10-bit strings, and then we compare those because that's easier. So this K here is in fact 3. And for each of these 10-bit blocks, we compute the difference and the square, and then we compute the sum. But like whatever this sum is, even if this goes to like 100, it has hardly no effect on the homomorphic noise. So it's just about like a running time if the strings get longer. But it has the difference, like it doesn't really hurt performance that much. So we could easily go to longer strings.
Okay, let's thank our speaker. Our next team is from Seoul National University.
To Chicago, it's my first time, and it was very nice here. Of course, I'm happy to present our work. This one was done with Mira. She was the winner of last year iDASH competition, and my professor, my advisor, Professor. So this presentation consists of motivation and our cryptographic schemes used in the solution and experimental result. So, as you know, the track 3 is about outsourcing computation of testing for genetic disease. A database of chromosome number, position, and sequence of SNPs is included in each of database, and core genome is kinds of duple of this information. So we aim to find the matching of a query within the database. So we'll make the use of one-term function for encoding. So we'll send a pair of chromosome number and position to an integer di by this map, and di will be an integer of size 32 bit. and the sequence of SNPs will be also sent to an integer alpha I. Then our goal becomes equality checking using homomorphic encryption. So the problem is, as you know, the comparison or equality check is very expensive in homomorphic encryption. So we try to find a way for avoiding this operation. For a moment, I should explain about some basic cryptographic schemes because our solution is very theoretic. So the first one is just standard ring-doubly public key encryption. So the choice of cyclotomic ring and the degree is power 2, and each register is standard choice for ring-doubly problem. And the secret key is just a small polynomial S. We will place the message polynomial in the MSB of modulus Q. So the ciphertext C of M will satisfy this equality. C times Sk is Q over T M plus small polynomial E. So we can very efficiently convert the ring-doubly ciphertext of this polynomial M into LW ciphertext of M0, where M0 is a constant term of this polynomial. This conversion will place an important role later in our solution. The second primitive is GSW scheme. So Gentry-Tsai and authors suggest let's say LW-based homomorphic encryption, encrypt 13, with matrix ciphertext. And this is the ring variant of GSW scheme described in Dukas and Michencho's Eurocrit 15. So we choose a decomposition base B and exponent K such that B to the K should be larger than the size of modulus Q. And Gaussian matrix is defined by the tensor product of power V and identity matrix. Each encryption of M is done by generating several, 2K number of ring LW samples and adding M times G. So each ciphertext is 2K times 2 matrix. So you can check that encryption of M satisfies this equality. We can operate addition and multiplication between GSW ciphertext, but I don't explain it because we may use the operation between GSW ciphertext. Instead, I introduce the multiplication of two different types ciphertext. This multiplication is motivated from this paper by Charlotte Eder, and it will be appeared in this year Asia Crypto soon as a best paper. But in fact, we already knew this intuition of multiplication already from several years ago. You can think about key exchange of homomorphic encryption. So anyway, it seems to be that the set of GSW ciphertext acts on the set of ring LW ciphertext. So their multiplication becomes again ring LW ciphertext. The multiplication is done by just decomposition of ring LW ciphertext and multiplication with GSW ciphertext. If we have two ciphertext of GSW encryption of M prime and ring LW ciphertext of M, then their multiplication becomes ring LW encryption of M prime with this increased error E star. You can check that if M prime is large, then this error becomes large, so we should use a small M prime here. So now return to the main topic. So as I mentioned before, our database will be encoded to this set of pairs. This integer di contains the information of chromosome number and position, and alpha I contains the information of SNPs. So we first construct this polynomial. Alpha I is here in the coefficient and di is in the degree, and use the public key ring double encryption to encrypt this database polynomial. And this ciphertext will be stored in the server. And then for a query, d and alpha, we use only integer d and make the monomial x to the minus d. It is equal to minus x to the n minus d because we use the cyclotomic polynomial of power 2 degree and use the symmetric GSW scheme for encryption of query. So assume that we have these two ciphertexts. If after server multiply these two distinct type ciphertext, then we gain an encryption of this ciphertext alpha I times x to the di minus d. Note that the constant term of this polynomial is alpha k if dk equals the first one, index k. Otherwise, it will out the random number. So our evaluation is done already. It's not like equality check, but I can say that it's like a secure searching and extraction of required information. So, and additionally, you can, you should carry out conversion. I mentioned in the ring and double encryption because this ciphertext contains too much information about database. So if you remove the second entry of ciphertext except the constant term, then every information is disappeared except this only one scalar. So you can prevent information leakage. And additionally, you can carry out modular switching to reduce the size of resulting ciphertext. If you don't care about communication costs, then this step can be skipped. And the client get this FW ciphertext and decrypt and compare with his value alpha with this alpha k. So this diagram summarizes our solution. So database was encrypted by ring and double scheme, and query was encrypted by GSW scheme, and multiplication result is converted into SW ciphertext, and you can use modular stitching for size and decryption output alpha k. Our multiplication can be done very quickly because it's just one circuit, just one multiplication. This is our experiment result. Every computation was done in my MacBook laptop because I don't have any supercomputer. So here, this number denotes the number of SNPs used in comparison. So in fact, I feel sorry that the comparison of performance was not unfair in some sense because we used 20 number of SNPs for reference and alternative each. It took 2.7 seconds for 10,000 lines of database and took about 7 seconds for 100,000 lines. If we use only 5 SNPs for each, then every computation will be divided by 4. You can see that the timing of evaluation was divided for each. So if we use less number of SNPs, for example, 1, then this timing will be less than 0.2 seconds, I guess. And because we are not so professional at coding, so we use just a pure C++ language with some known library for polynomial operation. And for optimization, we split this degree integer d into 2 integers because 32 bit is too big for ciphertext dimension. So we have two ciphertext, and when alpha is too large, for example, in this case, we use the 20 SNPs, so alpha will becomes 41 bits. So we split alpha to, again, several ciphertext for optimization. And yeah, that's it. Thank you for attention.
Thank you. We have time actually for 3 questions.
Yeah, so can I ask, so on one of your slides you mentioned that when you decrypt, you'll get a random value if there's no match. So, but does it mean like when in encryption you'll fill the other terms with random values? Is an encryption of sum of alpha I x to di?
Yeah, in fact, I didn't mention here, but if some questions are empty, then we fill the random value here. So, if we don't fill the value, then it, sometimes it is alpha 0, then you can check that the DI is not in the database, so we fill the random value here.
I see. So can I ask? So also I'm curious about, so you mentioned that its DI is 32 bits, so it's too large, so you split it into 2 strings of then 16 bits. So is that like kind of the optimal, or have you tried different combinations? And that's
in fact, I didn't try any variants because split of I have some problems. In fact, for example, you assume that you have 2 integers. But if you split them into 2 DIs, then the first term may be equal. Then makes trouble in the evaluation. Because we should have the value in the same location, different values in the same position. So if you divide the to too many integers, then that will be, we should generate too many number of polynomials. So
I see. So but you don't multiply them all together at the end, like, but you return. So with this split, will you return 2 different?
No, we don't multiply the result. We just if we have several polynomials, then we will have several of them, and the client can check several times for each. Yeah, but the number of polynomials is not so big. Like for example, here in the case of 100,000, the number of polynomials is just 5, so it's not so big.
All right, let's thank our speaker again. And our third team is from Francis German.
Sorry for the delay. So my name is Henrik. I'm from RWTH University in Aachen, which is in Germany. And there are far too many people who work with me on that project to list them all. So since we're first timers with this competition, probably you've never heard of RWTH University or Aachen for that matter, so I'll give you a short introduction. So Aachen University is in Germany. It's located right on the border to Netherlands and Belgium. So if you ever come to visit us, you basically get 3 countries for the price of 1. And we have 40K students in a small town of 250K, so like every 5th or 6th person is a student. I'm from the chair of communication and distributed systems, short COMSYS, and we are mainly involved in the design, analysis, and engineering of communication systems, and in the last years it's also secure communication systems. So we're 1 professor, 2 postdocs, and a couple of PhDs. And I want to draw your attention to the Europe undergraduate research opportunities for North American students to come and visit us for 10-week research internships. And for our last student, Mary, down on the picture, we actually threw a German-American barbecue for the farewell. So we took part in this competition in the research-focused classes, which is a teaching format where we have PhD students teach bachelor's and master's students who want to pursue a PhD and tell them how to do first research experience. So basically we have 2 teams, 1 team working on track 2 and 1 team working on track 3. And I'm presenting the solution in track 3. And us PhDs, we just contributed with ideas and basic lectures about the basic techniques that they could use and things like this. So no professors harmed in these experiments. So let's dive into the solution. So the requirements for the test, basically it's a set intersection test, and we have a database with VCF files for each patient with 10K to 100K SNPs each, and a query. And the output should be the IDs of the patients that match all queried SNPs. And this is in the secure outsourcing setting. So what we want to do is minimize computations on the clients. And this means that the majority of computations has to be performed in the cloud and securely in the semi-honest model. And so what we use is fully or somewhat homomorphic encryption. So we actually developed 2 solutions, and I will present the high-level ideas of both. So the first one is based on HELIP and on fully homomorphic encryption, and the second one is based on the Payet scheme. So the outline for both solutions is the same. So what we do first is we take the database, and we take each VCF file in the database, and we encode each SNP, and we encode the entire file in a Bloom filter. So what we get is a very long Bloom filter with single bits in it. So think of like 500K to 1 million bits in this Bloom filter for the setting that we have here. Then what we do is we encrypt the Bloom filter and we upload it to the cloud server. So then the cloud server has we only call it the encrypted database from now. So this is all pre-computation. Now when we get the query, we do the same encoding. So we put it into a Bloom filter, we encrypt it, and we upload it. And then we can, in the cloud, securely do a matching and an aggregation, and we can return the IDs that match or don't match, and nothing else is disclosed. So next I will present the 2 solutions, the one that's based on HELIP and the one that's based on Payet. So basically it's how we realize the matching step. So for HELIP, what we do is we have the query Bloom filter, which encodes our query. So it's, if you look at this one, and we just take 1 hash function to map our SNPs into the Bloom filter, then this would be a Bloom filter that encodes 3 SNPs. The database Bloom filter will have a lot more ones in it. So what we have to do is basically we have to check for each column whether we have 2 ones. So we can map that just to a multiplication, and to do a secure multiplication on ciphertext, what we have to do is we have to have a encryption scheme that is homomorphic for multiplication. But since we have to do an addition later on, what we really need is a fully homomorphic scheme here. So here we use HELIP and just multiply bitwise the bits in the 2 Bloom filters, and we get a result Bloom filter. And in the result Bloom filter, of course, since we do multiplication, we will have ones exactly in those positions where the SNPs match. So in the end, what we just have to do is we count the number of ones in the result Bloom filter, and if we get as many ones as we have in the query Bloom filter, then we have a match. And we can do the counting also under encryption. So the second solution, or okay, so we run into one problem. Basically, if we encrypt each bit in one ciphertext, this will be horribly inefficient. So what HELib offers us is so-called SIMD slots. So basically, by manipulating one ciphertext, we can multiply many bits in the Bloom filter. So this is actually sort of batching stuff. However, since our Bloom filters have to be very, very big to not run into too many false positives, so you know that Bloom filters have some error probability, and I think we configured our Bloom filters to have an error probability of something in the order of 2 to the minus 64, so the probability is very low. Still, that makes the Bloom filters very large, and we cannot even hope of fitting one Bloom filter into one ciphertext. So what we do is simply we cut the Bloom filter into chunks, and then we operate on each chunk individually. So what we get is we get a lot of result Bloom filters, one for each chunk, and to aggregate them, we just have to add them. And then we return one ciphertext to the client, and the client has to decrypt only one ciphertext, which is good. And the second solution is a Palier solution. It's more efficient, however, it's a bit cheaty maybe. So what we do is, again, we encode everything as a Bloom filter, but before encrypting it with the Palier scheme, we introduce padding bits. So between each bits of the Bloom filters, we just introduce a 0 bit and encrypt this in the Palier scheme. So then what we can do is, on the cloud, we can use the additive property of the Palier scheme, and we can add those Bloom filters, and then we actually get in those padding bits. These are then carryover bits from the addition, which give us basically a bitwise AND. And then what we have to do is we have to return the whole ciphertext, which will be in the size of the whole database, which is not as good as in the HELib scheme. We have to return that to the client, and the client has to decrypt it and then count the number of ones in there, in the carryover bits. So we evaluated both solutions on the database with 100K SNPs and the database with 10K SNPs. So what you see on the top is the 100K SNP database, and for a query with 3 SNPs. But actually with our encoding scheme and our approach, it doesn't matter if you have 1 SNP in the query or 10 or 20. Just a little bit influences the error probability of the Bloom filter, but it doesn't really matter. So what you see is when you compare the two solutions, in the Palier solution, the yellow part is what the client has to do, so he has to do a lot of more work, but in total the runtime is maybe a bit more than half of it, and the same for the 10K database. But I think for this competition, the HELib solution was evaluated. So, in conclusion, our approach is based on HELib and Palier, and the main idea was to use Bloom filters, which enable us to do efficient matchings, and of course we have a possibility of false positives, which in this context is probably not as bad as having false negatives. So, and we can decrease the probability at the cost of performance just by increasing the size of the Bloom filters, or the number of hash functions that we use to map SNPs to Bloom filters. And to increase performance, we process Bloom filters in chunks. And this approach actually would also allow us to do a bit fuzzy queries. That's something that we're thinking about right now. And we think that we could also use the Palier approach with HELib. So instead of using Palier scheme, we could use the HELib, which would be faster. However, right now, HELib stores even bits as longs. Maybe we configured something wrongly or didn't compile it in the right way, but it would speed up things a lot if HELib would work also on single bits. So thank you very much.
Thank you. Actually, we evaluated both solutions. The Palea solution is very efficient. The reason why we didn't select that is because in our criteria we said you can only access up to 20 SNP and do 100 comparison locally. The Palea solution doesn't do less than 100 comparison on the local, so we picked a heat solution. So thanks for the great talk, and we have time for 2 questions.
Go ahead. For your first solution, the cloud knows that it's a match or not match, right? Cloud can find it out whether it's a match or not match, right?
For this one?
Is it the first one?
Yeah.
No, the first one was actually.
So this is the first solution based on HGLib.
Okay. So my question is whether the cloud can understand whether the find it is a match or not match. Do you get that information?
Only the cloud gets that.
Those filters with built-in hash functions?
Yeah, of course.
But you could use key hash functions, and with that you could upload to the database unencrypted, and then you will do simply a scalar multiplication, and you won't need a fully homomorphic encryption multiplication. It should be quite fast.
Sounds good. However, like you said, then you wouldn't need encryption at all, right?
Well, if you have
I don't know if that would satisfy the task required.
you publish hashes of an information which is secret, but keyed hashes, so they are protected by the security.
Yeah, I should mention that, as I mentioned, that we require the third task to be done in terms of encryption for this job.
Yes, but the database to query the query is encrypted, homomorphically encrypted. But
So,
the database
yes,
is not encrypted by homomorphic encryption. It's encrypted by a keyed hash function. But the query you send is of course an homomorphic ciphertext, but then you have a plain text and a ciphertext, and that's much faster than cipher to ciphertext multiplication.
So you're saying that you compose first use symmetric hash function to screen the database, and then you. But there's an issue with that because you may end up there's some risk with inference attack with the frequency of these issues.
Okay, let's thank our speaker and welcome the last team.
Okay, hello, good night. I would like to start by introducing myself. My name is João Sá, and I'm from EPFL. I'm a fresh software engineer at EPFL at Jean-Pierre's group. And today we're gonna talk about our solution to track 3 of this challenge. This solution was a conjoint work between 2 universities, so between the University of EPFL in Switzerland and the University of Toulouse in France. And also had a lot of people involved to come to our solution. So I could start with the motivation, but I'm the last group, so you've probably heard this 3 times already, but I will repeat it. So basically, what happens is we have the following scenario. So imagining we have this doctor, this data owner, which has a lot of genomic data. Stored in these VCF files, and he wants to send it to the cloud and then be able to securely and privately query the cloud without the server actually finding out anything about this information. So we can already identify 2 steps in this process. The first one is this initialization phase, where we want to securely store the information on the cloud to be accessed afterwards. And our querying phase, where we want our doctor to be able to do queries, to perform queries to our cloud server without the server finding out anything. So in terms of the requirements, we actually try to make things a little bit harder. I don't know. So what happens is that we had we divided into 3 requirements. So we have the architectural requirements, where we had to follow the client-server model. We had to enforce a specific bandwidth link and this one single round query reply. But then on the security kind of constraints or requirements, first we try to hide data, query, and access patterns from the cloud. We employ homomorphic encryption. We try to guarantee 80 bits of security. And then we have these 2. So first we allow for the search of anything, so not just the SNP, but everything. And we also try to reveal less than 20 variants during each search. One thing that was kind of a motive of discussion for today was the fact that we, as a standard, we used a VCF file with 5 million variants, and I will explain why this led to a lot of discussion. We decided to have this kind of VCF file because nowadays that's that's usually how many variants the person has, at least for now, and that's why we consider this specific number. So let's jump right into the protocol. So we start with the initialization phase. So what we do here is first we generate a symmetric key and an hash key, and what we do is that for each of our variants here in the VCF file, we basically compute an hash, so basically hash them. And from this hash, we extract a certain number of bits, which are we going to store in our encoding VCF file. Apart from this hash, so from this hash, which generates this tag, so from this tag, we also extract a certain number of bits, which will map to a specific position. So for example, if we go here for SNP number 2, we get the specific tag. This is just an example. We extract the 4 first bits, which maps to position 0, and we store it in the VCF file. Of course, with this approach, with this hashing approach, there are going to be some variants which will map to the same index. And so what we do, well, we just path them and consecutively, and we get something like this. And now we come to the 5 million VCF file. So what we do here is that after we do this mapping, what we do is that we add dummy data at the end of each of the lines, so that we hide the size of the VCF file. So we have in consideration the 5 million mutations, and we're going to hide. So we're going to add as much dummy data to basically the server, so to a VCF file with 1 mutation or a VCF file with 5 million mutations would be completely undistinguishable for the server. So they're always the same size, they're always the same number of entries, each line is always the same size also. Afterwards, we just symmetrically encrypt the data and we send it to the cloud. And then first we have this encoding phase, which we called it, and then our encryption phase. As I said, we're storing hashes, but this might be if we want to compute other kinds of operations on the data, not just retrieval, we could also alternatively switch it to an encoding where we could, for example, represent the operation with 2 bits, the chromosome with 5 bits, the position with 28 bits, and for example, the alternate database with the allele with 2 bits, and we could do this for different operations. And we could switch our hashing to an actual encoding. We have here an example on how could we do it. And so now we go into the
querying phase. So in the querying phase, what we have is we have our variant that we want to search, and we perform the first kind of similar steps. So we generate our tag, which is from the iDASH, and we retrieve the index where potentially that variant can be. And then we perform private information retrieval, XPIR, which was a library developed by our fellow colleagues at University of Toulouse. And what it does, it's basically, we have an array, which is going to be the size of the length of the database in the server, where we homomorphically encrypt an array of zeros and a 1 on the index that we want to search. So for example, here we're searching for tag 2, which is in index 0, so we put the homomorphic encryption of 1 in position 0 and the rest zeros. We send this to the server to perform multiplication, and whenever we have the encryption of zeros, we kind of erase that entry, and when we have the encryption of 1, we kind of absorb that specific index. Afterwards, we just add everything up and we get our results, so basically we get our first line. Afterwards, we just decrypt it, and we fetch the variant to see if it's actually there or not. In terms of the results, what we did, so we defined 4 different scenarios. First, we used this is the machine that we used to test the things. We used the HMAC SHA-256 to do the hashing, AES counter mode to do the first encryption, this first semantic encryption, and then the FV ring LWE scheme during the querying phase. And the setups for the file that we chose, so we chose a 5 million variant file, so it's a VCF file with 5 million variants, and which takes around 208 megabytes of space, and we perform 10 runs and kind of average the results out. So the setups we chose, so first we chose our default setup, and in this default setup we basically, so as you saw previously, we could actually retrieve more variants because we retrieved the whole line to the client. So in this setup we didn't care about how many variants we were retrieving to the client, we just decided to make it so that it would be the fastest, so we optimized the parameters so that it was the fastest solution. Then on the limit info we basically tried to fulfill the requirements of the competition by not retrieving more than 20 variants to the client. On our security setup, we basically increased our security parameters, and basically on our encoded one, we switched from hashing to the previous encoding scheme that I briefly presented here. In terms of the variables we have here, so you can see that the data hash size here basically says the amount of bits that we store from the hash, which is basically the same for all of the settings except for the encoded, where we stored an encoding, and then it's variable depending on whether it's a snip or whether it's an insertion. The bits of mapping allow us to map to a specific position in our encoded VCF, and will also give us the length, so basically the number of entries in the database. And then we have our padding size, and the padding size is basically the number of elements that we have to pad to in order to hide the number of elements that are in the database. So always having in mind our 5 million variant file as our model. The encryption mode, we used similar, so the requirements, always with more than 8-bit security, and we have this aggregation dimensionality to allow for the faster encryption, so we allow for encrypting multiple plaintext into one ciphertext, and this dimensionality which allows to introduce some recursion in the private information retrieval protocol. So in terms of performance, what we have is that if you look at our default, so the one where it's the fastest, we saw that we obtain around 2.18 seconds. So here we split this table in two sections. So the first section is basically the preparation phase, so the data preparation, the size of the encoded VCF file we get, in the protected VCF file we get, and the importation, the pre-computation that we do, and that in this section of the table, it's basically the protocol itself. And the time here is basically the round trip time, the turnaround time. So for our limit info, which is basically what was evaluated and it was matched with the other approaches, Of course, we got much worse performance because we needed a higher size database. But still quite good. And the same for security encoding. So all the time you can see that we can perform different tasks, and the time doesn't change that much. So in terms of the, we did this slide here because, so basically what happened is that right now, as our solution it is right now, it doesn't matter the size of the VCF. So if we have 10,000, 100,000, up until 5 million variants, this thing, so basically the turnaround time and most of these parameters are going to be exactly the same. It really doesn't matter because we always have to have enough data. So it's the same as when we have a VCF file of 10K, it's like saying we are querying a VCF file of 5 million variants. And so, yeah, so we could potentially not hide this number of mutations and just, and so we would basically, we didn't need to add any data. We would significantly reduce the size of everything, so of the VCF, of the query, and then of course we would have not just a faster setup time, but also better over turnaround performance. And we actually did it in a couple of minutes to actually see if what the result would be. And if instead of having the 5 million, if we just padded with 10, if we added the references 10K, we could actually make it much faster. So to conclude, we have our solution which kind of provides low querying time, confidentiality by using the symmetric encryption during the setup phase. We also allow for privacy, not just privacy in terms of private information retrieval, so all hiding the query, hiding the information that's in the database, but also the amount, so the number of mutations we have in a database, we also hide it. It's because we use lattices, it's relatively scalable, low storage complexity. By having the possibility of changing between hashing and encoding, we can also provide some generality, so we can probably compute something else besides extracting the data. And we try, there's some ways of minimizing the delivered data. However, this is not perfect, definitely not. And so what happens is, first, it's linear, the number of queries. So if you want to query 2 times, it's basically 2 times the same process, and which is not scalable. And then there's also this high overhead for small VCFs, because, like I said, querying a VCF with 1 variant is the same as querying a VCF with 5 million. So of course, if you have smaller VCFs, we have an higher overhead. And then we retrieve extra information. So there's this kind of situation where the client gets a little bit more information than just the query that he searched for. What we intend to do in the future is basically we intend to solve this extra information. We actually already solved it after delivering the project by adding this subtraction step, which we put it in a poster. I have some slides about it, but I'm not going to talk about it. Which allows us to completely just retrieve 1 variant. It kind of works as Microsoft explained about the subtraction that in the multiplication that they use, so it's the kind of the same idea. And we also intend to change a little bit the encryption scheme that's under XPIR library, so that we can try and solve this relatively big problem. We will try to see if we can solve it and make our solution much more scalable in this sense. And there I conclude my presentation. If you have any questions, feel free, and thank you.
Thank you. The solution is actually highly efficient. If it has a parameter that adapts to the length of the record, I think your performance will be much better.
Yeah, so basically we don't have like a specific parameter to do it. Right. We have to tweak 2 or 3 parameters, right. But yes, it's not intuitive to do it, to change it to kind of match, to reduce the 5 million to 10K or to 100K. And, exactly.
Okay, any questions? We have time for 2 questions.
Maybe one comment. Can you come back to slide 11? Because you went fast on that one.
Yeah.
So can you so if you read out the numbers, right, and read because it's not completely readable from here.
Yes, the quality of the image.
Focus on the row EPFL plus UT and then Microsoft. just go through those rows because you cannot read them.
Right, if you look at the total turnaround time, Microsoft is still faster.
Yeah.
It's 1.1 second, and the EPFL plus UT is 1.76. Actually, the top few teams are highly scalable. We tested on larger scale data as well, but in order to show all the numbers, we just put the 10K and 100K here. But I know your performance actually goes above like 2 million scale. That's great.
Yeah, it's just about the quality of my sleep tonight. I mean, yeah, number 4 after all that work is something that is hardly bearable. So if you look at this, and also with the optimization that Joe was mentioning, more or less in the ballpark of what Microsoft has done.
Yes.
Right? So
yes.
this is just
yes.
so the way it's just a matter. So we appreciate a lot all the work done by the organizers. We know how much effort it is. And we appreciate also that it is difficult to essentially define something that ends up on one scale, right? On a linear scale, while it is intrinsically multidimensional, right? But at the same time, if by just making use of the scheme you have, let's say the reasoning you follow for the evaluation of the various solutions, it appears that the numbers that you have shown, that were shown previously, were not correct, right? So this is
interesting. Right. Yeah, you can put the table in the final paper.
Right.
Yeah.
Right. So now I understand it's a bit late to let's say reallocate the wonderful gifts and awards you mentioned. I just wanted to mention this, and I asked Joao to let's say put the end of the title in larger font. He did not, but I would appreciate if this would be taken into account for the website of the event.
Yes, we'll correct that when you send me the result. But anyway, I think EPFL is one of the runner-ups in this context. According to our definition, we rank them by speed, memory use, and storage. Yeah. Okay. Thank you. Thank you all.
Okay, thank you.
So our next session is the award ceremony. And this year we had the great pleasure and the honor to have a few sponsors. So the workshop is officially sponsored by NIH through a grant mechanism called R13. And we sponsored 6 students. So if the students are in the room, please come here and let's take a picture together. Any students? Yeah, come. Yeah, the travel grant. Yeah, come here. Okay, take a picture. Oh, okay, sure.
Maybe not in front of the screen. There, that's fine.
Tell us where you're from. You can tell us where you're from.
My name is Susan Shah, and I'm from Princeton University. I was on the Microsoft team.
I'm Gizem Çetin. I'm a PhD student at Worcester Polytechnic Institute. I was working with the Microsoft team.
Hi everyone, I'm Zhi Yuan from Vanderbilt University.
Hi, Peter Rundall. I'm from Oregon State University and also on the Microsoft team.
Hi, I'm Mumin Aziz from University of Manitoba, master's student.
I'm from Maryland. I work on Maryland team.
Okay, so next, thank you. So next we will have awarding for the 3-track, and we will have Dr. Knox to give award for the 1st track. And thanks for Gene Cloud and Human Longevity for sponsoring this event.
Very nice. Congratulations.
Congratulations.
They want cash.
I'm sure. Anybody want to? Congratulations.
Blockchain.
Thank you. And also the second team from the first track, please come here. So we will have Dr. Heidi Sophia to award the second track. So in the order of IBM, University of Manitoba, University of Maryland, and Indiana University. So the IBM and the Cornell team, please come here.
Gilad's not here.
Oh, so
He had to leave.
can you come?
Yeah, but I'm not going to meet him.
The second team from University of Manitoba, please come here. Congratulations. The third team from University of Maryland. And the last team from Indiana. Thank you. Thank you all. So we will invite Dr. Ono Machado to award the third track in the order of Microsoft, Seoul National University, COMSIS, and EPFL. So please come. Microsoft.
Then we have. Do you want to come all the team?
Congratulations. Seoul National University. COMSIS. EPFL.
I would ask the remaining of the team. So no, come on. I would ask also Joey and Chichon to come, and also Carlos.
And we'll mail the check, in case you're wondering. Fake money. Fake money.
Okay, I just have a few final conclusion remarks, and then I will hand over to Dr. Heidi Sophia from NIH to talk about a few things. So this year we actually observed like a great progress. At the end of the last competition, I was really worried because we have been seeing such a big progress, and I was worried there's very little room for improvement. Thinking like, what if like we only have incremental performance improvement? But indeed, this year's result was surprising, and as Xiaofen just mentioned, for the secure multi-party computing, the improvement was from like 998 seconds down to 11 seconds, and the scale was larger. And for homomorphic encryption, our improvement was like a 2 magnitude in scale and performance. And in beacon data sharing, the two teams both performs better than our baseline, and everything was like just amazing. As a community, we are really moving forward, and we're thinking about the next steps for our competition. So this year we have been seeing a lot of highly optimized solution, which like customized to the target of our questions. And just like if we say 5 queries, then the parameters will customize and optimize to that. So in the future, maybe we're thinking about doing some more generic solutions, and also come up with additional topics beyond the genetic testing and similarity search.
Yeah, another interesting, important thing is, and we believe we have this is the third round competition, right? And I think the things are moving toward the state that we already have a set of technique, right? And we're making progress on the basic problem. So the question becomes, is it possible to using those building blocks to build up something, build up a framework, a toolkit, a kind of system, first step system, which exposed to the bioinformatics community to let them start using the things we already, the technique we have discovered, and we are making progress in our, during our 3 years competition. And in the first years, we're still very far away from there. And the last years, we step closer. But I think this year, looking at the result, already, I think some outcome, there's chance to be used by, bioinformatics community, in our opinion. So I'm thinking about, we just want to get an opinion from you guys. Well, at some point, if you guys are willing to share your toolkits and your technology, and we somehow and either open source code or provide some service to help the bioinformatics, to encourage the bioinformatics community to start using those techniques. We want to get an opinion from you guys.
Right. So we also think about next year's topic arrangement. So we would like to have everybody's feedback, and please let us know what you think, like what topic we should include. So please submit the feedback through this link after the workshop, and we welcome everybody to send us the input. And the final slide from me is tomorrow we have this Genome Pride workshop at Hilton, Chicago. Many people are joining, so people who don't know this, welcome to join us. It's just a one-day event. It will be very exciting. We have a lot of exciting papers from different perspectives. So, yeah.
Yeah, sorry to interrupt. First, I want to thank everyone for coming. I think it was very exciting. What I think we need to do for next year is go one step above and actually get a question that is of medical importance and have it done on the real genome, so protected ones. And I think that will start showing the community that we can do that in a protected fashion, and that it's, and it's also practical. So let's think about a real problem that needs to be solved. It was very good so far, but it can be even more exciting if we put it into context.
So if Suresh is already at 23andMe, why don't we ask them for data?
Yeah, or we could, some things, if done on an enclave with authorization from, for example, the organizers to run the algorithms, then it can be IRB approved and everything. So we can have our own data or DBGAP data used for this purpose, and I think it will be very exciting. But we need to plan well in advance because of the IRB and other issues.
Well, so there's a good example of this right now with the New England Journal of Medicine sprint competition, which I think would they got a good streamline down for doing data use agreements and IRB protocols for human subject exemptions in the U.S. at least.
Right.
So something to look at.
Yeah, I think we have 1 year, so it's kind of sufficient for UCSD's IRB approval.
All right, thanks. And Dr. Heidi Sophia can come. Yeah.
Oops, there's
Okay, I'm here from NHGRI, which is now funding the iDASH Privacy Challenge. And I want to let you know that I'd actually really like to speak to anybody who's interested in NIH opportunities in privacy technology development. So if you have any questions or want to kind of hear about latest developments or where NIH is at in that regard, please feel free to contact me and talk to me about that. I'd love to talk to you about it. Also, my colleague, Ed Ramos, is available for a similar type of discussion. I'm here through GenoPri and through the Monday of the AMIA meeting, and then he's coming in kind of a tag team way, and there really is this developing interest at NIH in privacy, not just genomic, but other data types as well. And so it's small but growing, probably pretty rapidly. So you can contact either of us directly by email or in person, but he will also be at the NLM booth at AMIA number 404, and that'll be on Tuesday from 11 to 1 p.m. if you want to talk to him. So next slide. So NIH is really getting interested in new models for data sharing, new ways to protect data, and so part of the growing interest. Previously, you could really say that the approach has been very black and white, all or nothing. It's completely locked up and safe, quote unquote safe, or it's fully public. But there's beginning to be an appreciation of the idea of levels of sharing and levels of risk, and putting together the social, the policy, and the technical sides to map up the levels of risk and models of risk. So this is just one concept. The NIH genomic data sharing policy requires grantees who've produced a certain level of data to deposit that data in this controlled access resource dbGaP, and it's kind of hard to get the data out again. It's hard to use that data, and partly in response to that, there are a limited number of trusted partners of the dbGaP resource, but those are required to be contracts, and that's also been very limiting, and really that was done on purpose, to be very conservative and to take very slow steps towards sharing data. But there's increasing recognition that this is not a very good model. So this is just a scheme, this is just one model, and it's just meant to be kind of an impressionistic model. But you could say that in this picture, that the more intense the color, the more sensitive the data, and you could say that the yellow part is dbGaP, or a trusted partner contract, where the data is very sensitive, and the size of the circle, you could say, illustrates the number of potential direct users of that data. So you can imagine, this is a kind of a picture of levels of risk and levels of access, where the larger the circle, the larger number of people that might potentially be able to use the data. So maybe just in terms of how NIH could take kind of conservative steps, because this involves changing policy, and that's quite hard. So building a rationale to change policy in constructive ways, a first conservative step might be, well, it's like a trusted partner, but it's if you could use grant mechanisms, that would be very, very enabling and open up the opportunity to many, many more people than requiring an actual contract mechanism. And so maybe one way to do that is you're not sharing the raw data, but you're bringing tools to the data. And maybe if you just let people download results at will, maybe you're still actually requiring full dbGaP authorization in that scheme. That's just one hypothesis. But maybe if you actually start measuring privacy leakage of the data, as was suggested earlier, actually try to detect how much is going out, then you could have a lighter weight just user registration. And then maybe if you have data that you want to just completely make open and free and fully publicly accessible, then you, if you try to measure how much you're actually leaking, at least you have a rational basis for it. And so I think a scheme like that brings real empiricism and real measurement is something that NIH could really benefit from. Because right now it's very much rule of thumb, and decisions are often made on the policy side, just best judgments. Well, surely that must be safe to share, without real quantitative knowledge and feedback on what is actually being done. So creating this empirical framework for bringing the policy together with the technology, I think would be a really significant next step for NIH. Perhaps fairly ambitious, but I think it's a lot of opportunity and a lot of desire to make it happen. And I think that people in this room, really have the ability to work together, contribute, and make this happen. So once again, please talk to me at Ramos, and bring us your creative ideas and the solutions that you can bring to the table. That'd be fantastic. Thank you very much, everybody.
Thank you. That concludes. Go ahead, Jeffy.
Can I say just something? So thank you very much. I would like to, I'd like to bootstrap actually everyone's mind about the discussion that we're going to have tomorrow at the end of GenoPride. Thanks to the efforts of several people, including the organizers of iDASH this year, we managed to bring the two events together, right, to collocate iDASH and GenoPride, which I think it's a good thing because it facilitates tremendously the cross-pollination between the two events that have a lot in common. Now, the thing is that for GenoPride, it's good to have it, let's say, to alternate. So far we alternated between Europe and US, so it was it was Europe and then US and then US. So it might make sense to go back to Europe in 2017. Now, I understand that NIH is a US organization, and so I was wondering to what extent it would make sense for iDASH at some point to go abroad to demonstrate also the willingness of the US government to open to the world. And see, I mean, so try also to see, to project maybe in the 1 or 2, 3 years to come, how those things could be organized. So Lucia was telling me that actually iDASH might go back to San Diego next year. It's not a big leap towards Europe, but right. So we'll have to figure out. So this is a discussion we're going to have tomorrow at the end of GenoPride, but we'll be happy to discuss this also beforehand, because it's good to make this kind of discussions and possibly decisions on site as opposed to let's say after the event. Yeah, well, that's it. Thanks.
Thank you all. So this concludes our workshop, and when you get out, there's a gift bag with popcorn. We have 100 bags, so please take plenty.
Thank you to the organizers.
Thank you.